Managing diverse types of data effectively is crucial for modern organizations to drive informed decision making and optimize operations. Understanding the characteristics and storage solutions for structured, semi structured, and unstructured data enables businesses to harness the full potential of their data assets and overcome challenges such as data silos and governance. In this course, you will learn about the historical challenges of working with data, including difficulties in accessing, managing, and analyzing large volumes of diverse information. You will explore the characteristics of structured, semi structured, and unstructured data and discuss the problem of data silos that hinder comprehensive analysis and decision making. Next, you will learn about the characteristics of various data storage systems. You will explore relational databases for structured data with complex relationships, document databases for semi structured data, and more. We will also examine data warehouses for analytical querying and reporting, and data lakes for storing vast amounts of raw data to support advanced analytics and machine learning. Finally, you will explore how to choose the right storage paradigm based on specific use cases and data requirements. You will examine the distinctions between first, second, and third party data and analyze the data value chain. Additionally, you will learn about data governance, including the policies and procedures needed to ensure data quality, privacy, and security. Hello, and welcome to the next course in the Google Cloud Digital Leader Certification journey. Enterprises that are slow to recognize and adapt to change in their operating environment are doomed to stagnate and eventually to fail. Organizations recognize this, which is why they have a healthy level of respect, even fear for change, especially big change. Over time, enterprises have found that one of the most reliable ways of coping with change is to be quick at spotting change in the operating environment and then getting ahead of that change. How is such change to be spotted? Well, by constantly scanning the environment for data signaling such change. And that in turn is what drives home the existential importance of data to organizations and enterprises. There was a time not so long ago where a primary challenge facing organizations was how to collect data. There just wasn't enough good, reliable data to go around. These days, that's rarely the issue. The problem these days is figuring out how to unlock business value from that data. How is raw data, which is collected from the environment, to be converted into actionable business insights? The good news is that the cloud is here to help. In particular, one of the most transformational ways in which the cloud helps organizations unlock business value from data is by making sense of hard to process data, usually unstructured data, which has been perhaps collected by the organization for a long period of time without really being processed or used in any meaningful way. In the last decade or decade and a half, in quick succession, enterprises have adopted big data technologies, the cloud, and now also AI and machine learning, all of which combine to help businesses leverage the data that they already collect from their environment a lot more effectively. Here, it's worth our taking a moment to understand some of the reasons why organizations have historically struggled with extracting value from their data. For one, the data was often siloed. Here, the silo might be organizational or technological. At one level, there might be different departments which collect differing types or quantities of data. That would be an organizational silo. There are also technological silos where information or data is gathered into incompatible systems. There was simply no way for two or more different stores of data to communicate with each other. This problem of limited integration between different data systems was often solved in the most manual and tedious fashion possible. Manual processes have many flaws, and being error prone is one of the most important ones. Another important challenge that enterprises used to face was that of limited storage and processing capabilities. These limits manifested themselves in the form of both storage and processing constraints. Storage constraints were typically solved by being selective about what data was actually stored. Along the way, data was lost, all because the traditional storage system just couldn't handle the volume of data being generated. Processing power was another bottleneck. Analyzing large datasets required significant compute resources. These were often unavailable or too expensive. Even after memory and storage both became cheaper and almost ubiquitous, it took some time for analytical tools to catch up. Consider, for instance, many legacy versions of Microsoft Excel, which only supported up to 256 columns ending in IV. If you wanted to process any more data than that, well, you then had to resort to manual and time consuming processes, which once again suffered the flaw of being error prone. Sticking with the Excel example, the astronomical salaries commanded by Excel jocks on Wall Street highlight another issue that organizations used to face: a skills gap. There simply was a serious lack of expertise. There weren't enough professionals with the skills needed to analyze and interpret data effectively. And this skills gap, of course, hindered the ability of an enterprise to leverage its data for strategic purposes. More recently, these constraints were overcome to a large extent with the advent of big data processing technologies. Now, the term big data itself is an interesting one. It's quite hard to define. A common definition centers around the three V's: volume, velocity, and variety. Once organizations were able to use tools that could cope with a high volume of data coming in at high velocity, maybe even streaming data, and cope with a variety of data sources, new possibilities were unlocked. The ability to deal with high velocity data meant that real time analytics could be generated. Machine learning and artificial intelligence focused heavily on dealing with image and text data, which in turn meant that unstructured data could be mined for insights. Once organizations began to understand their data better and better, they then began to innovate, coming up with actionable insights based on that data. And in all of this, cloud computing played an absolutely starring role, because it's actually cloud computing technologies which unlock the full potential of big data processing. The early appeal of cloud computing centered around its scalability, flexibility, cost efficiency, and elasticity. Scalability, because you could add compute and storage as and when you needed them. Flexibility, because you weren't tied down to the capex or capital expenditure of all of those compute and storage resources when you did not need them. This elasticity in turn led to the cost efficiency and the benefits of OPEX versus CAPEX. Over time, however, the cloud platforms have evolved and now have incredibly compelling offerings for data storage and management. They have specialized offerings for data warehouses, which specialize in analytical use cases, and data lakes, which specialize in working with unstructured data. We'll have more to say on those terms in a bit. In addition, the cloud platforms also now provide advanced tools, which allow you as an enterprise to seamlessly make use of AI and ML technologies. And because there's a constant arms race between the hyperscalers in order to see who can come out with the best AI ML offerings, you as the enterprise customer stand poised to benefit. The Google Cloud Platform, just like the other hyperscalers, has a large number of services meant for storing, analyzing, and generally working with data. As an aspiring digital cloud leader, it's important that you have an informed point of view on the choice of data technology, and in order to form such an informed point of view, you need to clearly understand the difference between structured, semi-structured, and unstructured data. Now, we are going to spend a lot of time understanding each of these types in detail, but first, some important examples. Data in an Excel spreadsheet or in BigQuery is structured. Data on Google Drive or in Google Cloud Storage in the form of text or images, that's unstructured. And how about semi-structured data? Well, examples of that would be data in JSON or XML format, HTML content, or for that matter, files in YAML format. So again, do keep these examples in mind. Now, let's take some time to understand each of these types in detail, starting with structured data. As the name would suggest, structured data is extremely organized. Typically, this is tabular. For instance, data in an Excel spreadsheet or in a relational database table lends itself naturally to being stored in rows and columns. Notice also that in the case of a relational database table, there is also a schema, where we effectively have rules about the types of data contained within each of the columns. In addition to the schema, relational databases also allow us to specify constraints which effectively are rules governing the relationships between items within that data. The effect of the schema and of all of these relationships is to impose data integrity and also to make it easy for data validation to be carried out. The data integrity comes from all of the constraints which can be enforced via the schema as well as via unique key, foreign key, and other constraints. It is important to note that while relational databases contain structured data, there are plenty of other use cases of structured data beyond relational databases. For instance, in a simple user input form, you might have a field of type email. Here, the data is going to be checked to ensure that it contains the @ symbol. A particular field might be a date and therefore must follow a specific format, or a field might effectively enforce a business rule. For instance, that price cannot be negative or that the discount cannot exceed a certain threshold. We encounter structured data all the time and take for granted all of the convenience that it gives us. Consider a CRM solution, for instance, where we'd have fields for the names, addresses, and purchase history of various sales leads. Another extremely common example, which we've already mentioned, is spreadsheet data. For instance, financial data in an Excel spreadsheet might contain revenues, expenses, and budgets. Spreadsheet software such as Microsoft Excel or Google Sheets use a tabular format in order to organize data, where each cell represents a discrete data point. CSV files are plain text files which follow a similar format, except that commas are used to delimit the data fields. Finally, consider the example of transactional data, such as maybe online sales transactions or inventory records. Such data could be stored in a SQL database. Now, SQL, of course, is a language which is used to access the data in a database. Databases such as MySQL or PostgreSQL and Oracle will make use of the relational data format where the rows represent individual records and the columns represent data fields. Looking at these three examples altogether, we can also see how easy it is to move structured data from one form of technology or storage to another. For instance, it's trivially simple to load data from a CSV file into an Excel spreadsheet or a relational database. Likewise, even the CRM system which we referred to probably makes use of a relational database at the back end. Again, this kind of data is relatively unlikely to be siloed because it can easily flow from one application to another. That is one of the main benefits of structured data. It's always relatively easy to extract structured data from a data source and move it to another. For the same reason, it's also relatively easy to analyze structured data using available tools, Microsoft Excel being perhaps the most famous. Equally important and probably more powerful are the business intelligence tools, such as, for instance, Tableau or Power BI. Data warehouses, such as Amazon Redshift, are also excellent for working with structured data. On the Google Cloud platform, BigQuery is a great OLAP tool for working with structured data. You could also make use of relational database offerings from Cloud SQL or Cloud Spanner. Users of spreadsheet software such as Microsoft Excel or Google Sheets tend to love working with these technologies because of their immediacy. That actually is a property of the type of data that these programs work with. Structured data is highly valuable because it's immediately available and it's relatively easy to perform real-time operations on such data. Structured data has been used by enterprises for decision making for far longer than the other two types of data. There are good reasons for this. Of course, structured data is far easier to work with. Companies can quickly analyze such data and make informed decisions. And that's why top level executives have been using structured data for decision making for pretty much a century. There are also important benefits when it comes to operational efficiency, for instance, in reducing errors, flagging errors, or anomalies. Let's say, for instance, that you were a quality control manager in a process that focused on manufacturing widgets. You'd want to know how many defects existed per batch, and a good system for working with structured data is pretty much all that you would need. Lastly, structured data is also great from a regulatory and compliance perspective. A regulator might find it easy to collect the same data in a uniform format from a large number of regulated entities. If all of that data is structured, it could then also be queried and analyzed more efficiently. Next, let's turn our attention to semi-structured data. Common examples of semi-structured data include JSON, XML, HTML, or log files, and semi-structured data has become a lot more important with the rise of cloud usage. As its name would suggest, semi-structured data lies somewhere between structured and unstructured data. Structured data is the most organized, and semi-structured data is partially organized. This means that it does not usually have a strict predefined schema. Consider an email, for instance. That's a pretty common example of unstructured data. Every email message has distinct sections for the sender, recipient, subject, and body. However, there's clearly no fixed schema across all emails. This points to one of the great strengths of semi-structured data. Because it does not have to adhere to a strict schema, it's more flexible and can adapt to more use cases. As the data requirements change, new fields and data types can be added without disrupting the existing structure. This makes it easier to integrate data and carry out updates across systems. Semi-structured data often contains tags or markers, and these are types of metadata to help provide context and hierarchy to the data elements. This term hierarchy is particularly important in the context of semi-structured data. In fact, maybe the key difference between semi-structured data and unstructured data is that there is some semblance of hierarchy in semi-structured data. These tags or markers are all too familiar to people who work with JSON or XML or even HTML. The tags help to organize and identify the data and separate out sections. It's worth noting that this hierarchical structure explicitly allows nested elements. This nesting of elements is a way to represent relationships within the data, and indeed, by making use of these nested elements, you can end up with very complex hierarchical data representations. This in turn allows us to specify rich and detailed data models. Did you know, for instance, that Excel spreadsheets can be represented entirely in XML format? All of the data in an Excel spreadsheet can be represented as a directed acyclic graph, which in turn can be written out in XML format. This hierarchical nature of semi-structured data leads to one of its great advantages, which is its scalability. Semi-structured data truly allows us to work with very large data volumes and express very complex relationships. Also, semi-structured data formats such as JSON and XML are explicitly designed to be machine readable and human readable. Now, in reality, JSON or XML formats can quickly get very complicated and very hard to read for a human user, and that's why there are specific tools and querying languages such as XPath for XML or JSON Path for JSON. These technologies are built upon the machine readability of the underlying data. That machine readability then allows these technologies to answer human queries. The relationships expressed in semi-structured data are more complex than those in relational data, and that's why the query languages mentioned here, like XPath or JSON Path, are more complex than SQL. It's worth noting here that semi-structured data is often stored in NoSQL databases, and these in turn often make use of distributed storage to enable horizontal scaling and high availability. On the Google Cloud Platform, Firestore would be a document database that you could use for such data. Next, let's turn to some examples of semi-structured data. We've discussed these at some length already. These include JSON or XML files, the fields and contents of an email, or the contents of log files. In case you've not encountered these terms previously, JSON is short for JavaScript Object Notation. This is a lightweight data interchange format. It's easy for humans to read and write, and it's also easy for machines to parse and generate. JSON objects are collections of name-value pairs, and arrays are ordered lists of values. XML stands for the Extensible Markup Language, and a markup language simply defines rules for encoding documents in a format that is both human and machine readable. HTML is another example of a markup language. Next, let's turn to another example of semi-structured data, and that's an email. As we've already mentioned, every email has several structured fields such as the sender's and the recipient's email addresses, the subject line, and the timestamp. These fields are standardized, and that makes it easy to organize and search emails. In addition, however, the actual body, that is the text of the email, is completely unstructured. This part could vary greatly in format and content. It might just have simple text, it might have complex HTML, it might even have embedded media and attachments. So an email is a bit different from JSON or XML in that it consists of an entirely structured component and an entirely unstructured component. Log files are another example of semi-structured data. Log files often have a structure where they have some timestamp fields and some data fields. The timestamp fields might contain records of events where each is marked with a timestamp. These provide a chronological record of activities and system states. The data fields are more unstructured. These might contain event types, source, severity level, and also a detailed message content. You can imagine, for instance, an exception stack trace. Semi-structured data is not quite as straightforward to work with as structured data. To begin with, because semi-structured data often has complex relationships, these might include hierarchy, nested relationships, or even nested hierarchies. Because of all of this, the tools required to extract value from semi-structured data are themselves more complex. They need to be able to deal with the less rigid structure. This gives rise to the need for NoSQL tools and ETL, that is, extract, transform, and load tools such as the technology PIG. A general rule of thumb is that semi-structured data is going to need more processing or pre-processing than structured data before value can be unlocked from it. Despite all of this, in recent years, enterprises have been unlocking more and more value from semi-structured data because they found that doing all of that work is worth it. The juice is worth the squeeze in this case. To begin with, semi-structured data lends itself ideally to the integration of diverse data sources. What kinds of diverse data sources? Well, these could be a combination of web services, APIs, IoT devices or sensors, social media, emails, and log files. Clearly, the systems which generate these different types of data are not going to be interoperable. But the semi-structured data which they generate is self-describing, and so their outputs can be integrated. Another key benefit of semi-structured data is the agility and the adaptability of the data. Unlike relational data, which has to adhere to a complex schema, semi-structured data can allow for quick adaptation. If the business environment is changing, well, the data format can change as well. For the same reason, application developers usually find it easier to work with semi-structured data. There are fewer rules that you need to adhere to while performing your rapid prototyping. Finally, semi-structured data can also lead to richer data analysis. One important reason for that is that semi-structured data allows you to represent more complex relationships than simple relational data. These complex hierarchies and nested structures, which are possible with semi-structured data, can also lead to more insights and more nuanced analysis. For all of these reasons, semi-structured data has been rapidly rising in importance in recent years, particularly as technologies make it easier and easier to deal with its complexities. Structured data has been a key part of enterprise decision making for generations. Semi-structured data is just getting there. Having dealt with structured and semi-structured data, now let's turn our attention to unstructured data. You can think of this as information which does not have any predefined data model or schema. Unstructured data is usually stored in a native format, such as an image file, for instance. This is the hardest kind of data to work with, but it is also very often the most prevalent and the most common kind of data that an organization collects. The challenges that arise while working with unstructured data are indeed formidable. It has no predefined structure, which means that there's no fixed schema, there are no rules which govern the relationships, and it's very hard to perform data validation. Also, such data comes in a large variety of forms. It could include text, images, videos, audio files, and more. This variety makes unstructured data extremely rich in information, but it's very difficult to get that information out and get actionable insights from it. Vast quantities of unstructured data are generated and collected by virtually every enterprise. You can imagine that sources such as social media, IoT devices, multimedia files, interactions with customers on the phone or via video conferencing, All of these are vast quantities of unstructured data that can be mined by an organization. The complexity of the unstructured data comes not only from its variety and volume, but also because it's so context dependent, and also because there are so many hard to identify sources of information. Think, for instance, of the tone of voice of a customer in an interaction with a customer service representative. Inconsistency is a very important word in the context of working with unstructured data. In fact, a lot of the excitement around AI models in the recent past has been because of the ease with which AI models are able to cut through all of this inconsistency. Think of a multimodal LLM, for instance. The input to such an LLM could be in the form of voice, image, or a text prompt. It's all the same. And that is why some of the biggest and most exciting advances in recent years in data processing have come in working with unstructured data. Each of these typical types of unstructured data has its own challenges and potential rewards. At one end, we have text documents. These could include Word documents or PDFs and text files. Such documents can contain a wide range of information. However, the lack of structured fields has made it difficult to extract specific information. That has changed dramatically in recent times with the advent of large language models. Other important types of unstructured data include multimedia files such as photos, videos, and audio recordings. Each of these requires its own specialized processing techniques such as image recognition, video analysis, and audio transcription. Multimedia files contain very rich visual and auditory information, and once again, AI has been at the forefront of unlocking all of this information from such data. There are also some very common types of semi structured data which are dominated by the unstructured data that they contain within. We've already spoken about social media content and emails, but this is true of web pages as well. Social media content, for instance, could include tweets, Facebook posts, Instagram photos and captions, and YouTube videos. Social media generates a mix of text, images, videos, and also user interactions such as comments and likes. Social media vocabulary is often fast changing and also might use special code words to get around content moderation, for instance. All of these add to the challenges of extracting insights from such data. Traditionally, unstructured data was the most likely to be locked up in data silos, but that's changing dramatically with the rise of AI and machine learning tools. It's worth noting here just how important the role of the cloud is in enabling all of those AI and ML techniques. The sheer quantum of unstructured data is such that you really need cloud based scalable storage solutions and distributed file systems in order to be able to do anything meaningful with such data. Because of the great variety in the sources and types of unstructured data, there is also now a great variety of tools and technologies for working with it. NLP, or natural language processing, is used for text and sentiment analysis, entity recognition, and more. Image and video analysis can be performed with tools such as TensorFlow, OpenCV, and AWS Recognition, amongst others. Likewise, there are also speech to text and audio feature extraction libraries to help you process audio data. Ever since the advent of LLMs in late 2022, there's a veritable gold rush amongst companies to try and unlock the benefits of unstructured data. Enterprises are constantly using sentiment analysis to see how customer reviews and social media posts about their products are trending. Behavioral analysis is being used in order to find insights about effective ways of dealing with angry or disgruntled customers. Organizations are also finding ways to squeeze operational efficiencies out of such unstructured data. This could range from processing or analyzing call center transcripts or emails and support tickets to predictive maintenance using sensor data and maintenance logs to predict when machines or other critical components might break down. Such data also drives innovation, and it can help a company maintain or enhance its competitive edge. For instance, a company might be looking for clues into product development. What kind of product would be welcomed by its target demographic? Market trends. What kinds of products are showing unexpected popularity? Unstructured data, even more than structured or semi structured data, is an ultimate driver of enhanced decision making. There are vast quantities of such data, and it's very hard to extract the insights from it. But really, organizations that are able to perform comprehensive analysis of all of their structured and especially of their unstructured data are likely to be a crucial one step ahead when it comes to making the big decisions. Now that we've understood how structured, semi structured, and unstructured data differ from each other, it's time for us to move on and understand some of the basics of data management, specifically on the cloud. The hyperscalers offer a wide range of data management and storage services, and a lot of those are designed specifically to deal with the problem of data silos. Data that is in a silo is isolated. It's not easily accessible to other parts of the organization other than the folks who actually collected it. This separation of data into silos often occurs because the data is stored in different systems by different departments. For example, different databases that do not easily communicate with each other. Data silos hinder an organization's ability to have a comprehensive, holistic view of its own data. This leads to inefficiencies, duplication, and missed opportunities. When people talk about large bureaucratic organizations where the right hand doesn't seem to know what the left hand is doing, it's often a data silo issue that they are getting at. Let's enumerate some of the problems that data silos cause. To begin with, the fact is that when data is siloed, there is no single source of truth. Different departments or parts of the organization have multiple and potentially conflicting versions of the same data item. Without this unified data source, it's very difficult to make sure that everyone in the organization is on the same page. Decision making becomes unreliable because of inconsistencies, and this fragmentation can also erode trust in data accuracy. Almost invariably, when data is siloed, different parts of the organization decide that it's easiest to just create copies or replicas of the original data. This leads to its own challenges, even beyond that of there being no single source of truth. Now that there are multiple copies of the same data stored in different locations, storage costs and management complexity also increase. And of course, there are the problems of synchronizing all of the changes across those multiple copies. This can result in data inconsistencies and increased administrative overhead. This problem of inconsistency in the data is a serious one. It slows down all of the processes of the organization, creates confusion and mistrust, and can also lead to poor customer experiences. This also has a corrosive effect on the culture of the organization. As in large bloated bureaucracies, once data gets siloed, it invariably leads to questions like who owns which data? Organizational turf battles break out because ownership of the data is unclear. The ambiguity over who is responsible for the accuracy, security, and compliance leads to breakdowns in data governance. All of this replication of data can lead to significant storage costs. Every department ends up storing its own version of the data, and high storage costs strain IT budgets, they require additional resources, and this in turn impedes the organization's ability to scale efficiently and invest in strategic initiatives. Lastly, this siloing of data can cause difficulties in meeting audit requirements. Data silos make it hard to meet audit and governance requirements because the data is dispersed and not easily accessible. That in turn can lead to legal and financial penalties and damage the organization's reputation. Inconsistent records make audits more labor intensive and error prone and often lead to costly remediation efforts. Data silos are a really serious problem, and enterprises have often found it very difficult to leverage their data, particularly their unstructured data, because of this data silo issue. Thankfully, the cloud providers now have a large variety of data offerings. These are carefully customized and tailored to help beat this data silo problem. These offerings can broadly be classified into three categories: databases, data warehouses, and data lakes. Let's understand each of these in turn. The cloud platforms make it a lot easier to deal with the problem of data silos than it used to be. Data storage technologies on the hyperscalers can be broadly classified into three types: databases, data warehouses, and data lakes. Of these three categories, databases and data warehouses both specialize in working with structured data. Data lakes, on the other hand, are meant to work with unstructured data. The difference between databases and data warehouses comes down to the type of use case. Databases specialize in OLTP or transaction processing, while data warehouses are more suitable for OLAP or analytical processing. There are different types of database offerings: relational and non-relational. Relational databases typically have data structured in tabular format with predefined schemas. These support the ACID properties of atomicity, consistency, isolation, and durability. Offerings of the relational type on the Google Cloud Platform include Cloud SQL, through which you can make use of SQL Server, MySQL, and Postgres, as well as Cloud Spanner. Non-relational or NoSQL databases, on the other hand, store data in more flexible schema-less formats. There are different types of NoSQL databases. These include document databases, key value stores, wide columns databases, and graph databases. On the Google Cloud Platform, examples of NoSQL database offerings include Bigtable and Firestore. Other popular NoSQL databases include MongoDB, Cassandra, and Redis. Let's run through a simple example of how a relational database sets up its data model. Here you can see that we have two tables, customers and orders. The customer table has a customer ID, that's a primary key, and then the customer name, billing address, shipping address, and other properties. There is a link between the customers table and the orders table because the customer ID is the primary key of the customers table and has a foreign key relationship with the customer ID column in the orders table. That's because we want to make sure that any order in the orders table references a valid customer ID. In addition, in the orders table, we also have other fields such as the order ID, the order date, shipping date, and order status. The basic unit of storing data in a relational database is a table. The table in turn has rows and columns. The schema governs the relationships between the different columns and the type of data that can be stored within each column. Each row effectively refers to one logical record. Tables belong in logical groupings called databases. All of this data is accessed via SQL or the structured query language. We can now list out some of the common characteristics of relational databases, beginning with structured data storage. The data is stored in tables or relations which have predefined schemas. These consist of rows and columns. Each row represents a record and each column represents a field or an attribute of the data. Relational databases are schema-based, which means that the structure of the data must be defined before the data can be stored. Such products are also referred to as schema-on-write products because whenever data is added to a relation, all of the schema rules and relationships will be checked. Any attempt to insert data into the database that violates the schema will be rejected, and in this way, the database maintains data integrity and consistency. SQL, or the structured query language, is the common way of accessing data in a relational database. It has powerful and flexible commands for data retrieval, insertion, updation, and deletion. It's also widely known. Because so many folks know the SQL language, data gets somewhat democratized. Relational databases support the ACID properties, short for atomicity, consistency, isolation, and durability. This ensures that transactions can be supported. These are groups of operations which are all executed in an all or nothing fashion. The ability to roll back or commit a transaction, that is, a group of operations, ensures the data is stored reliably and that the database remains in a consistent state. Finally, in a relational database, data is stored in normalized form. This means that the tables are designed to eliminate redundancy and ensure logical data organization. This normalization of data is usually performed at the table design stage. Large tables are divided into smaller related tables, and the database allows us to define relationships between them. Relational databases are extremely widely used. For instance, in the case of financial systems, in applications which require high data integrity and consistency for transactions, relational databases are ideal. while working with customer relationship data, storing and managing detailed customer information and information about interactions and transaction histories, all of these are perfect use cases for OLTP or online transaction processing. Relational databases are also favored for ERP or enterprise resource planning use cases such as accounting, procurement, project management, and supply chain operations. Finally, in healthcare use cases such as storing patient records, appointment schedules, billing information, and medical histories, once again, relational databases are a product of choice. Notice how each of these use cases centers around transactions and requires consistency and transaction support. It is for good reason that relational databases are the most popular and widespread of the data management technologies. They provide data integrity and consistency by enforcing schemas and making sure that the asset properties are maintained. Even complex queries are easy to write using SQL. This is especially true because SQL is now widely known and understood. The widespread use and standardization of SQL has made relational databases compatible and interoperable with a large variety of applications and tools. Finally, transaction management is a very important requirement in many use cases. Consider, for instance, the database behind an ATM network, where thousands or maybe millions of customers are performing withdrawals and deposits at the same time. In such a complex multi user environment, reliable transaction support is critical. Relational databases are not without their limitations, and a primary one is scalability. Relational databases struggle with horizontal scaling, that is, scaling out across multiple servers, and they are much better suited for vertical scaling, that is, scaling up a single server, making it more and more powerful. The rigidity of the schemas in a transactional database can also become a drawback. This makes it difficult for relational databases to work with unstructured or semi structured data, and new data types or changes in the data environment lead to schema changes and are quite heavyweight. Although SQL makes it very easy for folks to write complex queries, the performance of these complex queries can sometimes leave much to be desired. When writing complex joins on large datasets, it's very easy to get a significant drop in performance. Finally, relational databases have a justified reputation for being costly. The licensing and maintenance costs can be quite high for enterprise grade relational database systems. Next, let's turn our attention to non relational or NoSQL databases. These store data in a more flexible and schema-less format. There are different flavors of non-relational or NoSQL databases. These include document databases, key value stores, wide column databases, and graph databases. For our present purposes, we are going to focus on two types of NoSQL databases: key value stores and document databases. As their name would suggest, key value stores store their data as key value pairs, where each key is a unique identifier. The value, on the other hand, can be data of any type, such as a string, JSON, or even a binary object. The main appeal of a key value store is fast lookup or fast retrieval of the value given the key. For this reason, key value stores are great for applications requiring fast retrieval, such as caching, session management, and configuration storage. Key value stores are schemaless. This makes them flexible, but they also have rather limited querying capabilities beyond the key-based lookup. Let's consider a simple example of a key value store and the data contained within it. You can see here that the key corresponds to the employee name, and the values correspond to information about each of those employees. The values are themselves in dictionary form. For instance, the employee Jason Schaap has the key Jason Schaap. The value is a dictionary which contains two attributes: the title, which is VP, and then the salary, which is 100,000. Looking closely at this data, we can see that each of the three employees has a title. However, 2 out of 3 have a salary field, the third does not have a salary and instead merely has a department. This is an example of the flexibility that is given to us by key value stores. Let's say we had wanted to store the same data in a relational database, then we would have a fixed schema where we would have the key, which is the employee name, and then we would have columns for title, salary, and department. In this kind of a fixed schema design, we have a lot of nulls in the data. And what's more, the data would be relatively static in terms of its schema. For instance, let's say we wanted to add a new field, such as city or location, we would have to explicitly modify the schema of the relational table, add a new column called city, and populate it with nulls for all of the pre-existing data. With a key value store, all that we'd have to do is to add a new city field to any new records that we store in our database. Let's quickly talk about some of the characteristics of key value stores. Key value stores have a very simple data model. Here, each data item is stored as a key value pair. The key is the unique identifier and the value is the associated data. The whole point of this key value store data model is to allow for fast data retrieval using the key. Given the key, you would like to access the value extremely fast. Key value stores are schemaless. Unlike relational databases, they do not require a predefined schema. The value can be of any data type such as a string, number, a JSON, or even a binary object. Also, the fields within the JSON themselves are not fixed in any way. This flexibility allows for dynamic changes to the data structure without having to modify the schema. Finally, key value stores are designed for high performance and scalability. They can deal with large volumes of both read and write operations efficiently. They scale easily, both horizontally and vertically, in order to accommodate growing data loads. Let's consider some common use cases of key value stores. Caching is one extremely popular use case. Key value stores are often used for caching data. This helps to improve application performance by reducing the load on a primary database. This, for instance, would be used in storing session data in a web application. Another common use case is in configuration management. Storing configuration settings and preferences for applications is another place where key value stores shine. Online shopping carts are another classic use case for key value stores. Let's enumerate the pros and cons of key value stores. The first pro is simplicity. The data model is simple, and this in turn leads to excellent performance, particularly for retrieval of the value given the key. Key value stores are optimized for fast data access and high throughput. As we've seen, key value stores are schemaless, and this allows them to support dynamically changing data. On the other hand, they are not without their limitations. The querying capabilities are limited. Lookup of the value given the key is very fast and optimized, but any other kind of querying is likely to be difficult and may not even be supported. Data relationships are hard to express in key value stores, and so if your data has complex relationships and if you'd like to perform joins, then key value stores are not your choice. Key value stores also often only offer eventual consistency rather than strong consistency. This might not be suitable for all applications. A quick word on the difference between eventual and strong consistency. In most horizontally scaled systems, there is some form of replication going on so that data items exist in more than one location. When an update is made to a particular data item, the question is, will the next retrieval of that data item fetch the stale value or the new value? If all retrievals are guaranteed to only fetch the correct updated value, then that's said to be strong consistency. If, on the other hand, it is possible for some retrievals to end up with the stale value, that's known as eventual consistency. Key value stores often only offer eventual consistency guarantees, in contrast to relational databases which support the asset properties. Let's quickly take stock of where we stand now. As we discussed, data silos are a major problem, and cloud offerings come up with three broad types of products in order to solve this problem: databases, data warehouses, and data lakes. Within databases, there are SQL, that is relational databases, and NoSQL databases. We are currently talking about two of the flavors of NoSQL databases. We finished discussing key value stores. Now let's quickly talk about document databases. Document databases are optimized for data which is document oriented, such as, for instance, JSON or XML data. They allow for complex nested data structures, and as we've already discussed, Data in JSON or XML tends to be hierarchical and also has nested elements. Document databases provide schema flexibility, thus, different documents within the same collection can have differing structures. Document databases also support much more advanced querying, indexing, and aggregation than key value stores. This makes them suitable for applications like content management systems, product catalogs, and user profile management, where diverse and evolving data models are required. Here's a quick look at what document-oriented data might look like. Here, we have a snippet of JSON code which represents a single customer. The customer ID is user123, and then we have sections for other information such as the name. The name itself is nested in that it contains two subfields, first and last. The highlighted fragment doesn't look that different from what we might put in a key value store. There, name would be the key and the value would have the first and the last names. In a document database, on the other hand, these are known as fields and values. So here, name is the field and the value is a dictionary containing two subfields, first and last. Let's enumerate some of the characteristics of document databases. To begin with, of course, they focus on document-oriented storage, that is, for documents in JSON, XML, HTML, or BSON formats. Such data is semi-structured and it has fields and values. Documents can have nested structures, arrays, and dynamic fields. Another attribute of document databases is schema flexibility. Different documents within the document database do not need to conform to a fixed schema. This allows for flexible and evolving data models. As an aside, a commonly used term for a group of documents is a collection. So all of the documents in a particular collection do not need to have the same schema. Schema flexibility also makes it easy to store and retrieve complex data structures. In contrast to key value stores, document data stores provide rich querying support. The relationships that can be specified using data such as JSON or XML can be very complicated, involving nesting and arrays, and all of this is supported via document databases. Technologies such as XPath or JSON Path support field-based queries, indexing, and aggregation. Just like key value stores, document databases also have their classic use cases. One of these is in content management systems. These require the management and storage of diverse types of content such as articles, blogs, and multimedia files with varying structures. For such use cases, for example, storing and retrieving web pages and user-generated content, document databases are a natural fit. Product catalogs on e-commerce applications are also likely to be built using document databases. Each product will have different attributes, categories, and specifications. Such data lends itself naturally to being expressed using XML and in turn to being stored in a document database. Finally, user profiles and preferences are also often stored in document databases. Each user may have different sets of attributes and settings. Let's take a balanced look at the strengths and weaknesses of document databases. An important strength, of course, is flexibility. There's no predefined schema, and the structure of the XML or the JSON can be dynamic and change from one document to the next. Secondly, document databases support complex queries. As discussed, it's possible to run indexing, field-based queries, and aggregation on document contents. Thirdly, document databases are great for working with nested hierarchical data. Of course, document databases come with their own limitations, the first of which usually relates to consistency. Similar to key value stores, document databases often only support eventual consistency and not strong consistency. Secondly, they often incur heavy storage overhead. Documents can be large, storing data in text format is not always efficient, documents themselves might contain much redundant data, and therefore such databases have relatively high storage requirements. Finally, the performance of document databases can suffer when we perform complex queries and indexing, especially with large document datasets. We've now discussed a wide range of database technologies. Let's return to our taxonomy of data storage technologies and now talk about data warehouses. Data warehouses differ from databases. Databases tend to focus on OLTP, that is transaction processing use cases, while data warehouses tend to focus on OLAP, that is analytical processing use cases. You can think of a data warehouse as a centralized repository which holds a large volume of structured data. That structured data might come from multiple sources. In contrast, databases tend to focus on data from a single source. Data warehouses are optimized for queries and analysis. They aggregate data from different transactional databases, create curated datasets, and thus help management with a comprehensive view for business intelligence and reporting. Data warehouses are built for read heavy operations and support extremely complex queries and data mining activities. Let's take a quick look at how a data warehouse could be used in an enterprise setting. We can see that data flows from left to right. Over on the left, we have data sources. These could be individual data sources, which include CRM or ERP software, SQL and NoSQL databases, as well as potential sources of real time data, such as IoT devices or social media and websites. We also might have data which comes in from spreadsheets or flat files. We can see that the data sources include the databases that we've referred to. Relational databases as well as NoSQL databases both appear prominently in this list. The data from each of these sources is then effectively aggregated and various transformation operations are carried out. Here, the acronym ELT stands for Extract, Load, and Transform. The transformed data is then actually passed into the data warehouse itself. This is represented by the storage layer. Without going too deep into the implementation, it is worth noting the metadata manager. The data warehouse effectively maintains metadata about all of the data coming in from the different sources. By the end of this process, we have curated datasets which are ready for consumption for different use cases. That consumption could be either through API, that is programmatic access, or by simply running SQL queries. That in turn leads us to the presentation layer, where we have business intelligence tools. These are executive decision making support tools such as Power BI or Tableau. We could also have dashboarding and reporting tools, as well as various business applications and operational systems. To summarize this complex architecture, the inputs into a data warehouse come from different sources. The data can be structured or semi structured, and the outputs tend to be focused around decision making activities. It's important to note that data warehouses cannot store unstructured raw data. That's what data lakes are for. All of the hyperscalers have their own data warehouse offerings, and of course, BigQuery is the data warehouse offering on the Google Cloud Platform. All of these data warehouses have some common characteristics. They are all centralized repositories for data which comes in from multiple different sources. That data is aggregated, stored, and managed, and all data warehouses are designed to handle large volumes of data and to integrate information from various transactional systems, such as relational databases, as well as other external sources. Data warehouses are optimized for querying and analysis, also known as analytical processing. These are typically read heavy operations which involve the use of complex queries, data analysis, and reporting. In order to support such operations, data warehouses have specialized storage architectures such as columnar storage. This helps to enhance query performance and speed. Data warehouses are typically not great if you have a lot of writes going on with your use cases. Complex analytical queries used for decision making and business intelligence often rely heavily on past trends and on comparing present data to past trends. For that reason, data warehouses have to store historical data in large volumes. This is important for business intelligence and strategic planning. Data warehouses focus on structured and semi structured data, and they tend to be schema based. So the data in a data warehouse is highly structured. There's a predefined schema to ensure consistency and integrity. The data that comes into the data warehouse might be semi structured. However, it's going to be transformed and cleaned during the ETL, extract, transform, load process before it's actually loaded into the data warehouse. Data integration is an absolutely key feature of a data warehouse. The whole point of the data warehouse is to integrate data from diverse sources and provide a unified view for cross-functional analysis. ETL tools and processes are then used to consolidate, transform, and load data into the warehouse. Again, all of this is only possible if the data warehouse supports data integration from different sources. That's why data warehouses make it especially easy to get data in or to ingest data from differing sources, such as relational databases, spreadsheets, and so on. Data from transactional databases is a primary input into data warehouses. This could be from operational systems such as ERP, that is Enterprise Resource Planning, CRM, Customer Relationship Management, or POS, that is Point of Sale Systems. Note that ERP, CRM, and POS systems are all focused on structured data and on transaction support, that is, support for essential day-to-day operations. In addition, data warehouses are also set up to ingest data from external data sources, which are often streaming data sources in nature. These might be IoT devices such as sensors, which send out a continuous stream of readings and metrics. They might be sources such as social media feeds or data from third party providers. Support for streaming data is also important in the context of data warehousing if real time insights and context are required. It's also important for data warehouses to work with flat files such as CSV files and spreadsheets, particularly Excel and Google Sheets. These files are often used for data that is manually collected or temporarily stored. Finally, data warehouses also integrate closely with cloud services and APIs. These sources serve as yet another way to get real-time or near real-time data feeds into a data warehouse. Next, let's talk about the types of data stored in data warehouses. Typically, this takes the form of structured or semi-structured data. Structured data often comes in from relational databases and usually adheres to a predefined schema. Examples might include sales transactions, financial records, customer information, and inventory data. This is effectively raw data that's taken from a transaction processing system and placed in the data warehouse. In addition, it's also common to aggregate and summarize data before placing it in the data warehouse. That way, it's more suitable for high-level analysis and reporting. Examples of such aggregated and summarized data might include monthly or quarterly sales totals, revenue, or customer segmentation metrics. As we've already mentioned, historical data is typically found in data warehouses. Historical data is important for identifying and analyzing trends because that's what a lot of business intelligence and higher level executive decision making processes are about. Finally, because data comes in from so many different sources and passes through so many complex transformation steps, it's critical for the data warehouse to also contain metadata, which describes the origin of the data, the transformation processes, the storage details, and so on. This includes information about data lineage, quality, and governance. Maintaining correct metadata is very important because otherwise, through all of the complex transformations, the audit trail of where a particular result came from could be lost. Effective metadata management will guard against that possibility. BigQuery is quite possibly the most popular service on the Google Cloud platform, and data warehouses in general are incredibly popular and useful. One of the most common use cases, of course, is for business intelligence and reporting. So, sales performance reports, financial analysis, operational dashboards. Use cases around data mining and analytics are also very important. This is where complex queries are carried out in order to uncover patterns, correlations, and other insights. For example, market basket analysis, customer segmentation, and predictive analytics. The curated datasets contained in data warehouses are often consumed by high level executives for strategic decision making. This includes budget planning, market expansion strategies, and risk assessments. Lastly, data warehouses are also very important from a regulatory compliance perspective. Organizations store historical data in data warehouses, and this helps to meet regulatory requirements, and it also maintains comprehensive and auditable records. Once again, in this context, maintaining correct metadata is crucial in ensuring that an audit trail is preserved. Use cases related to compliance include financial reporting, compliance audits, and data retention policies. By this point, the strengths of data warehouses are pretty obvious. Comprehensive data integration is one. A data warehouse integrates data from multiple sources and provides a unified view for comprehensive analysis and reporting. The data warehouse products are workhorses for the hyperscalers, and each of them has highly optimized performance, high speed querying and complex data analysis, quick access to large datasets, and support for consuming data via APIs as well as SQL. As we've already discussed, data warehouses are also great when you'd like to perform historical analysis, and also because they help to maintain data consistency and quality. Even if the data coming into a data warehouse is only semi-structured, it is usually processed using an ETL pipeline in order to ensure that the transformations and standardizations lead to structured data that is easily consumed using SQL. Of course, there's no free lunch, and one of the common gripes about data warehouses is the high associated costs. These are expensive products due to the infrastructure, software, and ongoing maintenance. Secondly, data warehouses are complex. Managing a data warehouse requires specialized skills, including data modeling, setting up the right extract, transform, and load processes, and database administration. Data warehouses are also relatively inflexible because they are not optimized for a high volume of write operations, and also because they impose schemas and relationships on data that comes in. So data warehouses are similar to transactional or relational databases in being less agile than NoSQL databases. Finally, data warehouses are typically updated via batch processes. They are optimized for fast reads of large quantities of data, and they are not optimized for numerous small updates. This in turn can introduce latency into data availability, and so they are not always perfect for real-time data systems. It's now time for us to turn our attention to data lakes. These are optimized for dealing with unstructured data. The data lake offering on the Google Cloud platform is Google Cloud Storage. Data lakes are vast storage repositories. They are meant to handle large volumes of raw, unstructured, and sometimes semi-structured data. Unlike data warehouses, data lakes store data in its native format. This gives data lakes a great deal of flexibility in data storage and retrieval. They can store pretty much any kind of data: text, images, videos, log files, and all of these types of files can be kept in the data lake until such time as they are required for processing. The results of that processing might then be placed in a data warehouse. In recent years, one of the primary use cases for data lakes has been to serve as the starting point for machine learning or AI related applications. Advances in AI and ML have made it possible to deal with and extract insights from unstructured data such as text, images, video, and audio. The raw text, image, audio, or video files will reside on a data lake. Let's take a look at how the data lake architecture typically fits into an enterprise cloud system. Over on the left, we have the sources of data as usual. Notice, however, that these data sources are spewing out data in their own proprietary formats. So here, for instance, we do not find any relational databases or document databases amongst the sources. On the other hand, here we might have document inputs such as PDF files or device logs, output data from IoT sensors or CCTV cameras, all dumping complex unstructured data into the data lake. Then, after a relatively rudimentary ETL or extract, transform, load set of operations, this data is placed in the lake. Here, we have object storage, metadata storage, and replications. We'll come back to the topic of object storage. You've possibly heard that technologies such as Google Cloud Storage offer object storage rather than either file storage or block storage. And that's because all of the data stored in a data lake is effectively treated as an object. There is the underlying raw data, but then there is in addition also a lot of metadata. It's very important to note that the data processing layer in a data lake needs to support data governance, security, and administration. Data governance can be thought of as a comprehensive set of policies to govern the entire life cycle of data from the point where it's ingested to controlling access as to who can view or work with that data, and finally to the correct disposal of that data subject to various compliance and regulatory requirements. Features such as role-based access control to make sure that only appropriate users can access the data, lifecycle management to ensure that data is preserved for the required length of time while also optimizing storage and retrieval costs. All of these come under the ambit of the security and administration within the data processing layer. This data in the data lake is then set up via more complicated ETL operations, and an API is provided, which in turn makes the data available for its end use. These could be enterprise data warehouses, that's abbreviated EDW for short. It could be analytics dashboards, data visualization applications, or data science projects. Consider, for example, an e-commerce retailer which collects each day an image representing the volume profile for that day. Each image is then going to be dumped in the data lake. Over time, there may be thousands of such images. Those images might then be subject to some kind of clustering or ML algorithm, the results of which would be written out to BigQuery. So here we have the raw image data in the data lake, that's Google Cloud Storage. The APIs would allow an AI or ML clustering algorithm to be applied to that data, and then information about the clusters would be written out to BigQuery, that's the enterprise data warehouse. The images themselves might be viewed through a data visualization application. It's worth emphasizing that data lakes store the raw data in its native format. This adds flexibility to the cloud architecture, and in this way, organizations can apply various schemas and structures as needed, but all of that happens after the data in the data lake has been processed and possibly placed in a data warehouse. This also has the benefit of mitigating bias. By retaining the original data, analysts reduce the risk of introducing biases that might occur during pre-processing. In this way, all subsequent downstream analysis are going to be based on the unaltered, authentic information. Data lakes help to preserve detail. All of the granular details and nuances that might be lost during transformation or aggregation are still available in the raw data. You can imagine again the image clustering use case we just mentioned. Every image is going to be reduced to a single number, that's the cluster ID. The cluster ID loses a lot of the detail in the original image, but that original image is still available in the data lake. In a sense, retaining the original data also future-proofs any modeling or aggregation process. Over time, advances in AI and ML models might lead to the development of new analytical methods and tools. At any point in the future, let's say a new and more advanced clustering algorithm is developed, all we need to do is to go and apply that new improved algorithm to all of the original image files. And in this way, we've effectively future-proofed our AI ML application. Let's talk about some of the characteristics of data lakes. To begin with, data lakes are schema on read. This is in complete contrast to relational databases, which are schema on write. In a database, every time you write data to the database, the schema is going to be checked, and if the data violates the schema, it's going to reject that write operation. This is not how data lakes work. Here, the data is going to be stored in its raw format, and it will only be structured when it is needed for analysis. This, of course, leads to a great deal of flexibility. Data can be written into a data lake even if it does not fit a predefined schema. In this respect, data lakes are different from data warehouses as well. Remember, the data warehouses have data which must fit a predefined schema before storage. The whole point of a data lake is to support vast volumes of raw data. For this, they need to be extremely scalable, and that level of scalability is best achieved using horizontal scaling. It's not difficult for a data lake to store petabytes or even exabytes of data. This scalability has to be achieved using distributed storage systems, and each of the hyperscalers has its own such storage system: Amazon S3, Google Cloud Storage, or Azure Blob Storage. Cost-effective storage is yet another important feature of data lakes. In contrast to data warehouses, there's no transformation of the data into a proprietary format. Because it's stored in its native format and in very large quantities, Data lakes are usually significantly cheaper than either database or data warehousing applications. Thus, they can serve as a staging area for data until use cases which feed the data into a data warehouse. Data lakes are explicitly designed to work with a very wide variety of data. Because the data continues to be stored in its native format, this could include text, images, videos, audios, log files, and more. Finally, data lakes serve as a starting point for advanced analytics. Imagine, for instance, that a company has stored voice recordings of all interactions between customers and its customer service representatives. Such recordings have quite possibly been stored for many years. Recently, with the advent of advanced AI techniques for processing voice and audio data, new capabilities have come online, and all of that old pre existing data, which is stored in a data lake solution, can now be passed through one of these advanced AI models. That's a fairly common use case for data lakes in the context of AI and machine learning. Data lakes, like data warehouses, integrate data from multiple sources. Of course, the difference is that they do not process that data in any way. Even so, data from inputs such as transactional databases and our familiar examples of the ERP, CRM, and point of sale systems, which have structured transactional data, these can all be dumped out into a data lake. External data sources such as social media feeds and the IoT devices also can feed their outputs into a data lake. Likewise, flat files and spreadsheets, including CSV files, log files, or multimedia files, containing the most classic examples of unstructured data such as images, videos, and audio. This might include surveillance camera footage, social media feeds, or multimedia applications. This list is very similar to that for a data warehouse. Of course, the difference is in the way or the manner in which the data is stored in the data lake. The most common use cases for data lakes tend to focus on unstructured data, but there's actually nothing preventing a data lake from holding structured or semi structured data, or even real time streaming data for that matter. However, out of all of these types of data, unstructured data can only be stored in a data lake. You cannot place unstructured data directly into a data warehouse or a database. So, even though all four types of data can be placed in a data lake, the most widespread use cases are for unstructured data. Let's turn to some of the use cases of data lakes. The first of these has to do with big data analytics. The input into a lot of big data analytical algorithms, such as AI and ML procedures, tend to be unstructured data which resides in a data lake. These two categories of use cases have become particularly important in the last year or 18 months or so with the advent of large language models and new advanced techniques for working with audio, video, and text. There are also the more classic use cases such as data archiving. For some enterprises, compliance and regulatory reasons might dictate the storage of very large quantities of data for a very great length of time. In such a case, a data lake might be a cheaper and more cost effective solution than a data warehouse. It's also common for real time analytical use cases to rely on data taken from a data lake before it is further processed and placed in a data warehouse. And along the same lines, data integration and preparation as a prelude to putting the data in a data warehouse, these are all classic use cases of data lakes. Let's wrap up with a balanced look at the strengths and weaknesses of data lakes. The first and primary strength is flexibility. The schema on read approach allows for flexible and dynamic data structures, and it also allows files from diverse data types to be stored without any predefined schemas. Integrating data from multiple sources is also simple in a data lake. Of course, that integration is very loose. Effectively, the data lake is just a repository. It doesn't link up or establish any relationships between the different kinds of data. Another great advantage of data lakes is their scalability. They are designed to deal with very large volumes of data and to scale horizontally and accommodate ever growing data needs. Relatively speaking, data lakes are very cost effective. Object-based storage in data lakes is far cheaper than the proprietary data storage that we have in the case of data warehousing solutions. They also support advanced analytics as discussed, because they are effectively a staging area for more complex processes which will process the raw data and place the results into a data warehouse. Of course, data lakes have their own limitations, and one of these, surprisingly, has to do with complexity and governance. It's very easy to start using a data lake. It's not quite so easy to set up the correct governance and lifecycle policies. Consider a Google Cloud Storage bucket, for instance. You've got to make sure that you set up data governance to restrict access using role based access control. In order to optimize the cost, you might need to set up the right storage classes and lifecycle policies. There's a lot of complexity if you've got to use data lakes just right. Data quality issues can also arise because of the schema on read approach taken by data lakes. Effectively, it's quite common for data lakes to become a dumping ground of sorts for all kinds of data, sometimes of dubious quality. Performance can become a problem, especially if you're comparing access speed in a data lake to that in a data warehouse. This is especially true while dealing with unstructured data or large datasets. Finally, it's extremely important for enterprises to set up the security of data in a data lake correctly. As the dictum goes, security of the cloud is the responsibility of the cloud provider. Security in the cloud is the responsibility of the end user. Object storage, such as through Google Cloud Storage, is often through URLs, and for that reason, it's very easy to access data in a data lake. Correctly setting up role based access control is extremely important in this context. As a Google Cloud digital leader, it's important for you to have a strong, well informed point of view on the correct choice of storage technology. We'll go through a set of use cases and the steps that you can use in order to identify the correct technology for your use case. But before that, there's another term that we need to familiarize ourselves with, and that is a data lakehouse. As of June 2024, there's no direct lakehouse offering on the GCP. There are some other lakehouse offerings which we will get to in a bit. First-party data is collected directly by the enterprise from a customer or from audience transactions and interactions. It's the most reliable type of customer information because it comes directly from the business's own activities. Next comes second-party data, which is obtained usually through partnerships or agreements. Enterprises are able to use such data to get additional insights beyond their own proprietary data. This is some other organization's first-party data that is being shared by that organization with our enterprise. And so we must be mindful that the sourcing enterprise might have changed or tweaked or redacted some portions of that data. Finally, we have third-party data. This is collected and managed by organizations that have no direct relationships with the customers of our enterprise. These datasets are aggregated from different sources and help with broader market insights and can contribute to audience segmentation. Examples of first-party data might include website analytics, pages viewed, time spent on site, and user behavior. Similarly, the classic workflow for a data lake, which collects data from many different sources and stores all of that data in its native form in the data lake. Most importantly, this data could be unstructured data. For instance, it could be multimedia, video, audio files, or simply text files without any discernible structure. All of this data in the lake then can be processed using data prep and validation and then consumed by machine learning, data science, or other reporting purposes. You can think back to our example of all of the raw images which are stored in a data lake, which are then going to be processed using a clustering algorithm, and the resulting cluster IDs will be written to a data warehouse, and the raw images might be used in a visualization. The workflows for data lakes and data warehouses are clearly somewhat different from each other. However, very often as end users, what we really want is one unified workflow where all data, whether it's structured, semi-structured, or unstructured, is then passed through data prep and validation or ETL pipelines and then either stored in a data mart or consumed for the various end use cases. This architecture that you now see on screen has a single system for all use cases, whether those use cases are related to business analytics, that's typically the strong point of data warehousing, or machine learning. typically the forte of data lakes. This is hard in the paradigm where we have only data lakes or data warehouses. However, using an architecture known as the data lakehouse, it is possible to combine business analytics and machine learning and AI use cases in the same workflow. As on date in June 2024, this architecture is not directly available via a single GCP offering. However, there is a Google white paper on how it can be implemented using various component GCP services. There are also other competing platforms which do have their implementations of the data lakehouse architecture. Microsoft Fabric is one. Iceberg tables in Snowflake also tend to approximate a data lake implementation. On the AWS Lake Formation is the service that you can use if you are interested in a lakehouse architecture. Let's now understand some of the characteristics of data lakehouses. To begin with, they have a hybrid architecture which seeks to combine the best of data warehouses and data lakes. This gives us a unified architecture which supports both structured and unstructured data and which can be used for both BI use cases as well as AI ML use cases. Data lakehouses provide schema flexibility. In this, they are different from data warehouses and they are more like data lakes. They support schema on read as well as schema on write. This means that they can store raw data in its native format and apply those schemas only during data retrieval. It is also possible to enforce schemas upon data ingestion. Once again, you can see that you can go with either the data warehouse approach or the data lake approach. Data lakehouses are great at efficiently processing data. They make use of technologies such as Apache Spark and Delta Lake, and in this way provide robust data processing capabilities for transformation, cleaning, enrichment, and they also help with complex analytics and machine learning workloads. Data lakehouses provide unified data management. This means that they integrate all of the features such as data governance, security, and metadata management, thus helping with data governance, that is, control of every aspect of the data over its life cycle, from ingestion all the way through to disposal, and making sure that only authorized users get access along the way. Data lakehouse architectures are carefully optimized to incorporate indexing, caching, and query optimization techniques, and in this way, data lakehouses somehow manage to provide good performance for both transactional and analytical workloads. Because they heavily rely on data lake for the storage layer, data lakehouses provide both scalability and cost effectiveness. Remember again that for data lakes, it's no big deal to store very vast quantities of data running into petabytes or even exabytes. That's the whole point of unstructured data storage. Unlike data warehouses, data lakes do not convert the data into a proprietary file format. And by leveraging this feature of data lakes, lakehouses are able to provide that scalability and cost effectiveness. Now that we've understood the compromises that data lakehouses make between data lakes and data warehouses, let's return to our original question. How do we decide on the right type of storage from between databases, data warehouses, and data lakes? Databases are optimized for transaction support. So if you need to handle structured data with high transactional integrity, and if you require real-time read and write operations, then databases should be your choice. Databases are ideal for operational applications with frequent data updates, that is, frequent write and update operations on the data. Data warehouses are geared towards business intelligence analysts, data scientists, and executive management. So you should use data warehouses when you need to perform complex analytical queries, when you need to generate reports from historical but structured data. Data warehouses are ideal for strategic decision making, trend analysis, and business intelligence. They are not great when you have a lot of write or update operations on your data. Data warehouses typically work best when only batch write or update operations are performed. Data lakes are typically used as repositories of vast amounts of raw, unstructured data. They can also, of course, hold structured or semi structured data, and they are best used by data scientists and engineers, machine learning engineers, and big data analysts. You should use data lakes when you need to store and process large volumes of data of diverse data types, including unstructured or even multimedia data such as images, videos, and text. They are ideal for big data analytics and AI ML operations. Once those operations run through, the results are typically going to be stored in more structured form in a data warehouse. These were general guidelines. Let's now see how we can make the choice between these three types of technologies based on specific criteria. If you are working only with structured data, then you are down to only choosing between databases and data warehouses. If your structured data requires ACID support and transaction support, then a traditional database is appropriate. On the other hand, if you're working with any unstructured data at all, i.e., if you're working with only unstructured data or a mix of unstructured, structured, and semi structured data, then a data lake might be suitable for you. Next, let's turn to use case. If your application requires real time data access and transaction processing, and if it has a lot of real time writes and updates, then you should use a relational database. If you're focused on historical analysis and reporting, or complex queries and business intelligence operations, then a data warehouse is ideal. If you are working with big data analytics or machine learning, then you should go with a data lake solution because you'll probably have large quantities of unstructured data, possibly in the form of images, audio, or video, and this raw data is best stored in a data lake. In terms of scalability and performance, if you have a high volume, high velocity use case, that is, if you need to ingest large volumes of data at high speeds, then a data lake is the most scalable. If it's optimized query performance that you are focused on, specifically with large datasets and structured data, then a data warehouse is preferable. If budget is an important consideration for you, data lakes are usually more cost effective, especially for large volumes of raw data. So let's say, for instance, that you have a very large data set, which is structured data, where you could possibly load this into a data warehouse. For budget reasons, you still might choose to just place it in a data lake, such as a cloud storage bucket, temporarily, and then later, when the usage becomes more urgent, you can process it and load it into a data warehouse. Finally, from a data governance and security perspective, if you are in a highly regulated domain and robust security measures are important for you, then data warehouses and databases are typically better and easier to use than data lakes. On the other hand, if flexibility is more important and you are relatively lightly regulated, then you might find that a data lake offers more flexibility in data governance. There, you will be able to apply security and compliance policies as needed. It's always worth remembering here, though, that security of the cloud is the responsibility of the cloud provider. Security in the cloud is the responsibility of the end user. Google believes that we are currently in the transformation cloud era. Enterprises are now using the transformation cloud to drive holistic change in their companies. They are aiming big, not just making small infra related decisions when it comes to the cloud. Rather, they are literally aiming to transform their businesses. In this context, it's worth talking about the role of data in a digital transformation. Specifically, there are three types of data here which have different roles to play: first party, second party, and third party data. First party data is collected directly by the enterprise from a customer or from audience transactions and interactions. It's the most reliable type of customer information because it comes directly from the business's own activities. Next comes second party data, which is obtained usually through partnerships or agreements. Enterprises are able to use such data to get additional insights beyond their own proprietary data. This is some other organization's first party data that is being shared by that organization with our enterprise. And so we must be mindful that the sourcing enterprise might have changed or tweaked or redacted some portions of that data. Finally, we have third party data. This is collected and managed by organizations that have no direct relationships with the customers of our enterprise. These datasets are aggregated from different sources and help with broader market insights and can contribute to audience segmentation. Examples of first party data might include website analytics, pages viewed, time spent on site, and user behavior, customer purchase history, information on products purchased, frequency of purchases, and transaction amounts. email campaign data, and metrics from campaigns run by our marketing team, including open rates, click through rates, and responses. And finally, customer feedback. This could be direct customer feedback through surveys, reviews, or interactions with customer support staff. First party data is the most pristine and can play a critical role in a digital transformation. Personalization is a classic use case of such data. Companies can deliver tailored experiences to customers, thereby driving engagement and satisfaction. After all, the company has the full history of its interactions with a given customer. Secondly, customer insights at the aggregate level can be obtained by analyzing first party data. The enterprise can derive insights into customer behaviors and preferences, see how those are changing, and possibly launch new products or innovations in order to capitalize. First party data can also help drive operational efficiencies. Because such data is often linked to our own enterprise's business processes, it can be used in order to find bottlenecks or areas of weakness or shortcoming. Finally, first party data usually scores very highly on compliance and trust. Because it's been collected directly with explicit customer consent, it often meets regulatory requirements more easily than second party or third party data, and it can also be used to build customer trust through transparency. Over time, discerning customers are able to figure out which enterprises treat their first party data respectfully and which do not. And over time, the ones that do are going to be rewarded. Next, we get to second party data. This is essentially someone else's first party data. It's been made available to our enterprise through a direct relationship, such as a partnership or an agreement. Use cases for this type of data in a digital transformation include media driven partnerships, where a media company shares its audience data with an advertiser to help tailor ad campaigns. Or there could be event data sharing. For instance, a tech company might partner with an event organizer to access attendee data for a technical conference. A third example could be retailer partnership data. Maybe a clothing brand obtains sales and customer demographic data from a retailer that sells their products. If personalization is the primary use case for first party data, then expanded reach can be thought of as the corresponding primary use case for second party data. Companies gain insights from data that they do not directly have access to, and this expands their understanding of the market. This expanded reach can then be used in order to create enhanced customer profiles. By augmenting first party data with second party data, an enterprise can better target its marketing campaigns. Finally, second party data can also lead to very fruitful collaboration opportunities and strategic partnerships. This data sharing between two enterprises can drive mutual benefits and innovation. Finally, we have third party data. This is collected by entities that do not have a direct relationship with the consumers that the data describes. The data has been aggregated from different sources and sold to our enterprise. Examples of third party data include market research reports purchased from reputed market research firms, which help give clarity on industry trends and consumer behavior. Demographic data providers, including companies such as Nielsen or Experian, also offer comprehensive demographic information, and like the closely related market research reports, these can be used in order to derive information or insights on consumer behavior patterns. Ad networks also collect information about user interactions and preferences. They do this across multiple websites and platforms. Finally, government data sources and data provided by various regulators could also be examples of third party data. Third party data is useful for macro level analysis. It can derive market insights on market trends and consumer behaviors. These might be difficult to get through either first or second party data alone, because first and second party data just may not have enough reach for us to draw valid conclusions about the entire audience profile. Audience segmentation is also something that's better done with large datasets that we might get from a third party compared to relatively small first or second party data. Finally, this kind of data is also great for benchmarking. We can benchmark our enterprise performance against industry standards or competitors. And in this way, we can help our organization assess where it stands relative to others in the marketplace. Next, let's talk about some key points to keep in mind while integrating data in the digital transformation journey of an enterprise. The first is data integration. This can be thought of as effectively preventing data from being siloed. It's very important for enterprises to effectively integrate and combine their first, second, and third party data and get a unified view of the customer as well as of their own operations. Otherwise, we are back to data silos and all of the associated problems that we've discussed. While doing so, data governance is extremely critical. Data governance can be thought of as the process of creating policies and standards to make sure that data is treated correctly at every step in its life cycle, right from when the data is gathered down to where it's disposed of. Along the way, data governance also imposes safeguards on who can access or use data, and this is also where we ensure that the data is used ethically and in a manner that conforms with regulatory standards and compliance requirements. Data governance effectively is a system of checks and balances on data integration and data usage. Once these two critical aspects have been taken care of, the organization can then apply advanced analytics utilizing ML and AI to derive actionable insights from their data. Of course, in doing all of this, the organization also needs advanced technical infrastructure. The data storage needs to be scalable, processing solutions need to be able to handle large volumes and varieties of data. And this indeed is where the cloud comes in. The cloud is a critical enabler of this transformation of an enterprise, and that's why Google believes that we are currently in the transformation era of the cloud. In this context, it's worth mentioning the Google Cloud Marketplace. This is an online store which offers a wide range of third party software solutions and services which integrate seamlessly with the Google Cloud infrastructure. On the marketplace, you can find both open source and commercial offerings and datasets which cover domains such as demographics, market research, and consumer behavior. The Google Cloud Marketplace is a centralized platform where your enterprise can discover, purchase, and integrate external datasets directly into your Google Cloud environment. Next, let's run through some quick examples of how organizations can leverage first, second, and third party data in their digital transformation. Let's start with Netflix. Netflix leverages first party data very heavily to personalize its content recommendations for its subscribers. Again, personalization is a classic use case of first party data. Starbucks has another approach to leveraging first party data. It collects such first party data through its mobile app and loyalty program and uses it to drive personalized marketing campaigns. It tracks purchase history, location, and customer preferences, and in this way is able to increase customer loyalty as well as to boost sales. That's another example of personalization using first party data. In addition, Starbucks also uses such data to drive operational efficiencies. For instance, it optimizes inventory management and looks to streamline its supply chain operations and reduce waste. John Deere has transformed its business by integrating sensor data using the Internet of Things into its agricultural machinery. It relies heavily on second party data from sensors on equipment. With this, it monitors performance, predicts maintenance needs, and optimizes operations. This is known as its farm side strategy. Finally, let's see how third party data can be leveraged effectively. Procter & Gamble, the CPG giant, uses third party data to enhance its marketing strategies and in product development. It analyzes demographic and purchasing behavior data from various sources, uses this information to get insights into customer trends and preferences, and then to tailor its ad campaigns as well as to develop products that better meet consumer needs. As we can see from these four examples, first, second, and third party data can all be leveraged extremely effectively. First party data, especially for personalization, second party data to expand your customer reach, and third party data to understand customer preferences and macro level behaviors. Data is a resource, a very valuable resource, and like any resource, every enterprise should look to be extracting value from it. Let's now talk about the data value chain. This refers to a series of processes that are involved in generating value from the data. The value chain starts from the collection of the data and ends with its ultimate use in decision making and insight creation. The data value chain can be thought of as consisting of 6 steps. The first is data genesis. This is where the original data source actually emits the data. This is where the data is born, as it were. Then follow data collection, data processing, data storage, data analysis, and finally data activation. That last step is where the data is actually used for decision making and where the value from the data is unlocked. Let's talk about each of these steps in turn, starting with data genesis. We can decompose data genesis itself into 3 constituent steps. Source identification. This is where we identify the original source of the data. This might be a sensor, it might be a social media feed, or it might be a transactional system such as a point of sale device. Once the source has been identified, we then can capture the raw data from that source for further processing. Data creation or data capture can be thought of as the point where the data is initially created or captured. For instance, maybe an IoT device generates sensor data, or a user inputs information into a system. Accurate data creation and capture is critical because this is the source of truth for every subsequent step in the data value chain. That's why it's so important to have some initial validation very close to the point of data capture. The initial validation might only have extremely basic checks, but even these are very important because they minimize errors that otherwise might propagate through the entire value chain. These initial validation checks could be quick checks on the data's accuracy as well as its completeness. Next in the data value chain comes data collection, often also referred to as data ingestion. This is where the data actually enters systems that are maintained and run by our enterprise. These systems need to be able to handle large volumes of data, and in this process, the cloud, with its focus on distributed systems and cloud storage solutions, is very important. It's also important to manage the velocity of the data. High-speed data, such as real-time streaming data, needs to be effectively captured using technologies such as Apache Kafka or Amazon Kinesis or Google PubSub. You might recall that data warehouses are not great for ingesting data at high velocity, and that's why you would not choose to ingest data directly into a data warehouse. A third aspect to consider here is the variety of the sources, and you can see how we've got to deal with each of the 3 V's of big data: velocity, variety, and volume. Data lakes are a great way to deal with a variety of data sources which might have structured, unstructured, or semi-structured data, and also do keep in mind that this needs to be able to deal with unstructured data in the form of images, audio, video, sensor data, and so on. Next in the data value chain comes data processing. This is where we make changes to the data by effectively transforming it into a form which can be used for extracting insights. Steps in data pre-processing, such as data cleaning, are also a part of this process. Here, we remove inaccuracies, inconsistencies, and duplicates from the data. There are plenty of data cleaning tools and algorithms available on the cloud to support this. Next comes data transformation, which might make use of mathematical or statistical processes such as normalization, standardization, aggregation, and enrichment. These all make the data more easily usable. It's also worth keeping in mind the role of ETL pipelines. ETL is an acronym for extract, transform, and load. ETL processes are essential for moving the data from various sources into a centralized repository, such as a data warehouse or a data lake. ETL processes ensure that the data is correctly extracted, transformed, and loaded into the storage system. The next step in the data value chain is data storage, and this is a step that we've spent quite a bit of time discussing. It's at this point in the data value chain that we've got to make choices about the type of technology. We've discussed databases, data warehouses, and data lakes in a great level of detail. We've seen, for instance, that SQL databases for structured data and NoSQL databases for semi-structured data are excellent choices. Structured data for analytical use cases can be placed in data warehouses. These include solutions like Google BigQuery or Amazon Redshift. And of course, data lakes are great for storing large volumes of raw data in native format and across a diverse set of data types. Once the data is available in a data warehouse or a similar convenient to use repository, we can perform data analysis. Now, there are different types of analytics: descriptive analytics, which summarize historical data and place current data in context. Tools like dashboards and reporting systems can provide insights through visualizations and text summaries. There are also predictive analytics. These employ statistical models and machine learning algorithms to forecast future behavior based on current and historical data. Predictive analytics actively help with making informed decisions because they predict outcomes. Finally, there are also prescriptive analytics. These recommend actions based on the data analysis. Prescriptive analytics use optimization and simulation techniques to suggest a best possible course of action. The final step of the value capture in the data value chain is data activation. The word activation here refers to an action that is taken on the basis of some data. Data activation involves translating the data into actionable insights, which are then used for informed business decisions. It's very important that the data be fully integrated with the business processes of the enterprise. This could mean, for instance, automating decisions in supply chain management or personalizing marketing strategies on the basis of those actionable insights. It's also important for there to be a feedback loop, in fact, a continuous feedback loop. The activated data is going to be used to take decisions. Those decisions will lead to outcomes. Those outcomes need to be measured and fed back into the data collection and analysis process to ensure that the data insights were actually correct. Over time, this will improve the quality of the entire data value chain and lead to better data driven decision making. Next, it's time for us to talk about the importance of data governance. Data governance is a framework of policies, procedures, and standards to ensure the effective, efficient, and ethical management of data assets within an organization. Data governance encompasses data quality, data management, data policies, business process management, and risk management around the handling of data. The primary goal of data governance is to ensure that the data is accurate, consistent, secure, and used responsibly to support the organizational decision making. It's also got to ensure that the data usage is in line with compliance requirements. Good data governance requires clear ownership, accountability, and procedures for data related activities. There are many dimensions to data governance. Let's examine these one by one. One important aspect of data governance is setting appropriate internal standards for data. Here, the organization needs to create and enforce policies to dictate how data is collected, stored, processed, and shared within the organization. By setting these internal standards, the enterprise ensures that data is managed consistently across all departments. This also enhances accuracy and reliability. The standards also help in maintaining data integrity, reducing errors, and ensuring that all stakeholders have access to high quality data. Also, having well defined data standards facilitates better communication and understanding between teams and systems within the organization. Another critical aspect here is granting appropriate access permissions. Data governance frameworks must define clear protocols for granting access to data and ensure that only authorized individuals can view or modify sensitive information. This process involves setting up roles and permissions based on job functions and the level of data sensitivity. By controlling access to data, organizations can protect against unauthorized access, data breaches, and potential misuse of information. Effective access management also ensures that employees have the right data at the right time, and this improves efficiency and decision making processes. It's also worth remembering the consequences of taking this particular step lightly. This could open up an organization to targeted ransomware attacks and even legal liability. Regulatory compliance is a critical aspect of data governance. Enterprises must adhere to laws and regulations such as GDPR, HIPAA, and CCPA. Data governance will ensure that data handling practices meet these standards and help organizations avoid legal penalties and fines. Compliance with external standards also helps to build trust with customers and partners, because it demonstrates a commitment to protecting personal and sensitive information. Regular audits and assessments are a part of the governance process to ensure ongoing compliance and to address any gaps or shortcomings promptly. Data governance also plays a key role in improving data quality because it will include mechanisms for monitoring, cleaning, and maintaining data quality. This could include implementing procedures for data validation, correction, and standardization to ensure that data used in analysis and decision making is accurate and reliable. High quality data reduces the risk of errors and ill informed decisions and will eventually, in the long run, lead to better business outcomes. Continuous improvement processes within data governance frameworks help to identify and rectify data quality issues proactively, and this enhances overall trust in the organization's data assets. It is important for enterprises to not treat data governance as an onerous burden, because done right, data governance will also improve operational efficiency. Good governance will streamline data management processes, cut redundancies and inefficiencies. By defining data management practices and responsibilities, organizations can optimize the data workflow and ensure that data is readily available and that the data value chain is fully exploited. This will lead to cost savings as fewer resources are wasted on correcting errors or dealing with the fallout from bad decisions driven by bad data. Improved operational efficiency will also mean that employees can focus on more strategic tasks, driving innovation and growth within the organization. Everyone involved with data governance should be careful to realize the upsides from good data governance. Good governance makes data more valuable because it's data that is accurate, consistent, and reliable that can actually be leveraged for decision making. More insights and more important decisions can be taken on the basis of reliable, high quality data. When organizational users can trust the data that they are working with and make decisions confidently, the enterprise as a whole will be able to respond quickly and decisively to market changes and to seize opportunities. This agility and decisiveness is extremely important in today's fast paced business environment where data driven decisions can provide a crucial competitive advantage. Data governance can also play a key role in cost control. Accuracy and consistency of the data implies that businesses can avoid costs associated with data errors and inefficiencies. Improved data quality also means fewer resources need to be spent on correcting mistakes or reconciling discrepancies. Efficient data governance will also reduce storage costs by eliminating duplicate data and optimizing data usage. Data governance, of course, plays an important role in ensuring regulatory compliance with requirements such as GDPR, HIPAA, and CCPA. By implementing robust data governance frameworks, organizations can ensure that their data handling practices meet legal and regulatory standards and even scrutiny in case something actually goes wrong despite the best efforts of the governance team. This can help to avoid hefty fines and legal repercussions associated with non-compliance. Over time, partners of an enterprise, including customers and suppliers, will be able to discern whether the data governance policies of an enterprise are effective or not. Effective data governance will win the trust of customers and suppliers. They can rely on organizations to demonstrate a commitment to data quality, privacy, and security. Data governance is also an extremely important part of enterprise risk management. During this process of defining all of the data governance policies, the enterprise will identify, assess, and mitigate risks associated with data management. By implementing comprehensive data policies and controls, the organization can protect against negative or adverse incidents such as data breaches, loss, and misuse. Proactive risk management will also ensure that potential issues are addressed before they blow up into significant problems, reducing the likelihood of reputational damage and costly data related incidents. The flip side of each of these benefits is a significant adverse impact arising from data governance failures. To begin with, of course, there is the regulatory stick. Fines and other legal penalties can result if an organization is not compliant with data protection regulations such as GDPR, HIPAA, or CCPA. Non-compliance can result in substantial fines and legal penalties, potentially in the millions of dollars. In addition to the financial hit, There is also the reputational damage sustained by an enterprise. Companies that take data governance lightly also end up with poor data quality. This then leads to inconsistent, inaccurate, and incomplete data being fed into decision making processes, and the result in turn is misguided business decisions, operational inefficiencies, and a loss of trust among stakeholders. Inaccurate data can undermine even the most sophisticated analytical efforts and lead to wrong insights, which in turn will lead to wrong decisions. If data governance policies are not well thought through, it's also extremely likely that data finds itself locked up in silos. And then the folks who need data in order to make decisions have a challenge on their hands in even finding that data. So, poor data governance leads to data becoming siloed, disorganized, and difficult to locate. Poor data governance is also likely to leave enterprises ill equipped for the AI revolution that's sweeping industries. That's because firms with poor data governance are also going to end up with poor data for their AI models. And if a model is trained on bad data, well, the model is going to be pretty bad as well. There are also considerable security risks to organizations that take data governance lightly. Data breaches, unauthorized data access, and the leak of sensitive information to cyber threats and potential bad actors, these are all increased security risks that an organization could face. And finally, poor data governance negates the whole purpose of the data value chain. Remember that the data value chain ends with data activation, which is when an action is taken on the basis of data. So it's not a stretch to say that the entire data value chain, the entire process of deriving business value from data, is contingent on good data governance in an organization. We started this course off by addressing the historical challenges of working with data, which included difficulties in accessing, managing, and analyzing large volumes of diverse information. We examined the characteristics of structured data, which is highly organized and easily searchable, as well as semi structured data, which lacks a fixed schema but includes tags or markers to separate data elements. We also discussed unstructured data, which has no predefined format and might include audio, images, video, and free text. Additionally, we discussed the problem of data silos where information is isolated within different departments or systems, hindering comprehensive analysis and decision making. Next, we learned about the characteristics of various data storage systems. We explored relational databases which use SQL, that is the structured query language, and are ideal for structured data with complex relationships. Document databases were covered next, emphasizing their flexibility in storing semi structured data as JSON like documents. We also discussed data warehouses designed for analytical querying and reporting, and data lakes, which store vast amounts of raw data in its native format. We highlighted the use cases of data lakes, such as their ability to accommodate diverse data types and support advanced analytics and machine learning. Finally, we explored how to choose the right storage paradigm based on specific use cases and data requirements. We examine the distinctions between first, second, and third party data, emphasizing their respective sources and reliability. We analyze the data value chain, illustrating the process of collecting, processing, analyzing, and utilizing data to generate value. Additionally, we stress the importance of data governance, which involves setting policies and procedures to ensure data quality, privacy, and security. In conclusion, we addressed historical data challenges, explored different database characteristics, and emphasized the importance of choosing the right storage paradigm and implementing robust data governance. We are ready now to move on to the next course in this journey: storage options for unstructured data on Google Cloud. Effectively managing unstructured data is essential for organizations to optimize their storage solutions and ensure data accessibility and protection. Leveraging Google Cloud Storage allows businesses to utilize scalable, cost effective storage options while implementing robust data management practices and using advanced features like lifecycle rules and versioning. In this course, you will learn about the various storage options for unstructured data with a focus on Google Cloud Storage. You will navigate through the Google Cloud Console, familiarize yourself with its interface and capabilities, and explore the properties of buckets. You will also learn about different storage classes such as standard, nearline, coldline, and archive, and understand the trade offs between storage and access costs. Next, you will learn how to view objects and their metadata within GCS, gaining insights into the stored data's attributes and structure. You will practice working with objects using the GSUtil command line tool, gaining hands on experience with essential data management tasks. Additionally, you will explore bucket level retention policies to ensure that data is retained for a specified period and understand the importance of placing holds on objects to prevent accidental deletion or modification. Finally, you will explore the concepts of generation and meta-generation attributes to track the versions and changes in metadata of objects on GCS. You will study object lifecycle rules to automate data management, defining actions such as transitioning storage classes or deleting objects after a certain period of time. Additionally, you will cover object versioning and the soft delete feature, enabling the recovery of previous versions of objects and providing an added layer of data protection. It's time for us to move on from the big picture to some specifics. Let's start talking about storage options for unstructured data on the Google Cloud Platform. On the Google Cloud Platform, we can broadly think about storage options for structured and unstructured data. Semi structured data, such as JSON or XML, is usually stored in a document database. The document database offering on the Google Cloud Platform, which is Firestore, also has transaction support, and so in many ways can be thought of as a part of the structured data offerings. For now, our emphasis is on unstructured data, and at a high level, there are three options available. These are block storage, file storage, and object storage. Let's talk about each of these in turn, starting with block storage. Block storage refers to physically addressable storage that is accessed from compute, that is, persistent disks. The compute offering on the Google Cloud Platform, of course, is Google Compute Engine, and you can access block storage, that is, persistent disks, via GCE VM instances. Persistent disks are durable and high performance block storage. These can be attached to VM instances and provide persistent storage, which means that the data remains even after the instance is stopped or has been deleted. Data is split into fixed size blocks and laid out in memory. This data is directly accessed via the operating system of the virtual machine. Persistent disks have only limited support for multiple writers to disk. In other words, these are meant for single user writes. There are two types of persistent disks: standard persistent disks, which are cost effective and good for sequential read writes, and solid state persistent disks, or SSDs, which give higher performance and are suitable for random access workloads. Features of block storage include resizing, so you can increase the size of your disks without downtime, snapshots, including incremental snapshots of disk backups, encryption, because data is encrypted at rest and in transit, and automatic replication. Use cases for persistent disks include boot disks for virtual machine instances and applications that require constant IOPS. Next, let's talk about object storage. This is represented by Google Cloud Storage, which is a scalable object storage service for unstructured data. You can also think of this as the data lake offering on the GCP. Cloud storage allows you to store and access any amount of data at any time. The term object storage comes from the fact that data is stored along with associated metadata and a unique identifier. That unique identifier happens to be a URL, which also makes it easy to access data in GCS. Google Cloud Storage supports unlimited scaling. There's no file limit or storage limit. It also supports multiple reads and writes. There are no locks on files. Some of the features of GCS include durability and availability, global accessibility because the data can be accessed from anywhere with that high availability, seamless integration with other GCP services like BigQuery, Dataflow, and so on, security, including encryption and identity and access management policies, and versioning and lifecycle management. Use cases for Google Cloud Storage include data backups and archives, content delivery, and as a data lake, that is, as a source of unstructured data for big data analytics and AI ML modeling. Google Cloud Storage is ideal for storing media files such as images, video, and audio. A third storage option for unstructured data is file storage. This is represented by FileStore, which is a managed file storage service for applications that need a file system interface and a shared file system. This is a fully managed network attached storage or NAS system. Files are stored with data and metadata, and file store is a form of persistent file storage, which means that multiple concurrent application instances can access the same file system simultaneously. File store does support write locks on files. Like block storage, file storage is also accessible via compute. There are types of file storage. These include the basic tier and a high scale tier. The high scale tier has high performance and is suitable for applications that need low latency and high throughput. Features of file storage include its fully managed nature. The GCP manages the infrastructure, so you don't have to worry about hardware maintenance. File store is scalable, infinitely scalable in fact, and it easily integrates with GCP services such as Compute Engine and Kubernetes Engine. FileStore also has NFS version 3 support. Use cases for FileStore include content management systems, shared file storage for applications, and media processing workflows. Zooming out, you can see that we are still talking about different options for storing unstructured data. We discussed persistent disks, cloud file store, and cloud storage buckets. Choosing between these three options is actually relatively straightforward. If what you need is a virtual hard drive for your VM instance, then block storage is the way to go. If you need file sharing for multiple users or virtual machines, then file storage is the way to go. And if neither of these specific use cases applies, then you should go with object storage. That way, you can store an infinite quantity of data without worrying about the infrastructure. This is a good place for us to study some of the key differences between persistent disks and buckets. To begin with, persistent disks are physically addressable block storage, while buckets are object storage in which the data is stored along with metadata and a unique identifier. In terms of capacity, persistent disks go up to 64 terabytes in size. Buckets, on the other hand, are infinitely scalable. A very important difference is that with persistent disks, you pay for what you allocate. With cloud storage buckets, you pay for what you actually use. Persistent disk access is tied to Google Compute Engine VM instances, while buckets can be accessed with a URL and are entirely independent of any infrastructure, including virtual machine instances. Persistent disks have zonal or regional access only, while buckets can be accessed globally. Another way of understanding these alternatives is by comparing them along different dimensions. In terms of type of storage, persistent disks are block storage that's physically addressable. File store is file storage that's network attached storage, while GCS buckets are object storage. Typical use cases for persistent disks include VM boot disks and databases. File store is perfect for shared file storage, while object storage is a data lake solution for unstructured data. In terms of access protocol, persistent disks are block level access. File store can be accessed using NFS, while object storage is accessed using HTTP or HTTPS. All of these have high levels of durability. In the case of persistent disks, this is because of automatic replication. However, object storage has the highest level of durability of all. In terms of scalability, object storage is the winner hands down. It's virtually unlimited in terms of its scalability. File store will scale up to petabytes, while persistent disk storage will only scale up to the instance requirements. In terms of common use cases, persistent disks are great for databases and application storage. File store is great for content management services and shared directories, which are going to be accessed by multiple VMs. And object storage is suitable for backup storage as well as a data lake solution for unstructured data. That would include media files such as images, audio, and video. It's now time for us to understand the Google Cloud Storage Service in great detail. GCS is a scalable, fully managed, and highly durable object storage service, and is designed for working with unstructured data at any scale. GCS supports a variety of storage classes tailored to different access needs. Google Cloud Storage is a form of data storage architecture that is known as object storage because the data is accessed as objects with associated metadata in addition to the underlying data itself. This makes object storage different from other types of storage such as file storage or block storage. Every object includes not only the data and its metadata, but also a unique identifier. Every object can be accessed via HTTP APIs, and these objects are stored in units known as buckets. Buckets offer advantages in durability, availability, and cost efficiency with different options based on how often the data item is accessed. We've referred to the metadata attributes that are maintained for every data item. One of the most important of these metadata attributes is the storage class. Remember that objects are stored in buckets, and when we create a bucket, we specify a default storage class for that bucket. Then, when we add objects to the bucket, they inherit this storage class by default unless it is explicitly set otherwise. The appropriate choice of storage class depends on how often the data item is accessed. Data, colloquially referred to as hot data, is accessed many times a month. Cool data is accessed about once every 30 days. Cold data is accessed about once every 90 days, while archive data is accessed on average about once a year. The storage classes appropriate for these are standard storage for data accessed many times a month, nearline storage for data that's accessed about once every 30 days, cold line storage for data accessed about once a quarter, and archive storage for data that's accessed about once a year. It's important for you to understand each of these storage classes and also their pricing and billing characteristics. For instance, the cost of storing data is lowest for archive data and highest for standard storage data. This intuitively makes sense because if data is going to be accessed very infrequently, it can be placed on relatively inexpensive storage devices. However, the opposite is true when it comes to the cost of accessing data. Data in standard storage that is going to be accessed multiple times a month will have the lowest cost to access. On the other hand, data in archive storage will have the highest cost to access. Now, another independent attribute of a bucket is where it is accessible from. Based on where the data is going to be accessed from, there are different types of buckets. If the data is going to be accessed only from a specific region, a regional bucket will suffice. If it's going to be accessed from geographically separate locations, but where those locations are known in advance, then a dual regional bucket is good enough. On the other hand, if the data is going to be accessed globally, that is from anywhere in the world, then you've got to go with a multi-regional bucket. Regardless of the storage class, all cloud storage has some common features. First, it's unlimited storage with unlimited access. Second, there's no minimum object size. Third, GCS buckets feature worldwide accessibility for storage locations. Fourth, latency time is low. Time to the first byte is typically on the order of tens of milliseconds. Buckets are redundant across regions if the bucket is multi-region or dual regional. Finally, cloud storage has extremely high durability. It can be tricky to settle on the correct storage class for your use case because there are trade offs along many different dimensions from availability down to access frequency and the use cases. Let's cycle through each of these one by one. In terms of the availability SLA, for instance, nearline and cold line regional buckets support 99% availability. Regional standard storage buckets have 99.9%, and that goes up to 99.95 for dual and multi-region standard storage. It's also worth keeping in mind that dual and multi-region buckets are tied to multi-regional locations, that's the US, the European Union, and Asia. This is done to make it easy for users to adhere to data storage regulations in the US or European Union. Let's get a quick sense of storage costs. As previously discussed, these are lowest for archive storage and highest for standard storage. There is a full order of magnitude of difference between the storage cost in cents per gigabyte per month between archive and standard. The picture changes when we turn to retrieval costs. These are zero for standard storage, but the highest for archive storage. It's also worth noting that there are minimum commitments in terms of how long data has to be stored in a bucket for the storage classes other than standard. Early deletion will incur charges, and these minimum commitments are in line with the frequency of storage. In terms of durability, 11 nines is the level of durability for all of these buckets. Once again, it's worth reiterating that access frequency is a primary dimension while choosing storage class. If you're going to access your data many times a month, you should go with standard storage. If it's approximately once a month, then nearline storage is fine. If it's every few months or about once a quarter, then cold line storage is probably best for you. And if it's going to be very infrequent, on the order of once a year or even less, then archive storage is the best. Here are some common use cases for the different storage classes. Standard storage works well for serving websites, interactive workloads, and mobile and gaming applications. These use cases also require global access, and that's why it makes sense for the bucket to be dual or multi-regional. Let's say you're accessing your cloud storage bucket from a Compute Engine VM instance or a Dataproc cluster, then regional standard storage is probably sufficient. For use cases related to data backups, disaster recovery, and archival storage, nearline buckets are considered best suited. While for legal and regulatory requirements, such as where an enterprise has to preserve all of its data for a certain number of years, cold line or archive are probably sufficient. A final use case for cold line and archive buckets is for disaster recovery scenarios where recovery time is not important. Let's now discuss some other features available in Google Cloud Storage. Object versioning is one such. This is a feature that needs to be enabled for a bucket before it kicks in, and once you enable it, the bucket is going to create archived versions of each object. Then, whenever a live object is overwritten or deleted, a new version with a unique generation number is going to be created in its stead. Each copy, that is, each version, is going to be charged separately. It's important to note that object versioning will not provide protection against bucket deletions, it will only help with object deletions or overwrites. Another powerful feature of GCS buckets is object lifecycle management. This can be used for use cases where you'd like to set a time to live or a TTL for objects, or if you'd like to retain non-current versions of objects, and also to downgrade or change storage classes of objects for management of costs. Using object lifecycle management, you can specify a set of rules. Each rule will contain an action and one or more conditions. By appropriately choosing the action and the conditions, we can perform all of the operations that you see on screen now. For instance, let's say we'd like to change the storage class from standard storage to nearline after 60 days. Or let's say that we'd like to delete all data created before a specific date, or even delete all but the three most recent versions of a particular object. All of these are possible with object lifecycle management. Let's very quickly talk about encryption. Google Cloud Storage will encrypt data on the server side even before it's written to disk. So data is going to be encrypted at rest and also in transit. By default, this encryption is going to be performed with keys generated by Google, but there are additional options for both server-side and client-side encryption. Server-side encryption can further be classified into customer-managed encryption keys and customer-supplied encryption keys. This is a complex topic, so we won't have a lot more to say on this. Another important and powerful feature is AutoClass. This is a feature in which objects are automatically transitioned between storage classes based on the access pattern. AutoClass is one step beyond predefined lifecycle management rules. No manual intervention is required at all. AutoClass will monitor how frequently an object is accessed, and it will move that object to the most cost-effective storage class based on usage. In this way, data will always be stored in the appropriate class for its access pattern. For instance, data that is not accessed often will be moved to colder storage classes to reduce storage costs. Data that is accessed more often but is in a colder storage class will move in the reverse direction towards standard storage. In both cases, AutoClass will serve to optimize and reduce the costs of cloud storage. It will try and seek the right trade-off between storage costs and access costs. In order to solidify our understanding of the theoretical concepts that we've been discussing, let's get our hands dirty. We'll be going through some simple demos on the Google Cloud. Now, it's not strictly required that you actually carry out all of these demos on your own, but it will definitely help if you do. At the very least, it makes sense for you to follow along with these videos and see what it's like to actually work on the cloud. Let's start by exploring the Google Cloud Storage service and see how we can create buckets using the user interface. We begin by navigating to a URL, and that is cloud.google.com. That takes us to the landing page for the Google Cloud, and over on the top right, we see a little link button, Console. We click on that, and this is the URL that we will be using a lot, console.cloud.google.com. At the center of the screen, we see the organization name, that's lunicorn.com, as well as the project, that is Luni GCP CDL. There's also a project number and a project ID. Remember that a project is effectively a container for all billable GCP resources that we provision. What if we'd like to work in a different project? Well, we can change that from the menu over on top. There's a drop down, and when we click on it, we see all of the available projects. Let's stick with our current choice of Luni GCP CDL. Now you can see that there are little buttons here which allow us to perform some quick operations. One of those is to create a storage bucket. This is one way of doing it. However, we will go with a more roundabout method so that we can explore more of the Google Cloud. Over on the top left, we see three horizontal lines. There's a tooltip there telling us that this is the navigation menu. Now, these three horizontal lines are often referred to as the hamburger. When we click on that, we see there's a section called Pinned Products. Right now, no products have been pinned, and it just says pin your top products here. This is to make it easy to access the services and products on the Google Cloud that we use most often. Let's get a list of all products by clicking on that View All Products button. Here are different sections, all the management products such as APIs and services and billing. Down below are the compute products, including Compute Engine and Kubernetes Engine. And then scrolling down, we have storage, analytics, networking, distributed cloud, serverless, databases, and a whole lot more. Let's scroll back up towards the top, and in the storage section, let's choose cloud storage. We are going to pin cloud storage, and we do that by clicking on the little pin icon just next to the name of the service. You see the tooltip there, pin to your menu. Now, if we click on the hamburger that's over on the top left, we now see that in the navigation menu, cloud storage appears right up top. We can also see that the pin icon is now filled, which means that we have pinned it. There's a sub-menu and there are sections there for buckets, monitoring, and storage. Let's click on buckets. That takes us into a view where we can see all buckets in this project. Right now, there are no rows to display. Towards the bottom, you can see there's a blue button to create bucket, or alternatively, we can scroll back up top. Let's quickly get rid of some of these announcements regarding soft delete and security recommendations. And then let's click on the plus icon and the create word over towards the top of the screen. Right at the start, we are asked to name our bucket. We are also told to pick a globally unique and permanent name. Let's go with the name Luni Cloud Leader Bucket. This name is available, there's no error. How do we know? Well, because if we try some other name like My First Bucket, we get a message telling us that that bucket name is taken. Remember that bucket names need to be globally unique, and so it's common practice to add an organization specific suffix. In any case, let's go with Luni Cloud Leader Bucket. We hit continue, and we are then prompted for the location type. There are three options: multi-region, dual region, and region. As we can see, multi-region has the highest availability, dual region has high availability and low latency across two regions, and region has the lowest latency within a single region. We can explore the options in multi-region. These include US, Asia, and EU. Next, let's click on dual region, and when we do so, we are prompted for the two regions where we'd like our bucket to exist. There's also an option for turbo replication, which is a more advanced feature. So here we have the location, which is Americas, Asia Pacific, or Europe. And then down below, we are prompted for the regions. There are checkboxes here, but the way the menu works, we can only select two regions, After that, all other options are grayed out. Finally, let's explore the region bucket. That's the simplest. And when we click on that, we are just prompted for the one region where we would like our bucket to exist. Let's scroll through really quickly and orient ourselves with all of the different regions. You can see that some of those are marked as having low CO2 emissions. In any case, let's click out of this menu and change the location type back to multi-region. Let's pick US and then move on to the next section of the inputs by clicking continue. At this point, we are going to be prompted for the storage class for our data. We see that there are a couple of options. We can either go with auto class or set a default class. Auto class is going to automatically transition each object to standard or nearline based on the object level activity. This is a relatively new feature. The older and more common approach is to set a default storage class. We see the four storage class names that we've already discussed: standard, nearline, cold line, and archive. The descriptions confirm what we already know. Standard is best for short-term storage and frequently accessed data. Nearline is great for data accessed less than once a month. Cold line for data accessed less than once a quarter. And archive for data accessed less than once a year. AutoClass will rotate our data item across these different storage classes. To learn more, let's click on that tooltip. As we can see here, all data will be in the standard class for the first 30 days. If the data is not accessed within the first 30 days, then it will transition to other colder storage classes. And colder data that does get accessed will be promoted and transitioned back to standard. We can also explore any of the other tooltips if we'd like to learn more. Let's hit continue, and we are then taken to a section on controlling access to objects. The first order of business is to uncheck that dialog which says enforce public access prevention on this bucket. We are doing this because we would like our bucket to be available for access via the internet. There are various other options here that we could explore, but let's leave those to their default settings and click on continue. We also see a checkbox there for soft delete policy that's checked by default. There's an object retention period. Further down, there's a data encryption section. Let's go with the defaults on all of these settings and instead scroll back up to the top and click on that little button which says estimate your monthly cost. We are still in the process of creating our first bucket, and we are now going to explore and estimate our monthly cost. You can see right now over on the top right, it shows that the current configuration is multi-region and the storage class is standard. Let's click on that estimate your monthly cost, and that then allows us to enter details of how we think we will be working with this bucket: storage and retrieval, object versioning, the number of Class A and Class B operations, and so on. Now, this is a very handy calculator, except that as of when this video is currently being recorded, it has a bug. Currently, our storage class is set to standard, and for standard, the retrieval cost is indeed 0. As we shall see in just a moment, however, even if we change this storage class from standard to nearline or cold line, the retrieval cost will still show as 0, and that's the bug. Right now, the bug does not manifest. You can see that the default class is currently standard, and over on the right, data retrieval shows as free. Let's change those estimates so that storage size is set to 100 and retrieval size is set to 1000. Both of these numbers are in gigabytes, and even at this point, we can see that data retrieval shows as free. This so far is correct because our default class is standard. However, now let's change the storage class from standard to nearline, and even now, despite having changed to nearline, the data retrieval cost still shows as free. We see that over on the top right, and that's the bug in this estimation. With this current bug, we see that the monthly estimated cost is $1.50. That's visible down below. That's for a nearline bucket where we've estimated our storage as 100 gigabyte and retrieval at 1000 gigabytes. We can experiment with the other storage classes as well. For instance, if we change to cold line, you can see that the monthly cost estimated here drops to just 70 cents a month. Once again, this still shows the data retrieval cost as free for data retrieval size of 1000 gigabytes. And we observe something similar if we switch to archive. Once again, we've got data retrieval size at 1000 gigabytes. Once again, it's still free, and now the monthly cost has dropped even further to just 24 cents a month. This calculator also allows us to click through into the actual pricing details page. So let's scroll back towards the top and click on pricing details. This opens in a new tab. This cloud storage pricing page is actually worth going through in some detail. You can see it explains the components of cloud storage pricing, which include data storage, data processing, and network usage. There are also pricing tables which give us very granular information by region. Let's scroll down to the very bottom, and there we can confirm that there was indeed a bug in the calculator we just viewed. This is the section about retrieval fees. These apply when we read, copy, move, or rewrite object data or metadata. Note that this is 0 per gigabyte for standard, but it's not 0 for the other storage classes. It's 1 cent per GB for nearline, 2 cents per GB for cold line, and 5 cents per GB for archive. This makes sense, of course, because the whole point of the trade off across these storage classes is that there is a trade off or an inverse relationship between storage costs and retrieval costs. In any case, having satisfied ourselves that that monthly cost estimator was wrong, we close this tab and return to the Cloud Console. There, let's set the default class back to standard and scroll down and click on the Create button. We get a message telling us that our bucket has been created, and a moment later we can see the bucket details. We'll actually start working with this bucket in the demo coming up next. We ended the previous demo by creating our first bucket. We can now see that bucket appear in a list of all buckets in the project. Here it is, the Looney Cloud Leader bucket. Towards the center right of the screen, we can work with this bucket. We can upload files or a folder to the bucket. We can create a folder or transfer data into the bucket. Up top, we also have a ribbon with many different sections, such as objects, configuration, permissions, and so on. Let's click on configuration, and there we find information such as when the bucket was created, updated, the replication policy, the default storage class, note that that is standard, and then importantly, the Cloud Console URL and the gsutil URI. We'll see how each of these is used. First, also note that we can copy this very easily by clicking on that little copy icon to the right of the data item. We go ahead and click on the copy to clipboard icon for the Cloud Console URL and open up a new browser tab and paste in this URL. When we do this, we are directly taken back to the properties of this bucket. We are in the Objects tab, and if we scroll down, you can see that there is a button for Upload Files or Create a Transfer Job. We'll add some data to this bucket in a bit, but first let's scroll up and click on Permissions. Up top, we have sections for public access and access control. Scrolling down, we have permissions. These can be viewed either by principals or by roles. We can see here that the properties of each bucket can be set using role-based access control. Let's scroll back up to the top and now switch over from the Permissions tab into the Protection tab. The first section here has to do with the soft delete policy, that's for data recovery. That's currently enabled with a retention period of 7 days. Object versioning is currently turned off, and various other protection related properties are visible here as well. Once we're done, let's scroll back up to the top and click on Lifecycle. This is where we would configure the object lifecycle management rules. Statistics about errors, reads, writes, and other metrics are viewable from the Observability tab, which we can see over up top. By this point, we've gotten a fairly good sense of the different aspects of a bucket that we can explore using the console. It's time for us to switch over to Google Cloud Shell. We can do that by clicking on the little prompt icon over on the top right. You see the tooltip, it says Activate Cloud Shell. When we click on this, a command prompt opens up down below. Cloud Shell is a web-based, free and interactive shell environment. It has all of the Google APIs and SDKs available so that you don't have to go through the trouble of installing them locally. We can see that the prompt includes the project name, that's Looney GCP CDL. This is a pretty cramped shell, so let's click on that Open in New Window tab over on the center right. This opens up a new tab where we have a lot more screen real estate. Now, the prompt does not seem to include the project name, So let's just make sure that we've set the currently active project. We can do this by running the command gcloud config set project followed by that project name, which is Looney GCP CDL. This command requires our authorization, and so we are asked to confirm that we actually wish to do this. We click on authorize and the prompt changes. You see now that Looney GCP CDL appears as a part of the prompt. Now let's start using gsutil. gsutil is a command line utility that you can use in order to work with buckets. gsutil -- version confirms that we have version 5.27. You can also use gsutil -- help. This gives us a long list of commands that we can run. We scroll up and down and orient ourselves with the output, and we find that gsutil mb can be used in order to create buckets. Some other commonly used commands include ls, you can see that right above mb, to list providers, buckets, or objects. And then further up, we have cp, which can be used to copy files and objects. Let's try out some of these commands in action. To begin, we will try gsutil mb, and then we will intentionally give it the same name as the bucket we just created. gsutil mb followed by the bucket URI, and that has the format gs colon / and then the bucket name. Here, if we hit enter, we'll get an error because we already have a bucket called Looney Cloud Leader bucket. The error also makes it clear that bucket names must be globally unique across all Google Cloud projects, including those outside your organization. This is important to keep in mind. Not only do the bucket names need to be unique within your project or organization, they need to be globally unique. In any case, let's now go ahead and run another different command in order to create a bucket. This is gsutil mb and then the bucket name with the URI. This bucket name is Looney Cloud Leader Bucket Source. This command runs through successfully, and we can confirm that yet another bucket has been created in a couple of different ways. We could switch back to the Cloud Console, and there we would find two buckets instead of one in our project. But a simpler way right here is to run the command gsutil ls. This lists out all of the buckets in our Looney GCP CDL project, and there are two: Looney Cloud Leader bucket and Looney Cloud Leader bucket source. Next, let's run gsutil mb again, this time with some additional flags in order to create a regional bucket. So you see we have the -c followed by regional, that's for the storage class, and then we have the -l, which provides the region, and that's US Central 1. The last argument continues to be the gsutil URI, which is gs colon followed by the two forward slashes and then the name of the bucket that we'd like to create. Here, that's Looney Cloud Leader bucket followed by US Central 1. This command runs through successfully, and we can confirm that now we have three buckets in our project. We'll do that in just a moment. But first, let's run gsutil help mb. Here is the syntax visible up top. -c stands for the class, -l stands for the location. Also note how the very last argument is gs colon / and then the bucket name. gsutil is very powerful. It allows us to perform virtually every action that we might via the console. Let's now run gsutil ls-l. This is going to list out all of the buckets in our projects along with their details. This output really includes a lot of details, so we'll have to sift through it. Up top, you can see details for GS Looney Cloud Leader bucket. The storage class is standard, location type is multi-region. Let's scroll down a little further and look at the properties for the Looney Cloud Leader bucket source. This also has standard and multi-region, but things are a bit different if we scroll to the third bucket. Here we can see that the storage class is now regional and the location type is region. The location constraint contains the name of the region, which is US Central 1. In the case of the multi-regional buckets, the location constraint was just set to US. We are now done with our quick exploration of gsutil via Cloud Shell. In the next demo, we'll switch back to the console and actually add some content into our buckets. Here we are back in the Cloud Console. You can see that we are looking at the details of the bucket Looney Cloud Leader bucket. The first order of business is to add some content to this bucket. So we click on the Create Folder button pretty much at the center of the screen. We are prompted for the folder name. Let's call this Images. We hit create and we see the images folder displayed down below. Let's click through into this, and once we do that, we can now upload files into the folder. We click on the upload files button, we browse to a location on our local machine, and notice that we've selected two image files. We hit open and we now see that those files appear in our object browser, hamster.jpg and pug.jpg. We can click through, these are clickable links, and that takes us into the object details. This page makes it really clear why Google Cloud Storage is known as object storage rather than file storage. You can see that we have a lot of metadata attributes, and if we scroll down, we'll find the actual image itself. But that image, which is the raw data, is encapsulated in an object, and that object has all of the other attributes that are visible up top. The type, size, when it was created, but also importantly, the storage class, which is standard. That was inherited from the bucket within which this object resides. Then you can see that public URL is set to not applicable, and lower down in permissions, it says public access is not public. We'd eventually like this image to be available to all, i.e. we would like to make it public, but before we do that, there are a few hoops that we have to jump through. We also see the authenticated URL. Let's click on the copy icon and then paste that into a different browser tab. And in that tab, we now see the image alone. This is the image of the hamster without any of the additional metadata. Let's switch back to the Cloud Console and edit access on this object. Remember that public access is currently set to not public. We can see that at the center of the screen, and we'd like to try and change that by clicking on edit access. It turns out that we actually can't do this. The message that we see tells us that we cannot get legacy ACL, that's access control lists, for an object when uniform bucket level access is enabled. We won't discuss this in much detail. It has to do with using ACL, that is access control lists, as well as role-based authentication, which is now the preferred method. In any case, let's keep going. We can click through on the breadcrumbs over up top. We can see buckets and then the bucket name, Looney Cloud Reader bucket, the folder name images, and finally the object name that corresponds to hamster.jpg. We click on the name of the bucket and that takes us one level out. Now let's click on the permissions tab here. That takes us to a page where we have the access control settings towards the right. We have an option there to switch to fine grained. Let's go ahead and click on that switch to fine grained. A dialog opens up. It tells us that there are two ways to choose how to control object access in this bucket. The first is uniform, which is the current setting. Here, uniform access to all objects in the bucket will be based only on IAM, that is Identity and Access Management. So effectively, the first option ensures that access control happens via role-based access control. The second option, fine-grained, tells us that we can specify access to individual objects using object level permissions, that's ACLs, in addition to the bucket level permissions. We are also warned that fine-grained access control might grant wider object access than your bucket's IAM policy. We are fine with that for now, so we hit save, and this will now allow us to make our hamster image publicly accessible. We are in the permissions tab. Let's click on the objects tab over on the top left. There we have the folder images. We click through into images, and now we can open up the individual properties of the objects. Let's click on the three vertical dots over at the right on hamster.jpg. The tooltip tells us that this is called the object overflow menu. So let's open that object overflow menu. Here you can see that there are numerous options such as download, copy authenticated URL, copy gsutil URI, edit metadata, edit access, and then also copy, move, rename, and more. For now, it's the edit access that we are interested in. So we click on that menu item and we then click on the add entry button in the dialog that opens up. Here we can specify actions at the level of different users, and from the drop-down menu we go with the most accessible, which is public. So the entity 1 is set to public, then name 1 is set to all users. In this drop-down we could also choose all authenticated users, but we are fine for even non-authenticated users to access this image. And finally, in access 1 we go with reader. The other option there is owner. We hit save, and at this point This image of the hamster is going to be publicly accessible. To verify that, let's click through into hamster.jpg. We see the metadata attributes, and this time there is a public URL in there. Notice how the public URL is different in its structure from the authenticated URL. The public URL is storage.googleapis.com, while the authenticated URL is storage.cloud.google.com. And you can also see, scrolling a little further down, that in the permissions section, public access now shows public to the internet, and it's got a pretty prominent warning icon next to it. Down below, we have the actual image itself. Let's scroll back up and let's copy the public URL to the clipboard. So we click on copy to clipboard, open up a new browser tab and paste this in. And we now see that we can access the image. We've successfully opened up our image for public access. In the previous demo, we saw how we could add objects to a bucket using the console. We were also able to make one of those objects publicly accessible. In reality, a more common use case for working with cloud storage buckets is for bulk upload and modify operations. After all, cloud storage is the data lake offering on the Google Cloud. That's where you would tend to dump a lot of unstructured data, such as images. For such large-scale operations, using the command line in gsutil is probably more convenient. So let's switch back over. To begin with, we will copy the gsutil URI of our object. Notice again how the gsutil URI always starts with gs colon and then 2 forward slashes. Then comes the bucket name, Looney Cloud Leader Bucket, the folder path, here there's just one folder, images, and finally the object, which is hamster.jpg. Let's copy that URI, switch over to Cloud Shell, and here we introduce a utility called curl. Curl is a simple command line utility that you can use in order to hit a URL. In fact, curl is actually short for CURL, that is command line URL. Let's start with a quick version check, curl -- version. This tells us that we are using version 7.81.0. What we are now going to do is use curl in order to download some image files from the internet, and then we'll use gsutil in order to upload those files to one of our buckets. We will then use gsutil to also delete those files. Let's get started. We first run ls-l. This is going to show us the present contents of our Cloud Shell home directory. This just happens to be a grab bag of files that we've been working with recently. Next, let's use curl to actually download files from the internet. Here is the curl command that will do this. This is a rather complicated command. You need not worry too much about all of these switches. What this does is it hits two URLs on the public internet, both from the URL https://unsplash.com, and downloads photographs of an orange and a cherry. The -l flag is merely an instruction to curl to follow any HTTP redirects, and the -o flag tells curl where to save the content locally. The command runs through, it hits those two URLs and downloads the contents, and those contents are now available in the files orange and cherry.jpg. We can confirm this by running ls-l star.jpg, and we can see that in our Cloud Shell home directory, we now have these two files safe and sound. Now that the files are available on the Cloud Shell directory, we can use gsutil in order to copy them over into a bucket. The command that we run is gsutil-cp. Notice the similarity between gsutil commands and common Unix commands. We specify three input arguments to gsutil-cp. The first two are file names which point to orange.jpg and cherry.jpg. These are local files which exist in the home directory of our Cloud Shell. The last command line argument is the gsutil URI where we would like to place these images. You see here gs colon // followed by the bucket name Looney Cloud Leader Bucket and then the folder images. Also note the / at the end of that path. That indicates that images is a directory. We run the command through and we can see that two files have been copied over. We also see the content type is image/jpg and the total size was about 37 KB. Next, let's verify that these files have actually been copied over to our bucket. One way of doing this is from right here with gsutil ls. So we run gsutil ls followed by the same URI that we had specified a moment ago. This is the images folder on the Looney Cloud Leader bucket. This confirms that we now have 4 images in there, not 2. Before we uploaded the orange and the cherry.jpg, we only had the images of the hamster and the pug. Another way of confirming this is by switching back over to the console. We click on the breadcrumbs on top and navigate back out to the bucket, that's Looney Cloud Leader bucket. Towards the center of the screen, we have the images folder. Let's go ahead and click on that. This opens up the contents of the images folder. Initially, we are a little worried because we still see only 2 files here, hamster.jpg and pug.jpg. But then we notice a little flash message telling us that the information on this page is out of date and that we should refresh. We click on refresh and there we confirm that we do indeed now have cherry.jpg and orange.jpg appear as well. Next, let's see how we can delete one of these images using gsutil. Let's switch back over to Cloud Shell and we use gsutil with rm. Again, note the similarities to Unix shell commands. gsutil rm followed by the exact URI of the object that we wish to delete. The URI begins with gs // then the bucket name, Looney Cloud Leader bucket, the folder name, that's images, and finally the object name, that's cherry.jpg. The command runs through successfully. We are told that this object has been removed, and we can confirm this using either gsutil ls or by switching over to the Cloud Console. Let's do both. We first run gsutil ls once again with the images folder, and we can now confirm that we no longer have 4 files in there, we have only 3. The cherry.jpg file, which we just deleted using gsutil rm, no longer appears in this listing. Let's confirm that this is also reflected in the Cloud Console. We switch back over and hit refresh over on the top right. And when we do this, we see that cherry.jpg no longer appears here either. We've successfully uploaded and then deleted images using gsutil. In this demo, we are going to work with retention policies on Google Cloud Storage buckets. A retention policy will allow you to specify a period of time during which objects should not be deleted or modified. You can imagine that retention policies can become very important in the context of compliance or legal liability. Let's go ahead and see how we can work with retention policies and also how we can lock a retention policy. This is an irreversible operation. We pick up the action from our Looney Cloud Leader bucket and we click on the Protection tab towards the center of the screen. You can see right up top that the soft delete policy for data recovery is in effect. This means that deleted objects will be kept in a soft delete state and the retention period is currently set to 7 days. Let's scroll down and get to the retention section. As it tells us there, retention is primarily for compliance reasons and it prevents the deletion or modification of objects in the bucket for a specified period of time after they are uploaded. Then in the bucket retention policy section, we are also told that the optional step of setting retention mode to lock ensures that no one can remove or shorten the retention period. Right now, there's no retention policy. Let's change that. So we click on the set retention policy. A dialog opens up. We set the duration to be 500 seconds. We can also choose different time intervals such as days, months, or years. It's important to note that the retention policy will retroactively be applied to all objects in the bucket. Now you can see that the retention period shows as 500 seconds. We can edit, delete, or lock this retention policy. We will come back and try and lock this policy in a bit. But first, let's see what happens if we now try and delete one of the objects in our bucket. Before we navigate away though, notice that the effective date is June 6, 2024 and the time is 3:40 GMT plus 5. Let's navigate back out to the Objects tab by clicking on the top left, and there we can see that in our images folder we have the 3 files. Let's select any one of these files and we expect that this file should not be deleted. One very quick note, we can see that hamster.jpg was created at 3:31 p.m. on 6th June of 2024. That time will become important in a moment. So we select hamster.jpg and we click on delete over at the center of the screen. We are asked whether we would like to delete this one object and we are given some information about the soft delete. But you can see that in this confirmation dialog, it doesn't say anything about a retention policy being in effect. In any case, we hit delete and we fully expect the deletion to fail. But to our great surprise, the deletion has gone through successfully. Wait a minute, if the retention policy applies retrospectively to all objects in the bucket, then how come hamster.jpg was deleted? And the answer comes down to the length of the retention policy. Recall that hamster.jpg had been created at 3:31 p.m. and our retention policy was 500 seconds. That 500 seconds had already elapsed after the creation of that file, and that is why it was possible for us to delete hamster.jpg. This could end up being a big issue depending on the exact compliance scenario that you are faced with, so just be aware that to be on the safe side, it's better to create a bucket, set a retention policy, and then add content into it. In any case, let's now see what happens if we try and re-upload hamster.jpg and then perform the deletion. We click on the Upload Files button at the center of the screen. We choose hamster.jpg from our local machine and hit Open. This time, we are faced with another warning, and this one makes it very clear that we are uploading objects to a bucket with a retention policy. So, any user who is going to add objects to a bucket with such a policy needs to actually acknowledge that he or she is aware that they are doing so. We are told a retention policy protects objects in this bucket from being deleted or overwritten. Until the policy expires, you won't be able to upload any objects with the same name as an existing object. We can also see down below the length of the retention policy, which is 500 seconds, that's in bold. We click on confirm to proceed with the upload, and a moment later, hamster.jpg is successfully added as an object. Now for the big test. Let's select this hamster.jpg object, click on the delete button at the center of the screen, and try again deleting it. Once again, we get the confirmation message. Once again, it mentions the soft delete policy but says nothing about a retention. And this time, when we go ahead and hit delete, we see that the deletion has failed. Down below, we have a flash message telling us that this particular object, hamster.jpg, could not be deleted. And then at the top right, we have two notifications, and one of them is an error. We know that because it's now in that bright red. We click on that and we see the error. It signifies that the deletion of hamster.jpg failed, and this is because of the retention policy of 500 seconds. Let's now navigate back into the protection tab. So we click on protection towards the center of the screen, scroll back down into the retention section. Here you can see that we have three possible actions: edit, delete, and lock. Also notice that all three of these actions are currently enabled. We click on edit and we find that we are indeed successfully able to edit our retention policy. We change it from 500 seconds to 300 seconds. We then hit save. Everything seems to work fine, no issues at all. We still see all three of those options are available, so we again click on edit. We change this from 300 to 600 seconds. Once again, no problem at all, and we hit save for a second time. So far, what we've done convinces us that we can edit our retention policy. Now, at this point, you might start to think through all of the implications of this from a compliance perspective. What if a particular user decided to edit the retention policy, reduce the timeout, modify or tamper with the data, and then reset the retention policy to what it originally was? Of course, such actions might be detected by going through the logs, but even better, the Google Cloud Platform has come up with the lock option. You can see here down below that retention mode currently states unlocked. We can change that by clicking on the lock icon. Locking a retention policy is an irreversible action, and we are warned of this right up top where it states this action is permanent. You can also see that this action will prevent the destruction of any key management service key versions that were used to encrypt this object's buckets for the full retention period. It's also worth noting that once we lock the retention policy, we can neither reverse the lock nor decrease the retention policy. In order to confirm that we really wish to do this, we've got to type out the name of the bucket. We do so, then we click on lock policy, and that does it. This action is now irreversibly performed. Notice also how the UI changes. Where there were three options, now there are just two: edit and delete. The lock option has gone away, and the delete option is grayed out. Let's try and click on the edit and see whether that works. If we try and set a duration that is less than 600 seconds, we encounter the error: a locked retention policy can't be removed or reduced in duration. It is possible to increase the duration, however. So let's cancel out of this edit retention policy. There's very little that we can do here now that the retention policy has been locked. Let's now navigate back to the object view. So we scroll up and click on the Objects tab over on the left. This takes us back to the object browser. Let's select a couple of files, hamster.jpg and orange.jpg. We click on the delete button at the center of the screen, and we are asked to confirm that we wish to delete these despite the soft delete. We provide the confirmation. However, the deletion fails. We can see two objects could not be deleted, and once again we have the bright red circle over at the top right. That indicates that one error has occurred. This time let's click on View Details at the bottom center of the screen. This takes us into the deletion details. You can see that the status is failed on two individually selected objects. Let's expand that error, and we can see that this is because the retention policy was not met. And we can further expand this to confirm that the deletion of hamster.jpg and orange.jpg failed because they were subject to the bucket's retention policy. Here you can see for hamster.jpg, for instance, we are also given the precise time. Note the bit in the error message which reads cannot be deleted or overwritten until, and then there is a long timestamp string. One last loose end is to actually wait out that retention period and then try again. So here we are again after a coffee break. We've selected our Looney Cloud Leader bucket in the buckets view. Please note again that this is about 10 minutes after our last attempt. We navigate into the details, we click through into the images folder, and now because the retention policy period has expired, we are able to select and delete files. Let's select hamster.jpg and click on delete. After we confirm that we do wish to delete, we can see that the deletion goes through successfully. That's confirmed by the message at the very bottom of the screen, Looney Cloud Leader images hamster.jpg deleted, and we also no longer see hamster.jpg in the object view at the center of the screen. And that gets us to the end of our exploration of retention policies on buckets on the Google Cloud Storage. In this demo, we are going to work with holds. This is another powerful data protection mechanism which is meant to prevent objects from being accidentally deleted or modified. There are differences and similarities between holds and retention policies, but one key difference is that a hold is at an object level, while retention policies apply at the bucket level. Their use cases are also slightly different. Retention policies are for regulatory compliance where the data must be retained for a fixed period. Holds are a protection against temporary deletion or for specific objects that require protection. Let's go ahead and see how holds work in practice. Here we are in our favorite Looney Cloud Leader bucket. At this point, we have only two objects in this bucket, orange.jpg and pug.jpg. We will now add another object, so we click on the Upload Files button, navigate to cherry.jpg, hit save, and see that cherry.jpg is added as an object to this bucket. Please remember that our retention policy continues to be in force, and that's why we are now prompted to confirm that we are okay to upload objects to a bucket with a retention policy. We hit confirm and cherry.jpg is successfully added as an object. Now let's select cherry.jpg and then click on Manage Holds towards the center right of the screen. This opens up a dialog where we are told that there are two different types of holds, temporary hold and event-based hold. The fine print on these dialogs is usually worth reading. For instance, with the temporary hold, we are told that it enforces object retention until the hold is removed, even after an object's retention expiration date has passed, and the bucket's retention policy would normally allow deletion. So in other words, the temporary hold takes precedence over the retention expiration date. There's also a sample use case to preserve relevant records until an investigation ends. The other type of hold is the event-based hold. This enforces object retention until the hold is removed, so that's similar to the temporary hold. The difference here is that removing the hold resets the object's retention expiration date and starts the clock on its full retention duration. The sample use case here is a little different. It is to retain records for a set duration of time after a user-defined trigger events. For instance, to retain records for 6 years after a contract ends. Let's now just select a temporary hold and then click on Save Hold Settings. The temporary hold has come into effect on the object cherry.jpg. To confirm this, let's select cherry.jpg from the object browser and navigate into its properties. There in the protection section, we can see that there is information about the retention expiration time as well as about the hold. The hold status is set to temporary hold, and then just above, in the retention expiration time, we can see that deletion or modification is prevented until, and then there's a timestamp. That's 4:42 p.m. on June 6th of 2024. If we scroll down, of course, we can see the actual cherry image. So far so good, the hold and the retention policy both seem to be in force. Now let's see what happens if we scroll up and click on delete. We are asked to confirm the delete because of the soft delete policy, but this deletion fails. You can see at the bottom of the screen the flash message telling us that cherry.jpg could not be deleted. And there's also a new error. We can see that from the 3 in the bright red circle on the top right. Let's click on view details. That's the most descriptive way to find out why exactly this deletion failed. Here we see that the status is failed for one individually selected object. Let's expand that error message, and this confirms why the deletion did not go through. The object is under active hold, one error. This also confirms that the reason that we could not delete cherry.jpg was because of the hold rather than because of the retention policy. Over on the right, we are told that the object cherry.jpg is under active temporary hold and cannot be deleted, overwritten, or archived until the hold is removed. Now, unlike an expiration policy, which is time-based, holds can be removed at any point. We click on the little bucket icon over on the top left. This lists out all of the buckets in this project. Looney Cloud Leader bucket is the one that we are currently interested in. Clicking through takes us to the bucket details. We are in the objects view, so we see the images folder at the center. We click through and we see cherry.jpg along with the other two images. Let's select cherry.jpg and now click on manage holds. In the dialog that opens up, you can see that the checkbox for temporary hold is selected. Let's uncheck that box. There's nothing preventing us from doing so. We click Save Hold Settings and the temporary hold has been removed. Now let's try and again delete this object and see what happens. So we select cherry.jpg and then we click the delete button at the center of the screen. Now, had the hold still been in place, the deletion would have failed. However, after we confirm that we do wish to delete this object, we find that the deletion goes through successfully. This is confirmed by the flash message at the bottom, and the errors over on the top right have gone away as well. Once again, remember that holds and retention policies are both protection mechanisms for data. The difference is that retention policies apply at the bucket level, so all objects in a bucket are governed by a retention policy. Holds are placed at a more granular level, so they apply at the object level. Also, retention policies are time-based and apply for a specified duration, while holds are manually set and removed. When both are in operation, the hold will take precedence over the retention policy. Google Cloud has a robust support for data governance, and one of the important aspects of data governance is the ability to track changes and versions in objects on Google Cloud Storage. As we shall see, there are two important attributes of every object on cloud storage: the generation number and the meta generation number. The generation number is updated every time the data in that object changes. The meta generation number is updated when the metadata associated with that object changes. Let's go ahead and see how these can be used to set up robust data governance on cloud storage. Here we are where we had left off. We are looking at the bucket details of Looney Cloud Leader bucket. Remember that this bucket has a retention policy turned on, and as we shall see, that implies that we cannot turn versioning on for this bucket. So let's click on the bucket icon over on the top left. There's a list of buckets available in this project. There are 3 of them, and we are now going to choose a different bucket, Looney Cloud Leader bucket source. It is this bucket that we will use for this current experiment. Let's click through into that bucket. It's empty. There are no objects in the object browser at the center of the screen. Let's change that. So we click on Upload Files, and then we add 4 files from our local machine: cherry.jpg, hamster.jpg, employees.json, and ccard.csv. We hit open. All 4 of these have now been added to this bucket. We can see them there at the center of the screen. Now let's switch over to Cloud Shell. So we open up Cloud Shell and we run gsutil, and this time we use it to get versioning information. The bucket that we ask for this information about is our old favorite Looney Cloud Leader bucket. The command is gsutil versioning get followed by the bucket URI. The response is rather cryptic. It just says suspended. This is on account of the retention policy that we had set on this bucket. We can confirm that by running gsutil versioning set on for this bucket. So here we are trying to set the property of the versioning attribute to be on for the bucket Looney Cloud Leader bucket. This operation does not go through and we get a pretty clear exception, bad request exception 400. Buckets versioning cannot be set for bucket Looney Cloud Leader bucket that has retention policy. Intuitively, this makes sense. The whole point of a retention policy is to prevent inadvertent updates or deletions to objects on a bucket. But the whole point of a versioning policy is very often to get rid of old non-current versions. The two would conflict with each other, and that's why it's not possible to set versioning for a bucket that has a retention policy. Let's just switch to another bucket, the Looney Cloud Leader bucket source. We now again invoke gsutil versioning set on, but this time the URI that we pass in is for this other bucket. This time the enabling versioning goes through successfully, there's no exception, and we can verify this now by running gsutil versioning get on that same bucket. And this time we do not get the suspended status that we previously had. Instead, the response is that versioning has been enabled. Next, let's use gsutil ls in order to get a listing of the objects on this directory. We see that as expected, there are 4 objects corresponding to the 4 files that we had uploaded. For now, we will be working with the cherry.jpg object. So let's run gsutil ls with the -l in order to get a detailed description of this particular object. This runs through and gives us a lot of information. Right now, what we care about are the generation and the meta generation. You can see them there towards the top left of the screen. The generation is an identifier that starts with 1717 and ends with 8113. The meta generation is currently set to 1. The generation number is a unique ID that's assigned to a specific version of an object. So if we overwrite or replace this particular version, it's going to receive a new generation number. The meta generation number is used to track changes to the metadata of the object. So it will only get updated, specifically it will only get incremented when the metadata of an object is changed. Unlike the generation number, the meta generation number will only change when the metadata is modified, not when the object itself is overwritten. Each of these has an important role to play in data governance because we need to be able to track changes in the object's contents or payload as well as changes in the metadata. In any case, here the generation currently ends with 8113 and the meta generation is 1. Now let's verify that these properties do work as expected. We switch back over to the web console. Let's select this file cherry.jpg and go ahead and modify its metadata. We do this by clicking on that object overflow menu. That's the 3 vertical dots way over on the right. A menu opens up and one of the items available there is edit metadata. This opens up a dialog where we can see first off that there is already some metadata, specifically the content type attribute, which is image/jpg. There's also the content language, which is unset. And then scrolling a little further down, we see custom metadata. Here we can add key value pairs of our choice. We type in type as the key and fruit as the value. Then we hit save, and in this way we've successfully added one new metadata attribute to this particular object. The question now is, how will the generation and the meta generation IDs have changed? That's easy enough for us to check. Let's switch back over to Cloud Shell. We can rerun the last command, that's gsutil ls-l followed by the URI for cherry.jpg. By the way, on Cloud Shell, you can always access the history of your commands by clicking on the up arrow. In any case, we run this gsutil ls-l command and we now again look at the generation number and the meta generation number. The generation number has not changed. It continues to be an identifier that begins with 1717 and ends in 8113. However, the meta generation number has changed. It's been incremented from 1 to 2. And if we look just a little above that, we can see that there is a metadata section in which there's one key value pair. The key is type and the value is fruit. So our updation of the metadata associated with cherry.jpg has gone through successfully. The meta generation number was incremented. The generation number was unchanged. Now let's try another experiment. This time we are going to re-upload cherry.jpg. So we switch back over to the console, click on upload files at the center of the screen, and then navigate to cherry.jpg. We hit open, and now we are going to be prompted to resolve an object conflict. We are told that cherry.jpg already exists in this bucket. How would we like to resolve this? There are two available options. The one that's chosen by default is to exclude object from this upload. But that's not what we want to do, so we go with the other option, which is to override the object. We click on continue uploading, and we can see down below that one file has been successfully updated. Now what do we think would have happened to the generation and the meta generation? Let's switch back over to Cloud Shell and find out. We rerun the same gsutil ls-l command on cherry.jpg, and we notice this time that three things have changed. The generation number has changed. That identifier now starts with 1717 and ends with 2482. Then the meta generation number has been reset back to 1. And finally, you can see that we no longer have the metadata type and fruit that we previously did. What we learned from this is that when we re-upload that same data and create a new version, the generation number changes and the meta generation number is reset to 1. So again, to reiterate, the generation number is a unique ID assigned to a specific version. When that object is overwritten or replaced, it receives a new generation number. The meta generation number, on the other hand, changes when the object's metadata is modified. It is incremented each time that happens. If a new version is created, the meta generation number will reset to 1. In the previous demo, we turned versioning on for a bucket and then went ahead and created multiple versions of a particular object. Once versioning has been turned on, updates to an object will create a trail. Each of those versions is going to be preserved. Each of those versions is also going to be billed separately. And if you stop to think about it over time, that could lead to a pretty hefty cloud storage bill. Thankfully, we can use object lifecycle versioning in order to optimize our cloud costs. Let's see how that works. Here we are back in the console looking at Looney Cloud Leader bucket source. As at the end of the last demo, we have 4 files in the object browser at the center of the screen. Let's now click on Lifecycle at the center of the screen. This takes us into another dialog where you can see that we can specify lifecycle rules. There's a warning right up top that after we add or edit a rule, it may take up to 24 hours to come into effect. As the text here tells us, lifecycle rules can let us apply actions to a bucket's objects based on certain conditions being met. There's also some relevant fine print down below. If an object meets the conditions for multiple rules, then deletion will take precedence over a change in storage class. And secondly, changes to older storage classes will take precedence over changing to warmer ones. Both of these rules make sense if you consider that lifecycle management is primarily a cost management tool. Just down below is a button where we can add a rule, but before we do that, let's verify that we don't have any pre-existing rules. For that, we click on Configuration, and there we scroll down to the bottom where we can see that under Lifecycle Rules, we have none. Before we add that rule, there's another property of the bucket that we need to look at that's under Protection, and this has to do with soft delete. You can see here that soft delete is enabled. There's a retention period of 7 days. And as the text there tells us, deleted objects will be kept for this specified period after they've been deleted, and they can be restored during this time period. Scrolling a little further down, we can also see here there is a reference to object versioning. We have a green checkbox indicating that object versioning is on, but then we have a warning icon. You have no lifecycle rules that apply to non-current versions. The warning here is because we might end up with a very large number of non-current versions and a correspondingly large cloud storage bill. Let's heed this warning. We click on the Manage Rules button there. This takes us into the Lifecycle tab. This is where we were a moment ago. So you can see how all of these different features of cloud storage buckets interplay with each other and their workings affect each other. In any case, let's now click on the Add a Rule button, where right up top we are asked to first select an action. Down below, you see that we can also select object conditions. Let's focus on the actions first. Allowable actions are set storage class to nearline, old line, archive. That's the first three options. Then delete object, and finally delete multi-part upload. Right now, we are interested in deleting objects, so that's the radio button that we select. A warning appears telling us that objects cannot be restored after deletion unless object versioning is enabled. And if versioning is enabled, then live objects will be made non-current and non-current versions will be permanently deleted. What we learn from this is that if we have versioning on and we delete a versioned object, the deleted object is going to be treated as non-current, and that adds to the number of versions of the object. We'll see how this plays out in a minute. Let's click on continue. We are then prompted to select the object condition when this action will be triggered. You see here that we have conditions related to age, created before, storage class matches, number of newer versions, days since becoming non-current, a date that this object became non-current before, live state, days since custom time, and custom time before. Let's check the number of newer versions box, and that opens up a separate input where we are prompted for how many newer versions we want to have before this rule kicks in. We type in 3, so effectively this will cause the deletion of an object when there are 3 newer versions. We hit continue, and at this point we can actually create the object lifecycle rule. Now we won't actually demonstrate this rule in action because these rules take some time to kick in. But here we are back in the lifecycle tab, and if we scroll down, you can see that we now have a rule in there. The action is delete object, the object condition is 3 plus newer versions, and it works with object versioning. This is Google Cloud telling us that there is a dependency between the object versioning feature and this particular lifecycle rule. In the previous demo, we focused on the interplay between two features of Google Cloud Storage, namely Object Lifecycle Management and Object Versioning. In this demo, we are going to focus on the interplay of two other features, Soft Delete and Versioning. We are still working with the same bucket as in the previous example, that's Looney Cloud Leader bucket source. Let's click on the Objects tab over on the top left, and you can see here that we have 4 files, and one of them is the employees.json file. Let's click through into the object, we get to the object details, and we can see the authenticated URL. Clicking on that opens up the file itself in a different tab. We can quickly scroll through the contents and then return to the console where we see that there are 2 tabs, Live Object, which is what we've currently selected, and the version history. Let's click on version history, and when we do that, we can see all versions of this particular object. At this point in time, there's just the one version. We can see from the object version, which says employees.json within parentheses live object, that this is the live object. There are no previous non-current versions for this particular object. Let's use the breadcrumbs to go back out to the bucket, and there let's click on the protection tab at the center of the screen. You can see here that soft delete is enabled, the retention period is 7 days. Scrolling a little further down, we have object versioning turned on. In addition, we also have one lifecycle rule. That's the one which we defined in the previous demo. Now, it will be a little confusing to study object versioning and soft delete on at the same time to begin with. So let's start by turning object versioning off. We click on the green checkbox. We are asked to confirm that we would like to turn off object versioning. We provide this confirmation, and then you can see that object versioning is off. And if we scroll a little further up, soft delete is still on with a retention period of 7 days. Now, one important point to note here, if we turn versioning off, then all of the pre-existing versions that we happen to have for our objects are unaffected. So by turning versioning off, we have not deleted or done anything to the old versions. So again, at this point, we have soft delete on and object versioning off. Let's click on the Objects tab over on the top left, and let's return to employees.json. We select it from the object browser and then click on delete over up top. So we'd like to delete employees.json, keeping in mind that we have soft delete turned on and versioning turned off. We are asked to confirm this deletion, and you can see that the message also tells us that a soft delete policy is enabled for this bucket. The message reminds us that deleted objects will be kept in that soft deleted state for 7 days before being permanently deleted. In that soft delete state, they can be restored. In any case, let's go ahead and confirm the deletion. Employees.json is deleted successfully. It no longer shows up in our list of objects. Now, if we look closely, we can see that this list of objects is actually only a list of live objects. How do we know? Well, because there's a drop down towards the center right of the screen. Show live objects only. Let's expand the drop down, and the other valid choices there include live objects only, live and non-current objects, and soft deleted objects only. Let's choose the last option, soft deleted objects only, and sure enough, we find employees.json. This is the object that we just deleted a moment ago. Remember, versioning is off, soft delete is on, and that's why when we deleted employees.json, it went into the soft deleted state. Let's go back to that dropdown and choose the middle option, live and non-current objects. And here we see that we have 2 live objects and 1 non-current object. That's the middle row for cherry.jpg. How do we know that cherry.jpg is not live? Well, because you can see under version history that it's got 1 non-current version. ccard.csv and hamster.jpg are both live objects because they don't have any version history. Now, if you're wondering where this non-current version of cherry.jpg came from, remember that in a previous demo, when we had object versioning on, we had updated the version of cherry.jpg. That was while working with the generation and the meta generation. We had added metadata and then updated the version by re-uploading the file. The version that was replaced went into this non-current version state. So the lesson we learned from this is that if we have object versioning on and then we update or delete an object, then the older versions go into the non-current state. There's another point worth noting about this output here. Again, notice that we've chosen live and non-current objects, and notice that we do not see the recently deleted employees.json file in here. That's because that shows up if we choose soft delete. By this point, we've learned that if soft delete is on and versioning is off, then deleting an object sends it into the soft delete state. Now let's see what happens if we turn object versioning back on. We click on protection towards the top center of the screen and we scroll down. Object versioning is currently off. Let's click on that and turn it back on. We are also informed that we have one lifecycle rule that applies to non-current versions. This is just an FYI. We hit confirm and we can see from the green checkbox that object versioning is back on. Looking just up above, we can also see that soft delete is still on with a retention period of 7 days. Let's now click on the buckets icon over on the top left. This gives us a listing of all of the buckets in this project. As before, there are 3. Let's click on Looney Cloud Leader bucket source. Here we are. Let's now click on cherry.jpg and go ahead and delete it. The question now is, with object versioning back on, what will happen to this deleted version? Well, this is not a trick question. In fact, the answer is visible right on screen now. The dialog tells us, because object versioning is enabled, this action will create a non-current version of the selected object. So if we delete an object when object versioning and soft delete are both on, then that object goes into a non-current state. It does not go into the soft delete state. Further confirmation, the flash message down below. Cherry.jpg made non-current. When we deleted cherry.jpg, it disappeared from the object browser at the center of the screen. And that's because the drop-down over on the center right is set to show live objects only. Let's change that. So we open up the drop-down and we choose soft deleted objects only. What do you think? Is there going to be any change? Well, the answer is no. There's only one soft deleted object, and that's employees.json. The reason that this soft deleted object appears here is because we deleted it when object versioning was turned off. What happens if we again change the drop-down setting and this time pick live and non-current objects? This time there's something more interesting going on. You can see that for cherry.jpg, which is the middle row, we have not 1 but 2 non-current versions. We can confirm this by scrolling over to the right. So if we delete an object and object versioning has been turned on, the deleted object will go into a non-current version state. Let's click through on cherry.jpg. This in turn leads us to the version history, and now in the version history, we see that there are two versions here. And very conveniently, over on the right, there is a restore button. Let's click on restore for one of these versions. We are asked to confirm that we would like to restore this version. This dialog also displays the generation number and the meta generation number, and that generation number is familiar. It's that same identifier which started with 1717 and ended with 2482. This is the version that we re-uploaded after we had set the metadata. We go ahead and hit confirm, and we've successfully restored cherry.jpg. The version history now has 3 rows, and the first row, the one on top, now says live object. We started this course off by examining the various storage options for unstructured data, focusing on Google Cloud Storage as a primary solution. We navigated through the Google Cloud Console, familiarizing ourselves with its interface and capabilities. We explored the properties of buckets, which are fundamental containers in GCS, and learned how to create and manage them effectively. We also learned about storage classes such as standard, nearline, coldline, and archive, and the trade-offs between storage and access costs. Next, we learned how to view objects and their metadata within GCS, gaining insights into the stored data's attributes and structure. We practiced working with objects using the gsutil command line tool, which provided hands-on experience with essential data management tasks. We also explored bucket level retention policies, which help ensure data is retained for a specified period, and discussed the importance of placing holds on objects in order to prevent accidental deletion or modification. Finally, we explored the concepts of generation and meta-generation attributes, which track the versions and changes of objects within GCS. We studied object lifecycle rules, which automate data management by defining actions such as transitioning storage classes or deleting objects after a certain period. Additionally, we covered object versioning and the soft delete feature, which enable the recovery of previous versions of objects and provided an extra layer of data protection. In conclusion, we built a solid foundation in managing unstructured data using Google Cloud Storage. We covered the essentials of bucket properties, object management, and data retention policies, as well as advanced features like lifecycle rules and versioning. We are ready to move on to the next course in this journey, storage options for structured data on Google Cloud. Effectively managing structured data on the cloud is crucial for ensuring reliable and scalable database operations. Leveraging services like Cloud SQL, AlloyDB, and Cloud Spanner allows organizations to optimize their data management, enhance performance, and integrate seamlessly with other cloud services for comprehensive data solutions. In this course, you will learn about storage options for structured data with a focus on the features of Cloud SQL. You will gain hands-on experience in provisioning a Cloud SQL instance, managing users, configuring settings, and ensuring security. You will also learn how to connect to a Cloud SQL instance using various tools. Next, you will learn about the high availability configuration to ensure continuous operation and reliability. You will explore the benefits of choosing Cloud SQL for different use cases, emphasizing its scalability and integration with other Google Cloud services. Additionally, you will use Cloud SQL Studio, a web-based interface, to simplify database management tasks, execute queries, and so on. Finally, you will explore advanced database solutions, starting with an introduction to AlloyDB, a fully managed PostgreSQL-compatible database service designed for high performance and scalability. You will also learn about Cloud Spanner, which is ideal for transactional data, offering global consistency and horizontal scalability as well. This course will provide you with a solid conceptual foundation in managing structured data using Cloud SQL, AlloyDB, and Cloud Spanner. Let's now turn our attention from unstructured to structured data. It's time to talk about storage options for structured data. Once again, to keep things simple, we'll divide all data into only 2 categories, unstructured and structured. We will cover semi-structured data such as JSON, XML, and other document data within structured data in this conversation. We've already spoken about the different options for unstructured data, including persistent disks, file storage, and Google Cloud Storage buckets. Let's now turn our attention to the other branch of the tree and focus on structured data. Very broadly, a choice which immediately faces us is whether we would like to access our data using SQL or NoSQL. For most use cases, SQL is the preferred option, and if that's the case, we are faced with our next choice, which is whether we are interested in transaction processing or analytical processing. Transaction processing is often referred to as OLTP or online transaction processing. OLAP, on the other hand, refers to online analytical processing. Previously, we've spoken at length about the difference between databases, data warehouses, and data lakes. You can think of databases as suitable for OLTP and data warehouses as suitable for OLAP. For use cases where we have a large number of individual transactions that need to be processed in real time, specifically where there are a lot of write and update operations, then our use case is OLTP. A typical example of OLTP would be in a banking system where each deposit, withdrawal, transfer, or payment transaction needs to be recorded and processed immediately to update all of the account balances. In such cases, relational databases such as Cloud SQL or Cloud Spanner would be our choice on the Google Cloud Platform. On the other hand, for analytical processing, a data warehouse such as BigQuery would be our choice of technology. Let's take a moment to contrast transaction processing and analytical processing. Transaction processing deals with the day-to-day operations of the enterprise, and there is a distinct emphasis on real-time transaction processing. Remember that a transaction is a set of operations which all succeed or fail together. A transaction can be committed or rolled back. Analytical processing, on the other hand, focuses on strategic decision making and on time trends and historical data analysis. Next, in terms of data volume, transaction processing focuses on a large number of small individual transactions. Analytical processing focuses on large volumes of historical data for business intelligence and senior management decision making processes. In terms of query complexity and type of operations, transaction processing involves simple queries involving a few records at a time. Transaction processing is notably heavy on write and update operations which need to be completed in real time. Analytical processing queries are a lot more complex. These typically tend to be mostly reads and they involve aggregations, joins, and scans across large datasets. Real-time or interactive write and update operations are very infrequent. Most updates or writes happen in batch mode. OLTP systems are optimized for fast query processing, high transaction throughput, and with an emphasis on data integrity. That's why relational databases typically have ACID compliance. ACID is short for atomicity, consistency, isolation, and durability. On the other hand, OLAP systems are optimized for read-heavy operations, data retrieval speeds, and support for complex queries. In terms of data design, data stored in relational databases is highly normalized in order to minimize redundancy and ensure data integrity. Database schemas are intentionally designed to handle numerous small transactions efficiently. In data warehouses and OLAP use cases, the data is usually denormalized and it's stored in a multidimensional schema such as a star or snowflake schema in order to optimize query performance and to simplify complex analytical queries. The Google Cloud Platform has a variety of services for each of these use cases. For transaction processing, we have Cloud SQL as well as Cloud Spanner. Cloud SQL is a fully managed relational database service. It supports MySQL, Postgres, and SQL Server. It automates the provisioning, patch management, and backups of databases and allows users to focus on app development rather than database administration. Cloud SQL ensures high availability. It has automatic failover and replication across multiple zones. It offers inbuilt security features including encryption at rest and in transit, identity and access management, and network isolation options. Cloud SQL is ideal for applications that need an RDBMS with managed services such as e-commerce platforms, web apps, or custom enterprise applications. Cloud Spanner is also an RDBMS offering, but it's far more premium and powerful. It's horizontally scalable, strongly consistent, and globally distributed. This combines the benefits of an RDBMS with non-relational scalability. It offers both SQL queries and transactional consistency at scale. Spanner is designed to handle high traffic, mission critical applications with automatic sharding, replication, and seamless scaling across regions. So remember, Cloud Spanner is global, Cloud SQL is regional. That does it for the transactional databases. For analytical processing, we come to Google's flagship BigQuery data warehouse product. BigQuery is a fully managed, serverless, and highly scalable enterprise data warehouse. It's designed for large scale data analysis. It's accessed using SQL queries on massive datasets. It has high speed and efficiency. It relies on data stored in a proprietary columnar format and integrates seamlessly with various data sources and other cloud services. BigQuery is certainly one of the most important and popular products on the Google Cloud Platform. Coming now to the NoSQL offerings on the GCP, there are two important ones, Bigtable and Firestore. These are very different from each other. Bigtable is meant for time series data, real-time data, and other applications which require very fast data processing and retrieval. Bigtable works at massive scale, so very large datasets with very high read and write demands. Firestore, on the other hand, is a NoSQL document database that can be used for semi-structured data such as JSON or XML. Because semi-structured data often features hierarchical data structures and nested elements, Firestore supports these using collections and documents. It's intuitive and simple to express and model complex data relationships. Firestore also offers real-time synchronization, offline support, and is suitable for web and mobile apps. It also integrates seamlessly with Firebase and other Google Cloud services. By this point, you might be finding yourself a little overwhelmed by all of the GCP services and their non-GCP equivalents. So here is a table summarizing all of this. For block storage, the GCP service is persistent disks or local SSDs. Equivalents on the other hyperscalers are Amazon's Elastic Block Store or EBS and Azure Disk. Next, for object storage, these are the data lake offerings, Google Cloud Storage buckets, that's for object storage on the GCP. Corresponding non-GCP offerings include AWS S3 and Azure Blob Storage. For relational database use cases with small regional payloads on the GCP, you would go with Cloud SQL. Remember that supports MySQL, Postgres, and SQL Server. On AWS, you could use RDS and SQL database on Azure. For a relational database that can support large global payloads, you'd use Cloud Spanner on the GCP, Aurora DB on Amazon, or Microsoft Azure's SQL DB Hyperscale. For semi-structured data, such as a document database, you'd use Firestore on the GCP, DynamoDB on Amazon, and Cosmos DB on Microsoft Azure. There's a special niche here on the GCP for large, naturally ordered data with NoSQL access. That niche is filled by Bigtable. On the other cloud platforms, you'd continue to use DynamoDB and Cosmos DB. And finally, in the data warehousing space, the offering from the GCP, of course, is BigQuery. The competing offerings are AWS Redshift and Azure Synapse Analytics. Now that we have a good big picture understanding of the different storage services available on the Google Cloud Platform, let's go in detail into each of them in turn. We will begin with a discussion about Cloud SQL for transactional data. We've already seen how Cloud SQL is suitable for relational data where our payloads are reasonably small and where our use cases are regional. If it's global availability that we are interested in, then we should be looking at Cloud Spanner instead. Cloud SQL is a fully managed relational database service. It supports MySQL, Postgres, and SQL Server. It offers high availability, automatic backups, and easy scalability. It's got a bunch of built-in security features like encryption, role-based access control, and VPC peering. It also greatly simplifies database management and it allows you to focus on development and building applications rather than on DBA admin tasks. Here is the architecture of a Cloud SQL instance. As we can see here, effectively each Cloud SQL instance is powered by a virtual machine instance. This is a Google Compute Engine VM, and that VM instance runs the database software, which might be MySQL, Postgres, or SQL Server. It also has service agents that provide supporting services such as logging and monitoring. Over off to the left, you can see the high availability standby. That kicks in if we've got high availability enabled, in which case there's going to be another standby VM instance that's going to be in a different zone from the original VM instance. It's going to have an identical configuration to the primary VM. Notice at the bottom how a persistent disk is used for storage. While talking about block storage, we had mentioned that databases are one of the primary use cases for persistent disks, and you can see why here. So persistent disks form the basis of the Cloud SQL storage layer. Right up at the top, we have an application which connects to the Cloud SQL instance through a static IP address. The reason that IP address is static is so that the IP address remains constant throughout the lifetime of the Cloud SQL instance. Please note that all of this is abstracted away from us by the Google Cloud Platform. Cloud SQL currently supports three choices of database engine: MySQL, Postgres, and SQL Server. MySQL is a popular choice for web apps and data warehousing. Cloud SQL for MySQL offers the choice of different versions and will also abstract us away from many DBA functions. For instance, it will support replication, sharding, full text search, managed backups, high availability, and integrated security features. MySQL is open source and so is Postgres. Postgres is considered a more advanced RDBMS. It's known for its robustness and standards of compliance. It's commonly used in more advanced use cases and data analytics workloads. Cloud SQL for Postgres provides a fully managed service, including automatic backups, updates, high availability configurations, and Postgres itself supports various features such as indexing, JSONB, full text search, and geospatial data. The third database engine supported by Cloud SQL is SQL Server. This is a proprietary RDBMS developed by Microsoft, and Cloud SQL for SQL Server offers a managed database service through which you can integrate with tools like SQL Server Management Studio and Visual Studio. Once again, Cloud SQL will abstract away a lot of the routine tasks such as patches, backups, and monitoring, and you as the consumer of the Cloud SQL service can focus on app development and database optimization. Cloud SQL offers a couple of different editions when you're working with MySQL or Postgres. There's Cloud SQL Enterprise Edition. This has all of the core capabilities. And then there's also something known as Cloud SQL Enterprise Plus. This has a few additional bells and whistles. These are performance enhancements that can drive maximum performance. The first is something known as data cache, which improves read performance. Data cache makes use of a fast local SSD instead of the ordinary persistent disk, and that helps to store data pages that are read frequently. The use of the SSD can give a speed up of up to 3 times in read performance. Data cache is an optional feature. You can enable it during instance creation or after the instance has been created. The Enterprise Plus edition also gives enhanced write performance with an improvement of up 2 times in write latency. You might want to use this feature when you have write intensive applications that need low latency and high throughput. And finally, the Enterprise Plus edition has an engine auto tuning feature to try and best match the capabilities of the database server with the underlying instance. In this way, Cloud SQL is a managed database service. It's got a bunch of interesting features. It has, for example, automated and on-demand backups. These ensure data protection and disaster recovery. The automated backups are scheduled daily, and you can configure the retention period according to your use case. On-demand backups allow you to create backups at any point. You can also restore your database from a specific backup and recover from accidental data loss or corruption. Backup data is encrypted both in transit and at rest. As we had seen in the block diagram, Cloud SQL offers a high availability configuration that includes automatic failover. This ensures minimal downtime. The way this works, there's a primary instance which replicates data synchronously to a standby instance. If the primary instance becomes unavailable, the standby instance is automatically promoted to the primary role. The use of the static IP makes sure that applications connecting to the database do not experience any changes. Additionally, Cloud SQL performs regular health checks and maintenance to ensure that the instances are working fine. Cloud SQL also offers a number of features related to network connectivity. There are multiple network connectivity options, so users can connect to Cloud SQL instances via public IP addresses or using private IP addresses for enhanced security. You can also make use of VPC peering and VPN to secure communication between Cloud SQL and other network resources. Finally, Cloud SQL also has a feature known as Cloud SQL Proxy. This can be used to simplify database access without exposing the database to the public internet. Next, Cloud SQL supports exports and imports. These help with data migration and backup management. You can export your data in SQL or CSV formats, and that makes it easy to move data between instances or to and from external storage solutions. Cloud SQL also has a close integration with Google Cloud Storage, and this allows for large scale data transfers. Cloud SQL takes a lot of the load around maintenance and updates off of your hands. It ensures that maintenance and updates occur automatically, and it does so using the latest patches and features. You can schedule maintenance windows to minimize the disruption to operations, and you can rely on the managed service to make sure that the latest security updates and performance optimizations are applied to your database instance. Like all other GCP services, Cloud SQL 2 has excellent monitoring and logging. It integrates with Google Cloud's Operations Suite, this is formerly known as Stackdriver, and this allows users to set up custom metrics, alerts, and dashboards. And in this way, you can identify and diagnose issues and optimize your performance. This monitoring is real time, and you can look into resource utilization, query performance, and connection statistics. It also offers automated notifications and detailed logs. Cloud SQL integrates with Google Cloud Logging, and it allows you to filter, search, and analyze logs in real time. This can also help in identifying suspicious activities, diagnosing performance issues, and keeping you compliant. Logs can be retained for extended periods. Next, let's turn our attention to the high availability configuration in Cloud SQL. To best understand that, we should start by first discussing the more basic single instance version. Remember that at its heart, a Cloud SQL instance consists of a virtual machine instance which is running the database software and which stores the database data on a persistent disk. There's a static IP address through which applications are able to connect to that instance. Now, that Cloud SQL instance, like any other, needs to reside in some zone. Very broadly, you can think of a zone as a location where Google Cloud resources are deployed, or to simplify things even further, you can think of one zone as one data center. Now, clearly, if that zone fails, then the database will become unavailable for the simple reason that the VM instance is going to be unavailable. And that's why the single instance version of Cloud SQL is not highly available. It is exactly this shortcoming that the high availability configuration tries to mitigate. High availability effectively replicates the Cloud SQL server. The original instance is called the primary instance, and this is constantly replicated to another VM instance called the standby instance. The primary and the standby both need to be within the same region, but they can be and will be in different zones. And for this reason, Cloud SQL can be thought of as a regional service. It's important to note that the standby instance cannot be used for read queries. It's only meant as a replica in case the original or primary instance goes down. The way the high availability configuration works, all changes made to data on the primary are replicated to the standby. This replication is synchronous and occurs via each zone's persistent disk. Remember, after all, that each instance is in a different zone, each is attached to its own persistent disk, and this replication occurs between the persistent disks of the primary and the standby. It's important to understand the meaning of synchronous in this context. Any write or update that's made to the Cloud SQL instance is not complete until it has been replicated and shows up in the data on the standby instance. This synchronous replication is going to introduce a slight latency overhead relative to, say, asynchronous replication, but it greatly enhances the reliability and availability of the data. The net effect of all of this is that all write operations made to the primary are also going to reflect on the standby. A couple of caveats to keep in mind. The standby instance, which is known as the failover replica, must be in the same region as the primary. Also, when we configure Cloud SQL in its high availability configuration, we effectively require two VM instances, and for that reason, a high availability configuration is going to cost twice as much as a standalone instance. Here is a visual representation of the high availability configuration. There's a client app which connects to the Cloud SQL instance. Within the Cloud SQL instance, abstracted away from us are two VM instances, the primary and the standby. The dashed arrow between the primary and the standby indicates the synchronous replication of the data from the primary to the failover. The client app communicates using the IP address that is associated with the primary. And note also that the primary and the standby are in different zones but within the same region. Cloud SQL is a regional service. The data replication is synchronous, which means that changes made to the primary reflect immediately on the secondary. Now let's say that the primary suffers an outage. It goes offline, but there's nothing to fear because Cloud SQL's health checks will pick up on that and the client request will get rerouted to the standby. Because it's a static IP address, there's no change from the perspective of the client. Now let's say that at some future point, the primary zone or the primary instance recovers. The failover will not automatically revert. You can perform a manual failback in order to go back to using the primary. Beyond the high availability configuration, Cloud SQL also supports replicas. These are important because Cloud SQL scales vertically. That is, as the load increases, a more powerful VM instance is going to be provisioned. Beyond a certain threshold, say about 10,000 queries per second, performance starts to degrade. So the capabilities of that instance start to become a bottleneck. Replicas on Cloud SQL help to mitigate this. The way this particular feature works, there are effectively read replicas, so all writes are still made to the primary, but these are then replicated asynchronously, that is, with a lag to the read replicas. And then additional incoming read requests can be redirected to the read replicas. In this feature, unlike with the high availability configuration, the propagation of the writes to the read replicas happens asynchronously, which means that there is a small chance that a read request sent to a read replica might end up with inconsistent data. This is known as eventual consistency. It's a weaker guarantee than strong consistency, but it's usually fine for read-heavy applications such as reporting and analytics. Also, in the case of failover, the read replicas could be promoted to act as a new primary instance. Once again, however, because of this asynchronous replication, there might be a brief period during which the most recent changes are not reflected in the read replicas. Because Google Cloud SQL is something of the starter service for databases on the Google Cloud Platform, it's worth our while discussing in what situations you'd actually choose Cloud SQL. As a classic RDBMS running MySQL, Postgres, or SQL Server, Cloud SQL only makes sense for transactional workloads that require the asset properties: atomicity, consistency, isolation, and durability. If it is an RDBMS that you're looking for, there are a couple of use cases that spring to mind. The first is migration scenarios. This is where you are already using an RDBMS on-premise or on a competing cloud platform. In any of these cases, it's quite likely that you would have been running MySQL or Postgres or SQL Server, and for that reason, Cloud SQL is an obvious first choice when you switch to the GCP. Cloud SQL also makes sense for cloud-first scenarios because, after all, Cloud SQL supports MySQL, which in particular is a very easy to use database. Let's talk about each of these use cases, starting with some migration scenarios. Let's say that you are currently using on-prem MySQL, Postgres, or Microsoft SQL Server. Well, in that case, when switching to the GCP, the obvious choice is Cloud SQL. Let's say that you're using some other cloud RDBMS on one of the other hyperscalers. In that case, as long as your payloads are less than 64 terabytes in size, Cloud SQL is still a good choice. Remember that this 64 terabyte constraint comes from the fact that Cloud SQL effectively runs on a VM instance and uses a persistent disk for storage. 64 terabytes is the practical limit for how far you can go with a persistent disk. What if you are using Oracle? Well, in that case, your best bet is to go with a GCE VM instance with a custom Oracle image. This will also hold true for other proprietary databases other than MS SQL Server. Remember that MySQL and Postgres are open source. SQL Server is the one proprietary database that is natively supported by Cloud SQL. For other proprietary databases, you'd probably want to explore the VM with a custom image route. It's also worth keeping in mind that Cloud SQL is regional, and so if you have users concentrated in one region, then Cloud SQL again is a suitable choice. On the other hand, if you end up having users distributed globally, then you ought to be considering Cloud Spanner. We'll also be talking about another offering known as AlloyDB, which allows you to set up a very heavy duty Postgres installation. More on that in just a bit. Coming to Cloud Spanner and Cloud SQL, if your user base is global, then you definitely ought to consider Cloud Spanner because, as we just discussed, Cloud SQL is regional. Next, we've also got to consider scaling. If vertical scaling is fine, then Cloud SQL will suffice. However, if what we need is horizontal scaling with virtually no limits, then Cloud Spanner is the go-to choice on the Google Cloud platform. These are some of the considerations if you are an existing user looking to migrate. On the other hand, if you are a cloud first user looking to start with a clean slate on the Google Cloud platform, here is a quick comparison of Cloud SQL with other GCP technologies. We've just discussed Cloud Spanner. This is an RDBMS with horizontal scaling and global reach. BigQuery is the data warehousing product from the GCP. You definitely should consider BigQuery if you have an analytical use case. BigQuery is one of the most popular products on the GCP. Bigtable works for NoSQL use cases where there is some kind of natural ordering in your data. It's broadly similar to HBase. If your data is semi-structured, hierarchical, JSON, XML, or HTML, and if your use case relates to a mobile or a web app, then you should consider Firestore, which is a NoSQL document database. And finally, for unstructured data storage, you can make use of Google Cloud Storage buckets. This is effectively the data lake offering on the GCP. Let's run through some simple exercises using Cloud SQL. Here we are on the Cloud Console. We click on the navigation menu, aka the hamburger over on the top left. We click on View All Products, and then we navigate down this list until we get to the Databases section. Cloud SQL appears here. It's simply known as SQL. We click the pin icon next to it, and then we again click on the hamburger. We see the pinned products include SQL right up top. Let's click on that, and that takes us into the Cloud SQL detail page. Right up top, we have a big bright blue button that allows us to create an instance. Another option that's less prominently displayed is Migrate Database. Down below, we have some information about how to get started, and then at the very bottom again, we have the Create Instance button and View Documentation. Let's scroll back up to the top and click on that Create Instance button. That takes us to a dialog where we are asked to choose our database engine. There are three choices available here: MySQL, Postgres, and SQL Server. There's also a plug here for AlloyDB for Postgres, and if you'd like to choose AlloyDB, there's a button that allows you to do that towards the bottom left. In any case, we are interested in MySQL, so we click on Choose MySQL, and that takes us into the Create a MySQL Instance dialog. We enter an instance ID, and then we experimentally click on the No Password checkbox. This tells us that without a root password, anyone will be able to access our instance with full admin privileges. That's definitely not what we want, so we uncheck this checkbox and enter a password. Initially, we've entered a simple password, but then we notice that Cloud SQL allows us to set a password policy. So we expand the password policy tab, and here are some policies. These could include minimum length, required complexity, restricting password reuse, and disallowing the use of the username in the password. Let's go ahead and check one of these boxes, the one with minimum length. So we are going to set the minimum length to 10 characters. As soon as we check this box, you can see that our simple password up above no longer qualifies. That's why we have that red exclamation mark telling us that our password must be at least 10 characters long. So we now enter a longer password and we get the green checkbox down below. Next, we can choose the version of MySQL. So here the major version is MySQL 8.0. There are various minor versions available. We'll just go with the default. That's 8.0.31. The next choice is between Enterprise Plus and Enterprise. As we can see here, the Enterprise Plus has higher availability and more advanced features. You can see that right now it's Enterprise Plus that's selected, that's the radio button, and that affects the choice of presets down below. So within Enterprise Plus, there are two presets called Production and Development. The Production preset is highly available. Development is single zone. The production machine is also more powerful. Now, if we switch to the Enterprise Edition, then the choice of presets will change as well. Now, there will be three instead of two: production, development, and there's also now a sandbox. For our simple use case here, the sandbox is perfectly fine, but for a real world choice, you might want to click on that Compare Edition Presets link button. That opens up a dialog where up top we can choose three different presets. So these might be either Enterprise or Enterprise Plus, and then within the choice of the edition, we can also specify the preset. And in this way, we can set up a horse race between three different choices of edition and preset. We can then compare these choices along different dimensions such as the vCPU, memory, storage, zonal availability, automated backups, point-in-time recovery, and so on. Once we are done comparing these choices, we can click on Close towards the bottom left, and that takes us back to the Create MySQL Instance dialog. Next up, we can choose the region and zonal availability. The region is chosen via a drop-down, and zonal availability can be either single zone or multiple zones. Multiple zones will give us a more highly available offering. As the fine print there tells us, that will give us automatic failover to another zone within the selected region. Remember again that Cloud SQL is a regional product, so we cannot pick zones across different regions. That's why we only have one choice of region up top. You can use the region dropdown to pick a region of your choice. For our current purposes, the default, that's US Central 1, that's sufficient. Now, in case you choose to go with the highly available configuration, then we've got to pick multiple zones within that region. So we choose the Specify Zones option, and here we've got to pick a primary and a secondary. As those dropdowns tell us, these will both need to lie inside the region that's selected up above. That's why all of these choices are in US Central 1. Also, the primary and the secondary zones cannot match, as you can see from that red warning there. A single zone configuration is sufficient for our purposes, so let's select single zone. We still have to pick the one primary zone. Let's go with US Central 1A. Next, we move to customizing our instance. Remember that Cloud SQL runs on a VM instance, and these here are the configuration options related to that. For instance, we can choose the machine configuration such as the vCPUs and the memory. Now, the cost can change a lot based on our choices here. You can see for now that the default that so far has been selected costs about 14 cents per hour. We see that towards the top right. Let's now experiment with some of these different dedicated and shared core configurations as well as memory choices, and you can see just how much this changes. If we go to shared core with just one CPU, the pricing estimate is now just 1 cent per hour. We can also get a cost breakdown there that will give us the estimated resource costs, usage and traffic costs, and more. Notice also that there is a feature known as data cache. This is only available in Enterprise Plus. This adds a local SSD for read caching. That checkbox is not enabled because we've currently selected the Enterprise Edition. Let's keep scrolling and now look at the storage choices. We can go with SSD or HDD and also choose the storage capacity. Also notice the checkbox Enable Automatic Storage Increases. So Cloud SQL offers automatic vertical scaling in terms of storage. As it tells us, if enabled, whenever you are nearing capacity, storage will be incrementally and permanently increased. Moving on, we can also configure encryption options. There are two choices: Google Managed Encryption or using a key that's on Cloud KMS. Cloud KMS is Google's cloud key management system. The defaults are fine here. Let's now open up the connections section. Here you see that there are two choices, private IP and public IP. If we go with the private IP, then our Cloud SQL Server will only be accessible from within Google Cloud. If we go with a public IP, then it will be accessible to anyone on the wider internet. Next, we get to the data protection section. Here, we can configure automated backups and point-in-time recovery. Automated daily backups have been checked by default. The number of backups is set to 7 by default, and there's also a backup window 11:30 a.m. to 3:30 p.m. Point-in-time recovery is also enabled by default, as the fine print there tells us. This allows us to recover data from a specific point in time down to the fraction of a second. This requires binary logging, which is needed for the replication. The number of days worth of logs is set to 7 by default, and the range is 1 through 7 for the Enterprise Edition. Scrolling a bit further down, we have Enable Deletion Protection. This is also checked by default. As we can see, this is under the Instance Deletion Protection section, and if this checkbox is enabled, then the instance cannot be deleted until the feature is explicitly disabled. There are a lot of choices to make, and that's because Cloud SQL is providing us a managed version of MySQL. It's abstracting away a lot of the actual maintenance and admin work. Speaking of maintenance, here we are in the maintenance section. As the fine print tells us, this will occur once every few months, and it will need the instance to be restarted while updates are made. So this is going to lead to short service disruptions. We can configure the maintenance timing. This is relative to when a new version is available. So week 1 is the default, and there's also a choice of maintenance window. If you'd like to make sure that this service disruption due to maintenance does not occur, you can install a deny maintenance period, which can last up to 90 days. There are some additional settings that we can configure related to flags, query insights, and labels. You can see that these are also available right here. However, we've hit the high points, so let's now move on and actually create our instance. We scroll down and click on that big bright blue Create Instance button at the bottom. Now, it takes a long time to create a Cloud SQL instance. After we click that Create Instance button, we are taken to a page where we see our Looney MySQL instance being provisioned. We can click on the All Instances link button. That takes us to a page where we have details of all of the instances. And right now, for the Looney MySQL instance, the icon shows that it's currently being provisioned. You can see here that it's going to take several minutes, and when we stop to think about it, that makes sense. It's because the VM instance has to be provisioned, MySQL or our choice of database engine has to be installed, and all of the dependencies have to be set up. So this is a pretty heavy duty process, and you can see here that it takes 9 minutes and 55 seconds. At this point, our Looney MySQL instance has been created, and over up top we can see in the list of instances that it's got a bright green checkbox next to it. Let's pick up right from where we left off at the end of the last demo. Here we have a list of all of the SQL instances in our project. We currently have just one, that's the Looney MySQL instance. If we hover over this, we see the status shows as runnable. If we'd like to understand what the tooltip is telling us, we can now hover over the question mark next to the instance ID. Here, we can see the explanations of the different instance status values. Runnable means that the instance is running or that it is ready to run when accessed. Other values of instance status include stopped, suspended, creating instance, deleting instance, and under maintenance. Scrolling a bit further down, the last instance status is failed to create or fatal error. In any case, let's now move on and perform some operations with our instance. We click through into our MySQL instance and start to explore the UI. Here right up top is a visualization of various metrics. Right now it's showing CPU utilization, but there is a long list of other metrics that we could track. Over on the top right, we can see that this visualization can be plotted for 1 hour, 6 hours, 1 day, and more. Let's scroll down. Here is information needed to connect to this instance. So we see the public IP address as well as the connection name. Let's skip over some of the more advanced information here and click on the tab on the left, System Insights. Please note that this menu only applies to the primary instance. So Cloud SQL Studio, System Insights, users, databases, all of these relate to our current primary instance. We click through into System Insights, and here we can get information about an events timeline, metrics of utilization of different resources, and data transfer in and out. Let's move on to the next tab over on the left, which is Connections. Here we get relevant information, some of which we've already seen. Right up top we have the connection name. Notice how that is a concatenation of the project ID, the region, and our instance ID. We see the public IP address, and we can also see that private IP connectivity has been disabled and public IP connectivity has been enabled. All of this is in the Summary tab. We can also explore the other tabs. For instance, in the Networking section, we have options for instance IP assignment. Notice how public IP is currently checked. Scrolling down, this is also where we can authorize specific networks or CIDR ranges to access our instance. Let's click through into Security. This is where we manage the SSL mode, and you can see that we've currently allowed unencrypted traffic, and we are also warned that this is not recommended. The other options are allow only SSL connections or require trusted client certificates. There's nothing else particularly interesting here in the connectivity test section. So we now go back to the pane over on the left and click on users. This is where we can add users, that is user accounts, that can connect to our instance. Right now we have just one, and that's the root. But we can also click on that blue button to add additional user accounts. So that's what we do. Now we can see here that there are two choices. There's the MySQL built-in authentication, and then down below we can also go with Cloud IAM. For now we'll be focused on the built-in authentication bit, but Cloud IAM is how you could associate an IAM principal with this user account. IAM is short for Identity and Access Management, and that's the way in which we implement a role-based access control on the Google Cloud. For our simple use case here, built-in authentication is fine. We are prompted for the username. We go with Looney Cloud User. Then we've got to specify a password. This has to be consistent with our password policy. We could also restrict this user to only access our instance from specific hosts. Here we've gone with the allow any host option. We click add, and this new user, Looney Cloud User, gets added to the list of usernames. We can also administer this user by clicking on those three vertical dots over on the right. In the menu which opens up, we can change password, edit password policy, or remove this user. The next order of business is to actually add some data to our Cloud SQL instance. So we click on Databases over on the left, and here we see a list of the databases on our server. Because MySQL is our choice of database engine, we have the usual pre-built databases: Information Schema, MySQL, Performance Schema, and SYS. Let's create a new database in which we will create a table and load some data. So we click on that Create Database button, and over on the top right, we enter the database name as Laptop Price DB. We can go with the default choices of character set and collation. So we simply click Create, and this database gets added to the list. There it is, below Information Schema. Before we connect to this database and start placing some data in it, let's quickly explore some of the remaining functionality. Here we've now clicked on Backups, and we are taken to a page where we can create a backup, and notice that button at the center of the screen. We also have information about automated backups, which are enabled, point-in-time recovery also enabled, configuration information about these two features, and then down below something really interesting. That is a list of backups, and we have one backup. As the description tells us, this was automatically created after the instance was created with PITR enabled. PITR is point-in-time recovery. There's also a restore button over on the right. So we can always restore our data to any specific point in time. Next, let's click on the Replicas tab over on the left. This takes us to a page where we can create a read replica. Again, there's a button in the center of the screen. No replicas have been created yet, however. We can also quickly explore the Operations tab. Here we can see a log of operations on our database, starting from when the database was created and all the subsequent operations. Let's now head back to the Overview section. We are going to connect to Cloud Shell and start working with our database instance. In the previous demo, we viewed the instance information of our MySQL server, and we created a user and a database. Now let's actually start working with it. We'll do this by clicking on the Activate Cloud Shell button over on the top right. Let's quickly go through the usual process where we open up Cloud Shell in a new window to get some additional screen real estate and then set the active project. We do this by running the usual gcloud config set project command with the project name. Next, we will use gcloud in order to work with our MySQL instance. Now, this marks a change when contrasted with BigQuery or Google Cloud Storage. Those tools both had their own command line utility. So for instance, while working with cloud storage buckets, we used gsutil. While working with BigQuery, we made use of bqueue. But for Cloud SQL, we will just use gcloud, and that will always be followed by the word SQL. The first command that we wish to run is visible on screen now, gcloud SQL connect. That's followed by our instance name, that's Looney MySQL instance. Then we have the user flag -- user, which is equal to Looney Cloud user. And then at the very end, we have the -- quiet. The quiet flag is required because we'd like to run this command in non-interactive mode. We do not want any prompts to be sent to us. So we go ahead and hit enter, but to our surprise, the command fails. We get an error, permission denied. The error tells us that the Cloud SQL admin API has not been used in this project, Looney GCP CDL previously, or it has been disabled. The message also tells us how we can enable it. It's got the URL in there, and then it has some more additional information. Before we enable this API, let's understand what caused this error. When we use tools like gcloud, or for that matter gsutil or bqueue, those tools are making REST API calls to the underlying service. So here, for instance, gcloud is attempting to invoke some REST APIs of Cloud SQL. Those APIs are not enabled by default, and that is for reasons of security. These APIs are known as the admin APIs. Here, because it's a Cloud SQL API that we are attempting to use, the error message tells us to enable the Cloud SQL admin API. With this context in mind, let's switch back over to the Cloud Console. In the search bar over up top, let's just type in Cloud SQL admin API, and this is then easy enough for us to enable. Click through on the first and most relevant hit. That takes us to the Cloud SQL admin API page, and there's a big blue enable button there, which we go ahead and click. Doing this takes us into a details page. Up top, we are warned that in order to use this API, we might need credentials. There's also a button over on the right to create those credentials, but we don't actually need them because we will be accessing this API through gcloud. What's more, that gcloud is being run from Cloud Shell, which is already authenticated. Now we can switch back to Cloud Shell and try the same command. This time it runs through successfully. Along the way, we are prompted for our password. Just to be clear, this is the password for Looney Cloud user. And also please keep in mind that Looney Cloud user was set up using MySQL built-in authentication. So this is not a Google Cloud user, it's a MySQL user. We enter that password successfully, and pretty quickly we find ourselves at a very familiar MySQL prompt. Let's put this database through its paces. Let's start with the usual show databases command. As expected, we have 5 rows in the result. 4 of these are the pre-built MySQL databases, and one of these is laptop price DB, which is what we had added. Everything seems to be in order here, so let's exit this MySQL prompt for now and go back to Cloud Shell. Let's also explore the help facility on gcloud SQL. Here we've typed gcloud SQL instances -- help, and as the result tells us, this gives us commands for managing Cloud SQL instances. We can also run more advanced administration commands using gcloud. Here, for instance, we've run gcloud SQL instances patch -- help. As the output tells us, we can use this in order to update the settings of a particular gcloud SQL instance. Now let's say, for instance, that for cost management reasons, you'd like to keep your Cloud SQL instance in a stopped state until you manually and explicitly decide to restart it. The way to do this would be by setting the activation policy to never, and that is something that we can do right here using gcloud. The command that's visible here is gcloud SQL instances patch, that's followed by the instance ID Looney SQL instance, and then we have the activation policy of never. Let's run this command through. It seems to go through successfully, and now after this, if we switch back over to the web console and click on all instances, there we will find that our instance looks like it's being updated, and a moment later the status changes to stopped as the tooltip tells us. We can confirm that by clicking through, where right up top we see the warning telling us that this instance is stopped, We can start it if we'd like to allow connections and other operations. There's a start button to the right as well as on top. Let's click the one on top. We are asked to confirm that we would like to start our database instance. As the fine print tells us, starting the instance will allow connections and operations. Also, the activation policy will be set to always. That's the exact opposite of an activation policy of never. It means that the server will keep running until we manually stop it. We give our confirmation, and at the bottom right, we see that the instance has been started again. We now have a green checkbox next to the instance ID, and we can also confirm that by clicking through into all instances. In the instance list, we have a green checkbox here as well, and when we hover over it, we again see that the instance is runnable. Let's again connect to our database. We again run gcloud SQL Connect with the instance ID. It's the same user and we have the quiet flag. We are prompted for the password. We enter it and find ourselves back at the familiar MySQL prompt. We'll now go into a quick series of query and update operations. We run show databases and confirm that the databases are online, including the laptop price DB. Let's set that as the active database with the use command, so that we don't need to include the database name in every query. The database has been changed. Let's run system clear to free up some screen real estate and then create a table. This is a table called laptop price. This runs through successfully. We won't go into the details of the SQL syntax because this is all pretty standard. Then let's start inserting data into our laptop price table. Here we've inserted one single row with an insert into command. Everything is working fine, so in quick succession we run many more insert statements. Each inserts just one row into the same table laptop price. By the end of this process, we've inserted 5 rows. We can confirm that by running select star from laptop price. The query runs through successfully and returns 5 rows, as we can see there at the center left. Let's run a few more simple queries, this one with a where clause, and then let's perform an update operation. On screen now, we've updated laptop price and set OS to be Windows 11 OS, where the brand is Lenovo. This runs through fine and we can see that one row has been affected. And that gets us to the end of this demo, in which we were successfully able to work with our Cloud SQL Server instance using gcloud. We used it to change the activation policy as well as to log into the server and run queries and update operations. In the previous demo, we made use of gcloud to connect to our MySQL Server instance from the command line, and that's quite good as far as it goes, but you might want a more user-friendly interface. If you are working with MySQL on an on-prem system, for instance, maybe you are used to using SQL Workbench. Now, there's no need to make use of a third-party tool like MySQL Workbench because Google Cloud has added a new tool called Cloud SQL Studio. So we switch back to the Cloud Console. Here we are looking at the overview of our Looney MySQL instance. Over on the left, you can see that we have Cloud SQL Studio as one of the options. Let's click on that. We are prompted for the database username and password. So this is a pretty user-friendly way to access our instance. Also notice right up top on the left, we are connecting to the Looney MySQL instance. Let's enter these details. There's a drop down for the database. We choose laptop price DB and then enter the username, that's Looney Cloud User, as well as the corresponding password. We hit authenticate and Google Cloud SQL Studio opens up. Over on the left, we have an Explorer view. So we have the database, there's just one, that's laptop price DB, within which we have the tables, again, just one laptop price. We also have all of the other relevant information such as the views, events, functions, and procedures. Lower down, we can also see the system-built databases such as information schema and so on. We are currently on the welcome screen. We can take a quick tour or just open up a new SQL editor tab by clicking on that button. Alternatively, we can just click on the Open Editor 1 tab right up above. That's pretty much all there is to it. We can now start running our queries. Here we've set use laptop price DB so that becomes the default database. Then let's run a simple query against our table. Select star from laptop price. Once again, we hit run and all of the data appears down below. Cloud SQL Studio is a relatively recently launched product. It launched in March 2022. One of the great benefits of Cloud SQL Studio is that it presents a uniform interface for any of the database engines supported on Cloud SQL. So you can make use of this same UI whether you are working with MySQL, Postgres, or SQL Server. That does it for our very quick look at Cloud SQL Studio. It's now time for us to delete our instance. We click on all instances over on the top left. This takes us back to the list of instances. We can see that Looney MySQL instance is currently runnable. We get that by hovering over the name and also from the green checkbox next to the instance name. To delete this, we can click on the three vertical dots over on the right. When we do that, a menu opens up, but to our surprise, the delete option is grayed out. Why is that? Well, let's find out. We just hover over it. The tooltip tells us that we can't delete this instance because deletion protection is enabled. You might recall that this is a feature that we had turned on while provisioning our instance. In order to delete this instance, we will have to edit the instance and explicitly disable deletion protection first. You can see that this is editable in the data protection section. That's a very clear set of instructions, so let's click on edit. Luckily, it's in the same menu. This takes us to the instance information. We scroll down until we get to the data protection section. We expand it, and then we scroll past the automate daily backups and the enable point-in-time recovery, and the last checkbox is enable data protection. So we uncheck that box, and that's all there is to it. Let's scroll down and save the changes to the instance information. This causes a pop-up to appear on the bottom left. When we close this, we are taken to the instance information, and another pop-up opens up on the bottom right. That confirms that changes are being made, that is, we are editing our instance. There's also an informational message displayed up above. Instance is being updated. This may take a few minutes. Let's click through into all instances, and we can see again that the status shows as instance is being updated. A little while later, the edit goes through successfully. We can see that from the green checkbox over on the bottom right. We now click back into all instances, and our instance is back to a runnable state. We know that from the green checkbox next to the instance ID. At this point, if we again click on the three vertical dots over on the right, this time the delete option is enabled. We go ahead and click on it. Of course, deleting a server instance is a major operation, so we are asked to confirm our intent. We've got to explicitly type out the instance ID, and we are also warned that this operation cannot be undone. We click delete and we get a status update over on the bottom right. It takes a long time. You can see here it took 27 minutes and 9 seconds in order for our Cloud SQL instance to be deleted. The main home page of Cloud SQL also changes. It recognizes that we do not have any instances, and that's why it shows that bright blue create instance button. This is where we had begun our exploration of Cloud SQL, and this is where we also wrap it up. We are done with our discussion of Cloud SQL, and before we turn to Cloud Spanner, we'll take a brief segue to discuss AlloyDB. This is a fairly recently launched offering on the Google Cloud Platform. It went into general availability in October of 2023. AlloyDB for PostgreSQL is a fully managed PostgreSQL compatible database service which is optimized for demanding workloads including hybrid transactional and analytical use cases. The key here is that it is PostgreSQL compatible. Under the hood, it makes use of a Google proprietary design from a Google internal product called F1. So applications will connect to AlloyDB instances using standard Postgres protocols and write usual Postgres queries. Under the hood, however, something different is going on, and that's why AlloyDB claims to be orders of magnitude faster than Postgres. You ought to consider AlloyDB for applications that need high availability, low latency, and the ability to handle complex queries and large datasets. That last attribute, handling of complex queries and large datasets, is typically thought of as the property of a data warehouse. So in effect, AlloyDB is combining some of the use cases of an RDBMS and a data warehouse. Let's take a quick look at the architecture of AlloyDB. As you can see, our application, which sits at the top left, just performs its usual SQL reads and its SQL reads and writes. Under the hood, however, you can see that read and write operations may be directed to the primary instance. There are also SQL reads directed to read pool instances, which effectively give load-balanced multi-zone data access. The read pool instances connect into read-only nodes. However, writes go through to the primary instance, which has high availability and supports both read and write access. You can also see that the primary instance is an abstraction of the active node as well as a standby node. That's where the high availability comes from, because there is a failover replica. Down below we have the storage layer, and taken all together we can see from this that AlloyDB has a multi-node architecture. Also note that a single AlloyDB deployment is called a cluster. This is a regional product, so all of these resources will exist within one Google Cloud region. The cluster contains several nodes, each of which is a VM instance running the PostgreSQL compatible database engine. Also, note that nodes are organized into instances, and each instance has a private static IP address in your VPC. That's the virtual public cloud. Right now, we are focused on the primary instance. Every cluster will have exactly one primary instance which gives read and write access to the data. Now, the primary instance could be highly available or it could be basic. If we turn on the high availability configuration, then we'll effectively have two nodes within that instance, an active node and a standby node. AlloyDB will monitor the availability of the active node and automatically promote the standby into active mode when necessary. Optionally, our AlloyDB cluster could also have one or more read pool instances. Each of these read pool instances will contain one or more read-only nodes. Again, please remember that instances can contain multiple nodes. Also notice how each instance independently can accept client requests. Within a particular instance, AlloyDB will automatically load balance all requests and route them to the appropriate nodes within that instance. There is a cluster-wide maximum of 20 read-only nodes. Beneath all of this compute sits the storage layer. That storage layer makes use of a cloud-based file system designed by Google, so it's proprietary and optimized specifically for AlloyDB. For the simplest use case, you could have just the primary instance and no read pools. Then all applications would use only the primary instance for all queries, whether they are read or write. As your payload increases in size and complexity, you can add read pool instances to the cluster, and then you can configure the different apps which connect to the cluster in order to hit the different read pools. And in that way, you'll reduce the load on your primary instance, and you can also distribute the load across the different read pool instances. Let's talk about some of the characteristics of AlloyDB. This is a high performance service. It's optimized for high performance and promises significantly faster processing than standard Postgres. It does this by making use of Google's infrastructure and the multi-node design that we just discussed. In this way, it supports complex analytical queries, and it also has an enhanced query optimizer and execution engine to back those up. As a result, it claims to handle both transactional and analytical workloads, which is why it's set to support hybrid use cases. AlloyDB supports both horizontal and vertical scaling. Users can adjust resources based on their workload requirements. For instance, you can add read pool instances as you go along. And in this, it differs from Cloud SQL, which only supports vertical scaling. A big plus of AlloyDB is its compatibility with PostgreSQL. This allows existing users to migrate with minimal changes in terms of their tools and frameworks, and it makes AlloyDB a less intimidating product for first-time users than Cloud Spanner. AlloyDB supports high availability configurations with the automated failover and replication. AlloyDB has been designed keeping security in mind, so it uses data encryption at rest and in transit, role-based access control, and it integrates tightly with Google Cloud's identity and access management module. Let's now turn our attention to another important product, that's Cloud Spanner for transactional data. In terms of our taxonomy, remember that Cloud Spanner comes in handy when we are working with highly structured data, when we want SQL access to that data, and when it's transaction processing rather than analytical processing that is our primary use case. Cloud Spanner has something of a special place in the GCP suite of offerings. It's a global, horizontally scaling, and strongly consistent relational database. The global is important because the other RDBMS offerings such as Cloud SQL and Alloy DB are regional. It offers horizontal scaling, which Cloud SQL does not support, and it's also strongly consistent. It achieves all of this with a proprietary architecture. Now, if you stop to think about it, it's actually quite a big deal for any product to offer both global access as well as strong consistency. As we've already discussed with Cloud SQL, the synchronous replication causes some slight latency, and that's within a region. So Google and the Cloud Spanner folks are justifiably proud at being able to offer very strong consistency guarantees despite global replication. It is for this reason that while Cloud SQL offers ACID support, Cloud Spanner goes one step beyond. It offers ACID support even for highly distributed data. Remember that Cloud SQL is not distributed, all of the data resides in the persistent disk of the Cloud SQL VM instance. Cloud SQL is a regional offering, while Cloud Spanner is global in reach. This means that you can add nodes and access from across regions. On the topic of adding nodes, Cloud SQL scales vertically, but Cloud Spanner can scale horizontally as well. Because of its distributed architecture, all you need to do is add nodes. We've already discussed how Cloud SQL is suitable for smaller workloads. That's not true of Cloud Spanner. It scales to pretty much any size or level of queries per second. Cloud SQL supports MySQL, Postgres, and SQL Server. Cloud Spanner is Google proprietary. Now, of course, there is literally no free lunch, so Cloud SQL is relatively cheap and Cloud Spanner is relatively expensive. Let's make sure that we understand the difference between vertical and horizontal scaling. In both cases, as the size of our data and processing needs grows, we want to have greater compute and storage capacity. The differences arise in how we achieve these end objectives. In vertical scaling, we add capacity by making an individual server more powerful. In the context of Cloud SQL, you can imagine that we have one VM instance, and then as our needs grow, we effectively scale up to a more powerful type of VM instance. This over time leads to the need for very expensive and proprietary hardware. Horizontal scaling, on the other hand, just adds more generic servers, each of which might run cheap hardware and software, but taken all together, this system can scale a lot more. Cloud Spanner, unlike many traditional RDBMSs, offers horizontal scaling as well. Horizontal scaling brings up the question of consistency. Let's say a write occurs to one of these servers. There has to be some internal system to make sure that that write is propagated to all of the others. Otherwise, the data across these different servers will get out of sync. Depending on how that is achieved, the service might provide different levels of consistency guarantees. We had previously mentioned that Cloud Spanner offers ACID++ support, and that comes down to some of the consistency guarantees that it makes. Before we talk about external consistency, which is what Cloud Spanner offers, it's worthwhile for us to understand the two more common types of consistency, strong and eventual. With strong consistency, when an update request comes in, all of the replicas of that particular data item are going to be updated before the request can return. So if for any reason one of those replicas is offline and cannot be updated, well then the update request is deemed to have failed and none of the other replicas will be updated either. With eventual consistency, this is not the case. An update request comes in, a primary replica is updated immediately, and then the request returns as successful. All the other replicas will only be updated later. If some of those other replicas happen to be down or are not successfully updated, then that leads to a problem because the data within the system is now out of sync. However, there are complex commit protocols to make sure that all of those replicas eventually do get updated. Cloud Spanner goes one step beyond. It offers something stronger than either of these. It offers external consistency. Cloud Spanner scales horizontally, which means that transactions are going to be executed on multiple servers in a distributed fashion. The important point is that Cloud Spanner is able to architect all of these transactions as if they were executed sequentially. This serial order is consistent with the order in which the transactions are observed to be committed. Taken altogether, this means that Cloud Spanner is indistinguishable semantically from a single machine database. The technical details of each of these different forms of consistency can get a little confusing, but it's worth remembering that external consistency is a stricter guarantee than strong consistency. By this point, we have a good sense of the strengths and weaknesses of Cloud Spanner and Cloud SQL. Cloud Spanner provides horizontal scalability across multiple regions, and thus it is a globally distributed database. It also has very strong consistency guarantees and low latency access. Cloud SQL is primarily designed for single region deployments. It has very limited horizontal scalability and is best suited for smaller scale applications that do not need global distribution. Cloud Spanner offers higher availability SLAs than Cloud SQL because it also has automatic replication across multiple zones as well as regions. The architecture has built-in fault tolerance even in the case of regional outages. Cloud SQL, on the other hand, has a high availability configuration mode which will provide automatic failover within a single region. Cloud Spanner offers stronger consistency guarantees and it does so at scale. Because it's able to provide these guarantees across distributed nodes while maintaining ACID++ properties and synchronizing data globally, it's ideal for applications that need consistent reads and writes across multiple regions. Cloud SQL is more limited. It has strong consistency within a single region, but it does not have global consistency capabilities. Both of these services integrate with other GCP products. However, Cloud Spanner has greater integrations with advanced features such as advanced analytics, AI ML, and real-time data processing. Finally, Cloud Spanner has something known as managed schema changes. This means that Spanner will allow online schema changes without downtime. Applications can evolve without service disruption. Cloud SQL does not offer this same facility. While schema modifications can of course be made, they are unlikely to be as seamless or instantaneous as those in Spanner, and typically they will be associated with some downtime or performance degradation. We started this course off by exploring storage options for structured data, focusing on the features of Cloud SQL. We learned how to provision a Cloud SQL instance, gaining hands-on experience in setting up this managed database service. We then moved on to administering a Cloud SQL instance, covering essential tasks such as managing users, configuring settings, and ensuring security. Finally, we connected to a Cloud SQL instance using various tools and methods, enabling seamless interaction with the database. Next, we learned about the high availability configuration for Cloud SQL, which is crucial for ensuring continuous operation and reliability. We discussed the benefits of choosing Cloud SQL for different use cases, emphasizing its scalability and integration with other Google Cloud services. Additionally, we explored Google Cloud SQL Studio, a web-based interface that simplifies database management tasks, providing an intuitive platform for executing queries, managing instances, and monitoring performance. Finally, we explored advanced database solutions, starting with an introduction to AlloyDB, a fully managed PostgreSQL-compatible database service designed for high performance and scalability. We also learned about Cloud Spanner, which is ideal for transactional data, offering global consistency and horizontal scalability. In conclusion, we have built a solid foundation in managing structured data using Cloud SQL, AlloyDB, and Cloud Spanner on the Google Cloud. We are ready to move on to the next course in this journey, Enterprise Data Warehouses on the Google Cloud. Managing large-scale analytics and diverse data types is essential for organizations to derive valuable insights and optimize performance. Leveraging Google Cloud solutions like BigQuery, Bigtable, Firestore, and Looker enables businesses to efficiently handle analytical and semi-structured data while gaining powerful business intelligence through interactive dashboards and reports. In this course, you will learn how to leverage BigQuery for large-scale analytics, focusing on managing and analyzing extensive datasets efficiently. You will explore Bigtable for semi-structured data, emphasizing its scalability and performance, and Firestore for its real-time capabilities and ease of use. Next, you will learn how to choose the right storage solution for structured data by considering factors such as data volume, access patterns, and performance requirements. You will discuss the process of migrating databases to the cloud and explore best practices for a smooth transition. Additionally, you will learn how to derive business intelligence and insights using Looker, which offers interactive dashboards and reports. Finally, you will learn some practical aspects of managing data in BigQuery, including creating datasets and tables, running queries, and optimizing data management. You will use Looker Studio to visualize data and practice command line operations using the BQ tool, enhancing your ability to manage BigQuery resources programmatically. This course will provide you with a strong foundation in utilizing Google Cloud's data solutions for enterprise data warehousing needs. It's now time for us to turn to one of the most powerful, easy to use, and popular offerings on the Google Cloud platform, and that's BigQuery. BigQuery is the enterprise data warehouse offering, which means that it is perfect for working with highly structured data where you would like a SQL interface and where your use cases relate to analytical processing rather than transaction support. BigQuery is a fully managed serverless enterprise data warehouse. It can deal with data on the order of terabytes and petabytes worth quickly and efficiently. The serverless architecture makes it easy to manage the infrastructure, and it allows users to focus on data analysis rather than on maintenance. You can use standard SQL queries on BigQuery, which makes it very easy to use. In addition, it integrates very tightly with other GCP offerings such as Dataflow, Dataproc, and the AI ML tools. It also has some built in ML capabilities which allow users to create and deploy ML models directly from within BigQuery. Finally, data is always encrypted in BigQuery, and it also works in multi cloud environments. Because of its popularity over the years, there's a great ecosystem of partner tools. One of the key aspects of the design of BigQuery is the decoupling between storage and compute. Let's quickly talk about each of these in turn. It makes use of a columnar storage format which effectively compresses the data, and that leads to good, fast retrieval and great query performance even on large datasets. In addition, it also supports semi structured data, including JSON and Avro formats. In addition to the core compute functionality required for standard SQL queries, BigQuery also integrates with various other analytics tools such as Google Data Studio, Looker, and a host of third party tools. It has built in support for geospatial analytics and also has a feature known as BigQuery ML, which allows you to create and deploy ML models directly from within BQ. Next, let's talk about some of the characteristics of BigQuery. The first and maybe the most important is that it's fully managed and serverless. So when you use BigQuery, you don't provision an instance or a cluster. All of this makes it very easy to use. You just focus on querying and analyzing the data. The serverless architecture allows for automatic scaling based on the workload. Autoscaling has a couple of important attractions. For one, performance remains consistent even during peak workloads. Also, it helps with cost management because you only pay for the resources that you actually use. At the heart of autoscaling is the automatic behind the scenes provisioning or deprovisioning of compute resources. Remember that compute and storage are decoupled, and here the autoscaling is referring to the compute resources. BigQuery provides high availability right out of the box. This is different, say, from Cloud SQL, where you might have a single instance or a high availability configuration. There's no such provisioning or configuration required with BigQuery. Here, there's built in high availability. The data is automatically replicated across multiple locations and protected against even regional failures. BigQuery works and scales effortlessly even to petabyte scale data. The internals of this are out of scope right now, but they come down to the use of massively parallel processing and the columnar storage, which we already discussed. ML capabilities are integrated right into BigQuery. The feature BigQuery ML allows users to create and execute ML models directly from within BQ using SQL. BigQuery ML supports a fairly wide variety of models, including linear and logistic regression and k-means clustering. BigQuery also has support for real-time data ingestion and analysis. This is important because it allows BigQuery to work with other streaming services on the GCP such as PubSub and Dataflow. This point is worth emphasizing. BigQuery is not suitable only for batch processing, it also works fine with streaming applications. You've quite likely heard of the three V's of big data. Google is justifiably proud that BigQuery actually supports the four V's. These are volume, variety, velocity, and variability. We've discussed BigQuery's ability to deal with petabyte scale data already, so that allows it to process any volume of data. It also can deal with a wide variety of data sources. Federated data sources are data sources which are not native to BigQuery. These include data which is in Google Cloud Storage, Bigtable, Google Drive spreadsheets, and so on. You might remember that we had discussed the concept of a data lake house, which combines the benefits of a database, a data warehouse, and a data lake. Here, through federated tables, BigQuery is able to provide support for the lakehouse architecture because unstructured data or semi-structured data, which is on Google Cloud Storage, is going to be accessible directly from within BigQuery, even though the underlying data has not been converted into BigQuery's native file format. Support for high velocity data comes through BQ support for streaming ingestion as well as real time queries. This way, users can ingest data continuously into BigQuery via PubSub and Dataflow and feed that data into real time analysis of the incoming data. It's important to note that streaming data that is ingested via PubSub and Dataflow will automatically reflect in BigQuery query outputs. That means that BigQuery is also a good choice of technology for use cases such as monitoring, fraud detection, and dynamic pricing, all of which rely on real time interventions. The fourth V here refers to data variability. BigQuery purportedly addresses variability through schema auto detection. When you're loading data into BigQuery, it will automatically infer the schema based on the data that's being ingested. This makes it much easier and simpler to read data in from diverse data formats and structures. Users do not need to manually define the schema for each dataset that's being ingested. This might not sound like a very big deal, but when you consider an enterprise data warehouse with a large number of data sources feeding into the data warehouse, this can save a lot of work. Remember that BigQuery is a SQL-based technology. BigQuery supports two dialects of SQL, Google SQL and Legacy SQL. Google SQL is compliant with Standard SQL 2011, but it also includes some extensions to deal with special cases such as geospatial analysis, ML, and nested and repeated fields. Legacy SQL is primarily for backward compatibility. In order for us to get the best out of BigQuery, it makes sense for us to understand some of the elements of its architecture. As you can see here, BigQuery under the hood includes two decoupled modules. It has replicated distributed storage and then a highly available compute cluster. You can see that each one of these relies on horizontal scaling. Way over on the left, you can see that both batch and streaming ingestion are possible. Between the decoupled storage and compute, there is a petabit network which allows extremely fast communication. Again, it's important to note that storage and compute scale independently. So if your datasets grow in size, but you aren't running any more intensive queries, you will pay a little more on the storage, but you will not incur any additional billing on account of the compute. Likewise, if your datasets are relatively small, but you run extremely intensive and complex queries on them, you'll pay for the compute, but not so much for the storage. As a flagship enterprise data warehouse tool, BigQuery supports a wide range of analytic workflows. These include ad hoc analysis, for which you can make use of standard SQL or some of the additional features available in Google SQL. You could also make use of any one of the numerous third-party tools that integrate with BigQuery. You can also use BigQuery for geospatial analysis. It has geographical data types, and the Google SQL dialect also has additional extensions for such purposes. BigQuery ML is a feature of BigQuery. Here you can use queries, that is SQL queries, to create and execute simple ML models right from within BigQuery. And finally, business intelligence, which of course is one of the core use cases. BigQuery has a feature known as BigQuery BI Engine, which is a fast in memory analysis service that can help you build dashboards right here within BigQuery, or you can also make use of Looker or other third party BI tools. Let's take a minute to talk about BigQuery ML. The first and most important feature of BigQuery ML is that it allows users to create ML models using standard SQL queries. This has the effect of democratizing machine learning access because now folks need not know Python or a programming language in order to build ML models. BigQuery ML supports quite a wide range of ML models. These include linear and logistic regression and k-means clustering, as well as some deep neural networks. It's also important to note that BigQuery ML integrates tightly with Vertex AI. That's Google Cloud's comprehensive ML platform. This tight integration allows users to make use of all of the advanced capabilities from within Vertex AI, such as AutoML, hyperparameter tuning, and model deployment, all from within the BigQuery environment. So, for instance, it's possible for users to train and fine tune models in Vertex AI and then execute them in BigQuery ML for inference. This creates a smooth and efficient workflow. Finally, BigQuery ML also supports real time predictions. The way this would have to be achieved is by streaming data into BigQuery and then performing real time scoring with a machine learning model that's used for inference. This way, the predictions will always be based on the latest information. Effectively, this combines the power of BigQuery ML with real time querying and streaming ingestion. Next, let's understand the BigQuery data model. Datasets roughly correspond to databases in an RDBMS world. So, a dataset can be thought of as a logical collection of tables. Tables and views have very similar meanings in BigQuery to their equivalents in the RDBMS world. We'll talk about these in more detail in just a bit. First, let's just understand the resource hierarchy in BigQuery. Right up top in this hierarchy, you see an organization. Here, organization is a resource. Every Google Workspace or Cloud Identity account has to be associated with an organization resource. When an organization resource exists, it's the top of the hierarchy. Within an organization, we have folders which can be used to logically group other resources. The organization also has to be associated with one or more billing accounts. You can think of a project as a container for billable resources, and that in turn means that a project has to be associated with a billing account. In this diagram, we've shown projects as being contained within an organization resource. Just to be clear, you actually could have a project which is not associated with an organization, but that's only possible if it's a free trial user or a free tier user. In any case, within the project, we actually get to the resources, which in this instance are BigQuery resources. These might include datasets, tables, views, and models. A BigQuery dataset is a top-level container which holds collections of tables and views. It can also hold an ML model, as you can see for the dataset in the middle. Datasets help to manage access control and permissions, so you grant users and groups specific rights at the level of the dataset. Each dataset is associated with a specific project and is identified by a unique name within that project. Again, datasets serve as a logical grouping for data, and this structure supports data governance and simplifies the administration of resources. A table in BigQuery is quite similar to a table in the RDBMS world. Each table is a structured collection of data. It consists of data in rows and columns. The columns have specific data types such as string, integer, and float. There's no limit to how much data a table can hold. BigQuery supports a few different table types, including native tables, external tables, which reference data stored outside of BigQuery, partition tables, which improve performance and manageability for very large datasets, and in general, tables are the primary entities that you use for storing and querying, similar to how you'd work with an RDBMS. Views in BigQuery are virtual tables. They are defined by SQL queries. Again, this is very similar to a view in the RDBMS world. BigQuery supports both materialized and non-materialized views. The non-materialized views are by far the more common. A materialized view is actually going to store the query results physically. This improves the performance if the query is going to be run very frequently. In the much more common variant, the views are not materialized, which means that there is no physical underlying storage of the query result, Whenever a view is queried, BigQuery effectively is going to execute the underlying SQL query and present the results as if they were in a table. Views help with simplifying query logic, they promote code reuse, and they can also be used as a way to enhance security by allowing users to only access specific parts of the data. This, of course, requires the correct access control to be set up at the dataset level. Putting all of this together, when would we choose BigQuery? One common use case is when you need powerful analytics and querying capabilities. BigQuery supports extremely complex queries and it allows you to run large scale SQL queries on massive datasets. It's specifically optimized for analytical queries and can handle windowing and other complex aggregations. That, of course, is the whole point of an enterprise data warehouse, which is what BigQuery is. This makes it preferable in such cases over other storage services like cloud storage or Bigtable, which are more focused on object or wide column data storage, respectively. BigQuery is also an excellent choice when you need a solution that is serverless and fully managed. There's no need for infrastructure management at all. Unlike other GCP storage services that might require provisioning and managing compute resources, BigQuery will automatically handle the scaling, performance tuning, and the maintenance. This is an extremely attractive feature of BigQuery. You might want to consider BigQuery when you need seamless integration with ML. As already discussed, BQML has built-in support for machine learning, and in addition, it also integrates tightly with Vertex AI, allowing you to leverage all of the advanced AI and ML capabilities on the Google Cloud Platform. Finally, you also should seriously consider BigQuery when you need high availability and real-time data processing. For instance, for the ingestion of streaming data. This last use case is one that people tend to think of a little less often than the others, but it's worth keeping in mind that BigQuery offers automatic high availability as well as real time data ingestion and querying. You can set up an architecture where data from an event source, so this is streaming data, is piped into BigQuery using a combination of pub, sub, and data flow, and you can then leverage all of the powerful features of BigQuery. Taken all together, you can now see why BigQuery is such a powerful and attractive service. It's now time for us to turn to Bigtable, which is a great solution for specific types of use cases involving semi structured data. Bigtable is a NoSQL technology, and in that sense, it's similar to Firestore. However, Bigtable and Firestore have very different use cases. Firestore is a document database suitable for working with documents in JSON, XML, HTML, and so on. Bigtable has very specific niche use cases, which we shall discuss in detail. Bigtable really comes into its own when you're dealing with very large, sparse datasets with sequential ordering in a key column. So, when all of these conditions are satisfied, that is, your dataset is very large, when it's sparse, which means that not all fields are present in all rows or all records, when there is a specific and natural key column, and when the data is ordered on that key column, then Bigtable should be your technology of choice. For such use cases, it gives very fast reads and writes. Remember that data warehouses like BigQuery do not support very fast writes, and relational databases such as Cloud Spanner are not great for sparse datasets because the relations will end up containing a lot of null values. So, again, in these specific niche use cases, Bigtable is the best option. Let's talk about some characteristics of Bigtable. As we just discussed, it offers high performance and low latency. This makes it ideal for use cases that need fast reads and writes. It can handle millions of requests per second and provide consistent and fast access to data. This performance is achieved using a distributed architecture and comes in handy when working with real time analytics, personalized content recommendations, and time series data. Bigtable is highly scalable. It can work with petabytes of data across thousands of servers. It allows for seamless scaling both horizontally and vertically. Bigtable is not serverless. It does have a cluster, which is effectively a server, but it supports auto scaling, which means that it will add nodes to a cluster when the workload changes. Bigtable provides a flexible, sparse, and schemaless data model. It makes use of a wide column format, which means that each row can have a different number of columns, and columns can be added or removed on the fly. These attributes make it a lot easier to make use of semi-structured data when working with BigQuery as compared to an RDBMS. Even at such high scales of data, Bigtable provides strong consistency and availability SLAs. It has strong consistency for both read and write operations and ensures that data is always up to date and accurate despite the replication across multiple locations. That replication provides the high availability and durability. So, Bigtable is suitable for mission critical applications where data integrity and uptime are very important. Finally, and somewhat expectedly, Bigtable integrates seamlessly with other Google Cloud services such as Dataproc, BigQuery, and Dataflow. In addition, Bigtable also supports the HBase API. The Bigtable storage model is quite different from that of a relational database, although it might seem familiar to you if you worked with other wide column technologies like HBase. Four concepts worth keeping in mind are a row key, column family, column, and finally a timestamp. On screen now, you see the storage model for one row or one record in Bigtable. We have a row key which uniquely identifies this particular record. Then we have various columns or field values. Those can be grouped together into column families. For each of the individual columns, we've got a combination of value and timestamp pairs. You should keep in mind that Bigtable is optimized for dictionary style reads, i.e., where you give Bigtable the row key and you ask for all of the other record values. This data model also explains why updates and writes in Bigtable are so fast. When an update or a write comes in, Bigtable will not bother to delete the old data. All it'll do is add a new version of the data, that is, it'll add the new value and the timestamp. From time to time, it will run a compaction job to delete all of the extraneous or old timestamps and values. Because Bigtable maintains this timestamp information, it's said to support versioned data. Also notice how Bigtable works well with sparse data. If the cell does not have a particular value for a field, that storage is not allocated at all. All of the cell values are stored sequentially, which means that all information for one record can be accessed extremely quickly given the row key. Cell values that are no longer required will be periodically deleted. This is a process known as compaction. Next, let's take a moment to understand the architecture of Bigtable. Bigtable is not serverless, so we've got to provision a Bigtable instance. Under the hood, that Bigtable instance includes a cluster of nodes as well as some file system storage using a very highly optimized file system called Colossus. Client applications are abstracted away from all of this, they only interact with the front end server pool. This abstraction comes in handy because Bigtable supports auto scaling. When the workload increases, Bigtable will automatically provision additional compute and add that as additional nodes in the Bigtable cluster. Again, please realize that the Bigtable cluster, that is the nodes, refer to the compute, the storage is separate. That front-end server pool does a good job of distributing workload across the nodes. So again, nodes are instances which belong to the cluster and each node handles a subset of the request to the instance. These nodes don't actually hold the underlying data. What they do hold is a lookup mechanism so that given a particular row key, they know where to find the corresponding record in the underlying storage. And that in turn brings us to the SS tables. SS tables, also known as tablets, actually hold the entire record, including the row key, all of the column families and columns, as well as the values and the timestamps. When a write request comes in, the node will figure out where that record needs to be written. When a read request comes in, along with the associated row key, the node will figure out where the entire record resides. In a sense, this entire Bigtable instance is acting as a gigantic distributed dictionary or hash table. It's worth keeping in mind that hotspots or performance degradations can occur if all of the user requests start hitting the same node. That's why key design is a very important aspect while working with Bigtable. When would you choose Bigtable? To begin with, if you're working with a very large volume of semi structured or structured data, exceeding maybe 1 TB, then Bigtable is ideal. Use cases of this nature include large scale IoT data collection from sensors or large user activity logs. You should also consider Bigtable if you are processing high velocity data with high throughput. Examples include real time analytics such as personalization, streaming data from financial transactions, and high frequency trading systems. Bigtable has low latency and high performance, which make it well suited to such applications. Remember also how it's cleverly designed to not perform deletes in real time. A third use case is while working with time series data, or in fact, working with any data that has natural ordering, such as timestamped logs or sequential records. Use cases here include monitoring systems, application performance metrics, and chronological event data tracking. Why does Bigtable perform well in such situations? Well, because it's easy to run range queries where you pull in all of the records where the row key lies within a specific range. Bigtable is also a good choice if your use case combines big data, that is high volumes and high velocity, as well as real time processing. Examples of such use cases might include real time fraud detection or recommendation engines, which are going to personalize content recommendations as the user navigates through your site. Finally, Bigtable is also a good candidate when you are performing inference. Remember that during the machine learning workflow, there are two distinct steps: training and inference. If your use case requires real time inference, then Bigtable is a strong candidate. Next, let's turn our attention to Firestore. This is also a storage offering for semi structured data. This is a pretty classic document database. Firestore is heavily used in web and mobile app development. Again, in terms of the taxonomy, remember that Firestore is a NoSQL database, but with very different use cases than Bigtable. That's the other NoSQL offering on the GCP. Firestore is a flexible and scalable database for mobile, web, and server development from Firebase and the GCP. It integrates tightly with the Firebase suite of apps, which of course is used in app development. It also integrates with other Google Cloud services. And taking all of this together, it's a great choice for real time app development. Firestore supports both document and collection data models, and it also has real time listeners so that an app can listen in on a document collection, as well as support for offline operation. That's particularly important in the context of mobile apps, which have to deal with scenarios where internet access may temporarily be unavailable. Firestore is a part of the Firebase platform. This is a comprehensive suite of tools and services meant to support the deployment, development, and scaling of mobile and web apps. This has a wide range of functionalities, including real time databases, authentication, integration with cloud storage, and hosting. Firebase is a one stop solution for backend needs. The main users of Firebase are again mobile and app developers who want the backend to just work. In addition to Firestore, the Firebase suite includes real time databases. It has Firebase authentication as well as robust analytics, performance monitoring, and cloud messaging. For now, we are only focused on the Firestore offering from the Firebase platform, so let's discuss its features. The first is the document data model. Data is stored in documents, and documents are organized into groups called collections. Each document has a document ID, and other than that, it contains attributes which are key value pairs. It's important to note that the values could themselves be sub-collections, and that's how hierarchical and nested relationships can be easily expressed. This data model makes Firestore ideally suited to working with formats like JSON, XML, and HTML. Another standout feature of Firestore is real-time syncing. When the underlying data changes, Firestore will automatically update all connected clients in real time. This is important for applications that require immediate data updates, such as, for instance, chat apps, collaborative tools, or live dashboards. The real time syncing makes sure that users always see the most current data. If you consider a mobile messaging app, something like WhatsApp for instance, you can see just how important this particular feature is. Offline support is another important feature for such use cases. Sticking with the mobile messaging example, Firestore provides a robust offline support. This allows applications to stay functional even when there's no internet connection. How does Firestore achieve this? Well, it caches data changes locally and then only updates those changes on the server from time to time. In this way, once the internet connection is restored, all of the updates will be sent at once. The offline capability is important in ensuring a seamless user experience on mobile apps. Firestore offers native SDKs for different mobile platforms, including iOS and Android, as well as for web development. These SDKs provide developers with all the tools and libraries needed to integrate Firestore into their apps. The native nature of the SDKs ensures optimal performance. Semi-structured data such as XML or JSON might contain very complicated relationships, and in order to work with such data, Firestore has powerful querying capabilities. These include the ability to handle large datasets and fast query performance, even on compound queries, range queries, and real-time query results. Firestore also provides automatic horizontal scaling. This makes sure that the database can accommodate increasing levels of data and traffic. As the application grows or usage grows, Firestore will handle the data and load balancing across multiple servers. This feature is once again designed for mobile apps where workloads can be quite spiky. Let's quickly talk about the data model in Firestore. At the top level, we have a collection which can be thought of as a logical grouping of documents. Now, from these terms, it's quite logical to think of each document as an individual JSON or XML file, but that need not be the case. In reality, you can think of each document as merely a fragment, that is, a self-contained element of JSON or XML or other markup. And in fact, it is the collection as a whole which might be a single XML or JSON file. So it's important not to take the term document too literally here. A document need not mean a standalone file. Within a document, we have a number of attributes which always are expressed in the form of key-value pairs. Remember that the values might contain sub-collections, that is, we could express nested and hierarchical relationships in a document. It's also important to remember that every document has a document ID, which uniquely identifies that document within the collection. Let's view an example of data that might be stored in Firestore. Here you can see that we have information related to employees. Employees here is a collection, and within this collection we have two documents corresponding to employee 1 and employee 2. Hopefully this example drives home the difference between a document in the Firestore data model and the term document used colloquially. What we see on screen right now might be contained in a single text file, and to that extent, we might think of it as a document file. But in this example, that entire document file actually contains a collection. The collection is called employees, and within that collection, there are two documents corresponding to emp1 and emp2. Also note how each of these two documents has a document ID, emp_01 and emp_02. What follows is a set of key value pairs for each of these employees. It's also worth noting that it's not necessary that all of the employees have all of the fields. For example, emp2 has a phone number, but emp1 does not. This is a simple example, but you might imagine that each employee might then contain a sub-collection, for example, a list of certifications. And that is how we can use a document database to express complex, hierarchical, and nested relationships. Real-time listeners in Firestore allow applications to listen in on changes made to documents or collections. And in this way, they keep the data in a particular app current. In terms of scalability, this must be achieved without retrieving the entire document database, else it would overwhelm the application. And that's why this is implemented via notifications. These are sent out by the Firestore platform to all of the real-time listeners who are listening in. The notifications will contain a snapshot of the updated data. Finally, a quick word on the offline support feature. Firestore is very proactive about caching data that's actively used. As a result, Mobile apps can read, write, query, and listen to data even when the device is offline, as long as that data happens to be in the cache. Then, at some future point when internet access is restored and the device comes back online, Firestore will synchronize all of the local changes. With all of the new knowledge that we've acquired by this point about the different storage solutions on the Google Cloud, it's time for us to return to one of the most important questions that we've been faced with. How do we choose the right storage solution for structured data? Here is a taxonomy with all of the information we've collected so far. Let's start walking through the branches of this tree, focusing on transactional workloads that we'd like to access using SQL. Choose Cloud SQL. For applications that need transactional workloads, they work with structured data and only need local or regional scalability. Cloud SQL is ideal for traditional RDBMS use cases such as online transaction processing (OLTP), CRM systems, and e-commerce platforms. Remember that Cloud SQL offers managed MySQL, Postgres, and SQL Server. It provides robust asset compliance and strong consistency. It's only regional and it can be configured either in single instance or high availability modes. If you have a transactional workload, but you also need global scalability and strong consistency for transactional workloads, then Spanner is probably your best choice. Spanner is perfect for very large scale applications like global financial systems, supply chain management, or multi region SaaS platforms. Remember that Cloud Spanner combines the benefits of relational databases with horizontal scalability and global distribution. It ensures high availability and low latency access even across regions. Its ability to handle high transaction volumes and complex queries make it suitable for mission critical applications that need both scalability and performance. If our access paradigm changes from SQL to NoSQL while we are still working with a transactional workload, then Firestore is an ideal choice. Firestore is a document database that works well with semi-structured data. It also has capabilities for real-time synchronization. If your use cases have to do with mobile or web apps, chat apps, collaborative tools, or user profile management, Firestore should be the first tool that comes to mind. Remember that Firestore provides automatic scaling, offline support, and real-time data sync across clients. Also keep in mind that Firestore supports both regional and multi-regional deployments. Let's switch now from transactional to analytical workloads. Here, provided that SQL is our standard access pattern, the only choice and the best choice is BigQuery. This is the most popular product on the GCP. It's a go-to solution for analytical workloads. It works with large-scale structured or semi-structured data. It's designed for big data analytics. It supports fast SQL queries even on petabyte scale datasets. It can be used for data warehousing, business intelligence, and advanced analytics. In addition, it also has inbuilt support for machine learning. Remember that BigQuery has a serverless architecture. It supports auto scaling and efficient resource utilization, and it decouples compute and storage. In addition, it supports very complex analytical queries, and its infrastructure has global availability across regions. That leaves Cloud Bigtable, which is perfect for NoSQL analytical workloads, especially those that need very high throughput and low latency on large datasets. Remember that Bigtable is well suited to time series data, IoT and sensor data analysis, real-time analytics of pretty much any sort, and monitoring applications. Bigtable provides horizontal scalability. It has auto scaling. It seamlessly expands clusters as your data grows. It excels in situations where the data is fast changing. It works well with sparse datasets and also handles rapid read and write operations. Bigtable is regionally available. This here is a perfect place for us to tie up a few loose ends and introduce a few other technologies that we've not discussed so far. Memory Store is one of these. You can think of Memory Store as a NoSQL solution. It is very similar to Redis. Google Cloud Memory Store is a fully managed in-memory data store. Because of its in-memory nature, it's extremely fast, so it can be used for low latency data access and very high throughput. It's ideal for use cases that need fast real-time data processing, such as caches. That's why memory store tends to be used in session management, gaming leaderboards, and real time analytics. Memory store itself supports two popular in memory data stores, Redis and Memcached. In Redis mode, you can think of memory store as a managed Redis service. Redis is an open source in memory data structure store which is perfect for caching and for key value lookups. It supports data structures such as strings, hashes, lists, sets, bitmaps, and hyperlogs. This makes it suitable for a variety of operations. The use cases where Redis jumps to mind include caching, real time analytics, pub sub messaging, and also geospatial indexing. Memory Store is a managed version of Redis. It takes care of automated provisioning, scaling, and maintenance. Memory Store can also be used as a managed Memcached offering. Memcached is an open source, high performance, distributed memory object caching system. Once again, a key use case of Memcache is for simple key value caching to improve the performance of web apps by storing frequently accessed data in memory and reducing the need to hit up the database. Migrating a database to the cloud is one of those scenarios that seems to come up over and over again. There are a few common techniques and approaches. Let's discuss them in detail. At a high level, one could do a lift and shift migration, or one could make use of a database migration service. The lift and shift is a very popular method. This involves moving an existing on prem database to the cloud, making minimal changes to the original architecture or design. This method focuses on quickly migrating data to the cloud without re architecting the data or the client apps. This is relatively straightforward, but also does not fully extract the savings and the benefits of moving to the cloud. The other approach is to use a database migration service or DMS. Here, there are specialized cloud services to help with the migration of databases from on prem environments to the cloud. These will provide support for real time data replication and try to minimize downtime. A DMS is a managed solution for transferring databases to the cloud, and if everything works smoothly, this can be a quick and efficient migration process which will fully leverage the benefits of the cloud. Let's talk a little bit more about the pros and cons of each of these approaches, starting with the lift and shift migration. As its name would suggest, lift and shift offers a relatively quick transition to the cloud. There might be reasons why the cloud migration is happening on very tight deadlines, or there may be financial pressures to move to the cloud and take advantage of the scalability, cost savings, and improved performance. In such situations, the lift and shift is a quick method to get to the end goal of being cloud only. The lift and shift approach ideally should lead to minimal disruption in business operations. Neither the existing database structure nor the client apps are going to be changed, and so there ought to be no need for extensive testing or retraining of staff. This continuity ought to ensure that business processes continue without disruptions or downtime. The flip side of this operational stability is that we likely will only get limited benefits of cloud native features. For instance, auto scaling, serverless compute, or integrated security features will not be fully leveraged in this approach. This could lead to suboptimal performance, and if the lift and shift approach is not tweaked in order to ensure that the cloud native features are used, it could even lead to higher operational costs in the long term because migrated applications might no longer be optimized for the cloud environment. Organizations could miss out on efficiency gains and cost savings that they could otherwise get by re architecting or modernizing their apps. So, in summary, a lift and shift approach is probably quite cost effective in terms of its initial investment because it maintains stability. However, in the longer run, additional steps ought to be taken after the lift and shift is complete in order to ensure that the full benefits of the move to the cloud are being unlocked. Next, let's turn our attention to the use of a database migration service. Specifically, the Google Cloud itself offers a service called DMS or Database Migration Service. You can think of this as the database migration service in the context of the Google Cloud. The DMS helps with transitions of data into Cloud SQL, and if you'd like to move Postgres workloads into AlloyDB, that is something that DMS can help with as well. So DMS is handy when you'd like to move either MySQL or Postgres to Cloud SQL. if you'd like to move Postgres to AlloyDB, and also if you'd like to lift and modernize your Oracle workloads into Cloud SQL for PostgreSQL. So you can see that the DMS supports both homogeneous and heterogeneous database migrations. Homogeneous migrations are those which involve transferring data from one database to another database of the same type or from the same vendor. Homogeneous migrations typically occur when moving databases between environments. The Google Cloud DMS supports all of the obvious homogeneous migrations, from MySQL to Cloud SQL for MySQL, from Postgres to Cloud SQL for Postgres, or from Postgres to AlloyDB for Postgres. Homogeneous migrations are relatively straightforward because no changes in SQL syntax, schema conversion, or data types are expected. In contrast, heterogeneous database migrations are more complicated. As their name would suggest, these involve transferring data from one type of database to a different type of database, usually involving different vendors or technologies. Here, one ought to expect lots of pain around schema conversion, data type mapping, the rewriting of SQL queries, and ensuring compatibility with the target database. Google Cloud's DMS can help with this complexity and will automate parts of the migration process. Specifically, the Cloud DMS supports a heterogeneous transition from Oracle to Cloud SQL for PostgreSQL. These homogeneous transitions that we just described are one of the common use cases of the DMS, and that is the lift and shift migration to a managed service. Google Cloud SQL is a managed service for MySQL, Postgres, or SQL Server, and you can lift and shift your existing MySQL, Postgres, or SQL Server installations into Cloud SQL using the DMS. Using the Cloud DMS for lift and shift is better than doing it entirely with the lift and shift approach, because this way you get the benefit of high availability, disaster recovery, and all of the performance tuning that we get with the managed database services. Another common use case for the database migration service is for multi-cloud continuous replication. As you might imagine, this service will only help to migrate your data into the Google Cloud. So if the data exists in another cloud provider, then a migration job can be set up to continuously replicate the database from that other hyperscaler into Google Cloud, thus giving us multi-cloud read availability. Please note that the database migration service will not support a dual write scenario. That is, it will not help you with writing to and reading from both the source and the destination. Obviously, this service is going to help to get data into the Google Cloud, and it's not likely to be so obliging when it comes to getting data out of the Google Cloud. On the subject of getting data into Google Cloud, it's worth now talking about DataStream. This is a serverless change data capture and replication service offered by the Google Cloud. It's used for real-time streaming of data from various sources such as databases and apps into Google Cloud services such as BigQuery, Cloud Storage, and Cloud Spanner. By capturing and delivering changes as they occur in real time, DataStream supports near real-time analytics and integration, ensuring that data is always up to date. DataStream is meant to help simplify the process of building data pipelines, specifically ELT, that is, extract, load, and transform pipelines, which are meant to carry out low latency data replication with near real time insights being made available in BigQuery. DataStream is serverless and scalable, and that eliminates the need for resource provisioning and management. It automatically scales up and down based on the workload demands. DataStream is meant to be simple to use for setup and monitoring. It has a nice UI and guided workflows to help with configuring data streams. It also has a set of monitoring tools for real-time visibility, and it allows you to set alerts and notifications to track any anomalies or disruptions. DataStream integrates with a range of Google Cloud data services, including Dataflow, Data Fusion, PubSub, and BigQuery. You can think of all of these as building blocks which can then be combined to create even more interesting architectures. For instance, you might have data which is captured by DataStream, then processed in real time using Dataflow, ingested into BigQuery, or synchronized with other databases using Cloud Data Fusion. We've not discussed Cloud Data Fusion. This is yet another Google Cloud service which is meant to integrate data from siloed on-prem platforms, the promise being that it helps to construct scalable, distributed data lakes. Finally, DataStream supports a wide variety of use cases, including analytics, database replication, synchronization of data for migrations, and building event driven architectures. We will now shift our emphasis subtly from data storage to business intelligence, and along the way, we will also explore the Looker offering on Google Cloud. Business intelligence is all about the last step in the data value chain, that was data activation. This specifically referred to using data in order to actually make decisions and have those decisions affect outcomes for the enterprise at large. So, data activation is the outcome that business intelligence is trying to drive, but of course, that outcome cannot be reached without an entire process of using people and technology to collect and analyze data that the organization has to use in its strategic and daily decision making processes. Identifying trends, detecting patterns, and gaining a deeper understanding of customers as well as of the enterprise's own operations. All of these are a part of business intelligence. BI tools and platforms often include dashboards, data visualization, and automated reporting in order to get easy access to the insights that are needed for such decision making. Business intelligence is all about analytical processing, and that's why BI tools typically work closely with the data warehousing solution employed by an organization. And for that reason, we can broadly think of three categories of BI tools: on premise, open source, and cloud based. On prem tools run on your own organization's infrastructure and commonly work with traditional data warehouses that also run on prem. They might, however, be less scalable than cloud based solutions. Open source tools can be cost effective, and in particular, if they are cloud based, they can also save you money on infra costs. However, open source tools often require a fairly high level of knowledge and hand coding for effective use. Cloud based BI tools are especially good at handling streaming data and with big data processing such as volume, variety, and velocity. They can also be cost effective because of the scalability and all of the cost advantages that come with using the cloud. Business intelligence has several benefits. For one, you can use data in order to understand the business performance of the organization better. BI can help to improve a company's overall performance and trajectory. Modern BI tools can help organizations understand what has just happened, whether it's in the marketplace or in relationships with customers or suppliers, why this has happened, and what needs to happen in order to optimize operations. In this way, BI can help to make sense of a fast changing and dynamic marketplace. In addition to understanding what's going on, business intelligence also helps an enterprise take actionable steps in response to key performance indicators. Companies have the ability to continuously track and analyze data and their progress towards their KPIs. Data that's been analyzed can uncover important patterns and trends in nearly every area of the enterprise, including sales, customer service, production, security, and more. By understanding changes, whether it be in customer behavior or suppliers or aspects of our own business, BI can also identify new opportunities. For instance, we've seen how first, second, and third party data can all be analyzed in order to unlock value. A key use case of first party data was personalization, that of second party data was expanding reach and striking strategic agreements, and third party data came in handy for understanding broader market demographics and trends. Audience segmentation also falls into this category. Of the various reasons why firms are unable to fully leverage business intelligence, three stand out. The first is poor quality data. Bad data leads to bad decisions. A second is data silos. Data that's been split across multiple systems and cannot be integrated to get a holistic view is basically useless in coming up with good decisions. And finally, a skills gap. BI tools might require a significant level of expertise in order to use. It's important for access to data and BI tools to be democratized. That leads us now to Looker. Looker is a Google Cloud offering which is a modern BI and data analytics platform. It's designed to help your organization explore, analyze, and visualize your data. As a part of the Google Cloud, it integrates seamlessly with other important Google Cloud services and aims to mitigate some of the problems that we just discussed. Within the Looker family of products, it's important to understand the difference between Looker and Looker Studio. Looker is a robust BI platform. It has various different products, such as an IDE, that can be used in order to manage and define data models. LookML, that's the Looker modeling language, is also a part of this platform. It ensures consistent and accurate business metrics across the organization. Looker, the platform, might be used by developers who are looking to benefit from its rich embedding and API features. Thus, they can integrate Looker's capabilities into other applications. It's worth calling out one of the Looker suite of products, and that's Looker Studio. This is a no cost, user friendly tool that helps users build fully customizable dashboards and reports. It's got a very easy to use UI, so it's got a drag and drop editor and allows users to connect to different data sources, including Google Analytics, Google Sheets, and BigQuery. Looker Studio plays a key role in democratizing access to data and ensuring that the skills gap doesn't come in the way of unlocking the power of BI. The Looker platform could run on a cloud service that could be Google Cloud or another hyperscaler. It can also be hosted on your own servers. Whichever way, the data will remain in database and will not be copied to a Looker instance. Looker Studio, on the other hand, is a Google Cloud service and it's available to anyone with a Google account. Looker has a number of powerful features, starting with embedded analytics and custom data experiences. So, using Looker, you can embed dashboards within applications. These might be bespoke applications that you have written and integrated into your workflow. In addition, Looker will directly integrate with Vertex AI, and that in turn means that you can create advanced AI workflows and analytics within the Looker environment. Looker has robust APIs, which means that pretty much any action that can be performed via the UI can also be done programmatically. Looker has something known as the Universal Semantic Modeling Layer, which serves to break down data silos. This modeling layer is intended to serve as a single trusted source of truth for all of your business metrics and data. You ought to be looking to use this universal semantic modeling layer to curate and govern critical metrics that all users across the organization can view in a consistent manner. Looker supports real time and self service analytics. The idea is that enterprise dashboards that are built in Looker can be relied upon because they make use of well governed data, and what's more, they provide real time insights right out of the box. These dashboards have sophisticated features. Users can interact with existing dashboard tiles, they can ask new questions, expand filters, and drill down to row level details. This self service approach encourages data exploration and democratizes access to business intelligence. Looker supports a rich and customizable set of visualizations. It has a wide range of chart types, graphs, interactive elements, and allows users to create tailored reports for specific business needs. The drag and drop interface makes it easy for anyone to build and customize dashboards, and as we previously discussed, these dashboards can then be embedded within other bespoke applications. Finally, as we've already discussed, Looker integrates seamlessly and tightly with other Google Cloud services, specifically BigQuery, Cloud Storage, and Vertex AI. The Looker platform is extremely feature rich, and that also means that it can sometimes be a little intimidating. Looker Google Cloud Core is a simplified and streamlined version of Looker. It has almost all of the original functionality and can be accessed via the Google Cloud. So, Looker Google Cloud Core will not be available for customer hosted or multi cloud environments. Again, the Looker platform could run on prem or on a different hyperscaler, but Looker Google Cloud Core will only work on the Google Cloud. By using this, you can provision and administer instances from the Google Cloud Console. When might you use Looker? Well, for one, when you'd like to have governance over key metric definitions. Enterprises that require strict governance over important metrics in order to ensure consistency and accuracy across the entire enterprise will find Looker a good choice. The Universal Semantic Modeling layer will standardize the definitions and measurement of KPIs. In the context of large enterprises with many different lines of business and divisions, this can be a lot harder than you think. Looker provides robust data access permissions. It has very fine grained access control, so you can define permissions at various levels control who can view, edit, and share data. This is likely to be particularly attractive firms in domains with strict governance needs, such as those in finance, healthcare, or other highly regulated industries. Because Looker provides real time insights into the operations of a business, it's perfect for firms which are in operationally intensive industries like retail, manufacturing, and logistics. There, timely, low level data driven decisions can significantly impact efficiency and financial performance at the aggregate level. Here, Looker's ability to drill down into data and understand the underlying details is especially helpful. Looker has strong embedding capabilities and very solid API support, and for that reason, it's a good choice for firms that are looking to integrate analytics into existing tools, workflows, and applications. This is especially relevant when combined with the tight integration with other Google Cloud tools such as BigQuery and Vertex AI. These are all compelling use cases for Looker, the platform. Now let's talk about choosing Looker Studio. The first likely use case is if you're interested in self service analytics and visualizations. Here, the drag and drop editor, which allows users to create customizable reports and dashboards without technical skills, comes in handy. In this regard, Looker Studio is perfect for decentralized organizations that want to democratize data access and enable employees at all levels to engage with data directly. Looker Studio is also a good choice if you'd like to create interactive dashboards that integrate extensively with many data sources. These go beyond Google Cloud offerings like BigQuery and also include Google Analytics and Google Sheets. These interactive dashboards can allow users to explore data in real time, apply filters, and drill down into specifics. Finally, Looker Studio is also a fine choice if you are looking for embedded reports for web and ad hoc reporting. These might be one off visualizations or reports to deal with special situations. This is especially useful if you need to share data with external stakeholders, clients, or a broader audience. The report embedding feature of Looker Studio will allow you to integrate these visualizations into websites, portals, or other web apps. Let's try out BigQuery for ourselves. I think you'll find that it's very easy to use. What we're going to do here is create a dataset, then upload some data into a table, and run some simple queries and visualization operations against the data in that table. Here we are at console.cloud.google.com. Let's quickly orient ourselves. We have the project ID in the middle of the screen. That's Looney GCP CDL. That project ID is also visible in a drop-down over towards the top left of the screen. And then we have three horizontal lines at the extreme top left. Those are called the hamburger. That's the navigation menu where we can access many different Google Cloud products. You can set the active project at any time by clicking on the drop-down on top. Here you see a list of all of the projects in this organization. Looney GCP CDL is fine, that's what we'll stick with. Then we click on the navigation menu on the top left. We have pinned a couple of products, SQL and Cloud Storage. Let's click on View All Products. This will take us to a comprehensive list. We scroll down until we get to BigQuery. That's listed under the Analytics section. We click on the little pin icon next to BigQuery, and now when we go back to the navigation menu, we'll see that BigQuery shows up there as one of the pinned products along with Cloud Storage and SQL. Now if we hover over BigQuery in the navigation menu, a sub-menu opens up and you can see that there are a lot of different options available. For now, we are not interested in any of them. Let's just click on BigQuery and this takes us into the product detail. The first thing that we need to do here is to click that big blue enable button in order to enable the BigQuery API. This is a one-time operation. The next time we click on BigQuery, we'll be taken through into the Explorer that we now see. The home page of this Explorer view is currently a bit cluttered. Let's declutter it by clicking on the close icon towards the center top. Then let's expand the pane over on the left. That is the name of the project, Looney GCP CDL, within which we have various BigQuery related resources, including queries, notebooks, data canvases, and external connections. Remember, our aim right now is to upload a dataset into a table and run querying and visualization operations against that. In order to do this, we first need to create a dataset. A dataset in BigQuery is a logical grouping of tables, something like a database in the RDBMS world. Creating a dataset is easy enough. We just click on the three vertical dots next to the project name. A context-sensitive menu opens up. The first item there is Create Dataset. We click on it, and over on the right, the Create Dataset dialog opens up. Once again, up top is the project ID, and then comes the dataset ID. Based on the Kaggle dataset that we will be working with, let's call this AutoMPG_dataset. This deals with the miles per gallon, numbers that we get from various cars. Down below, you can see the location type. The two choices there are region and multi-region. If we hover over that little question mark, we get a tooltip which tells us that this selects the location where our data will be stored. All tables in this dataset will share this location, and this can't be changed later. We'll take a moment to experiment with different choices of region and multi-region. For now, we can go with a multi-region dataset which is hosted in the US. There is another interesting option here, default table expiration. This is a checkbox, and by hovering over that tooltip, we see that any new table created in this dataset will be automatically deleted the specified number of days after creation. So this is something that we would use for temporary data that we don't really need to preserve. Let's keep going. Some other settings that are relevant here are the case-insensitive table names. Let's make sure that we check that particular box. Scrolling up, you can also see that there are different encryption options, and the default is Google Managed Encryption Key. Another setting that's relevant here is default collation. As that tooltip tells us, if we leave this particular checkbox unchecked, then default collation will have case-sensitive behavior. This can have consequences for how string queries on our data work. If you would like case-insensitive string queries, then you should check this box. We can leave most of these other settings to take their default values. Note the storage billing model option, and then the time travel window. That's an interesting one. BigQuery supports time travel, and that's turned on by default. The length of the time travel window by default is set to 7 days. Time travel is a feature which allows users to access data that has been modified or deleted, provided those changes occurred within a certain time frame. The use cases have to do with accessing historical data or accidental data recovery, and it's also quite useful for audit and analysis use cases. We are done with most of the interesting settings here. Let's click on the Create Dataset button towards the bottom of the screen, and our dataset comes into existence. We see it over on the center left, AutoMPEG_dataset. Also notice the flash message at the bottom of the screen telling us that AutoMPEG dataset has been created, and there's a link to go to the dataset directly. Instead, let's click on the three vertical dots next to the dataset name over on the center left, and in the context-sensitive menu which opens up, let's choose to open it in a new tab. Here it is in the center of the screen. We have the dataset info and other properties visible down below. We could choose to edit the details or create a table in this dataset. We can do that in a couple of different ways. One way to do it is to click on the Create Table button towards the top center of the screen. Another is to click on the three vertical dots next to the dataset name, and in the menu that opens up, click on Create Table. This takes us into the Create Table dialog where we are first prompted for the source. Right now, the source is set to empty table, but from the dropdown we see that other options include Google Cloud Storage, Drive, Google Bigtable, Amazon S3, and Azure Blob Storage. Let's go with the upload option. We have a copy of the dataset on a file in our local machine, and that's what we will be using. It is worth keeping in mind, though, that all of these are possible sources of data for a BigQuery table. Next, let's click on the Browse button in the Select File dialog, and we navigate to the file which is on our local machine. Here it is, autompeg.csv, and on screen now you can also see the URL. This is the Kaggle URL from where you can get the original data. Next, we see that the file format is automatically filled as CSV. Other supported formats include JSON, Avro, Parquet, and ORC, as well as data store backups. Let's keep going. We've got to enter the table name. Let's go with auto_mpg. There's also a table type. We'll stick with the default, which is native table. Then when we get to schema, we will check the box for schema auto detection. This will save us the trouble of entering all of the column names and column types. Then we have more advanced partition and cluster settings, which we need not change for now, tags, advanced options, encryption options, all of which we will leave to the default values. Finally, we click on the Create Table button over at the bottom, and we can see from the flash message that the table was successfully created. We can also verify that over on the left, we have a table under AutoMPEG dataset, and the table is called auto_mpg. Clicking on that show more doesn't really do anything, but if we click on the three vertical dots next to the table name, in the context sensitive help menu which appears, we can go ahead and open the table in a new tab. We've now come to the end of this demo in which we accessed BigQuery for the first time, we enabled an API needed to do so, we created a dataset, and then within that dataset we created a table. And we also populated that table with data uploaded from a file on our local machine. In the next demo, we will explore the properties of this table and start running some queries. We ended the previous demo having successfully created the table auto_mpg in the dataset AutoMPG dataset. On screen now, in the center of the screen, we can see the details of this table. There are tabs here for schema, details, preview, lineage, data profile, and data quality. We are currently in the schema tab. Remember that the schema was auto-detected because we had checked the schema auto-detection checkbox while uploading data into this table. Quickly glancing through the field name, type, and mode, we see firstly that all of these fields have been set as nullable. Secondly, we see that all of the field names have been taken from the title row of the CSV file that we had uploaded. This is quite intuitive. It's the types that are the most tricky, and if we look really closely, we'll see that while they seem broadly correct, there is at least one little error which jumps out. Horsepower is being wrongly detected as a string. One possible reason for this might be that missing values in the horsepower column might have some kind of character, such as a question mark or a dash. These are the kinds of details that we need to look into the data and perform some data cleaning in order to be sure of. Next, let's click on the Details tab. Of the attributes that we can see here, the most interesting is case insensitive, which is set to true. We can also see that there is a section for primary keys, but we've not specified any, and neither were any picked up while we were auto-detecting the schema. Scrolling down, we get the storage info. There are 398 rows, and the table occupies 30.5 kilobytes. Next, let's click on Preview, and there we get a sense of the data. Of course, we could also have examined this data in the CSV file, but we note here, for instance, that the horsepower column does indeed contain a question mark. There it is, right at the middle of the screen in row 7. So we now have an explanation for why the schema auto detection did not work perfectly for this column. Missing values are represented with a string identifier, and that's the question mark. Since we'll be running some queries and building some visualizations on this data, let's take a moment to familiarize ourselves with it. Clearly, this is an automobile dataset, and that's why the columns correspond to miles per gallon, cylinders, displacement, horsepower, weight, and so on. Scrolling way over to the right, we see that we have one string column, and that's the car name. Once we are done looking through the data, we can close this tab. You can see all open tabs over towards the top center. Currently, we are in the AutoMPEG tab. We shut that. That only leaves the AutoMPEG dataset info tab, and we shut that as well. Let's quickly glance at the available options down below. We can open a SQL query, a Python notebook, or a data canvas, or show the welcome page. Let's go ahead and run a query. One easy way of doing this is to just open a new tab by clicking on the plus button over on the top left. This opens up a new tab titled Untitled Query. Let's type out the simplest possible query we can think of. Select star from AutoMPEG. Conveniently, this query editor has line numbers, and you can see there that on line 4, we have the table name AutoMPEG enclosed within backticks. In case you're wondering where to find the backtick key, it shares the same key as the tilde, and it's typically just above the tab key on most keyboards. The backticks character is widely used in BigQuery. It's used to delimit identifiers such as table names, dataset names, column names, and any other identifiers that might contain special characters like spaces. It's also useful in handling reserved words. If, for instance, you have a query inside which you need to use a string like select, from, where, you ought to enclose these within backticks. So the backticks character plays a key role in Google BigQuery. We can choose to run this query or save it, download it, or share it. However, even before we do that, we can see way over on the right that we have that red exclamation sign telling us that we are going to encounter an error. The reason for that is that we've got to qualify the table name with the dataset name. Let's go ahead and click run in any case. Now that red exclamation sign moves from the top right down to the bottom left. But the error remains the same. Table AutoMPEG must be qualified by a dataset. The green checkbox on the top right is merely because the query completed. Let's try again. Let's modify our query so that on line 4 we now have backtick open AutoMPEG underscore dataset dot AutoMPEG and then backtick close. The query validator likes this. We can see this from that green checkbox way over on the right. Now if we click run, this query is going to run through successfully and we have the query results down below. There's a lot of functionality packed into that query results tab. Way over on the right, you can see that we can save the results, and it's in fact possible to either save the results to a local file or to a Google Drive link. We could also choose to explore the data, and we'll come back to that while working with Looker in a bit. At the center of the screen, we see that there are different tabs: job information, results, chart, JSON, execution details, and execution graph. We are currently in the results tab, and at the bottom right, you can see that results per page is set to 50, and we are currently looking at 1 through 50 rows out of 398. There are arrows over on the bottom right to move to other pages of the results. Let's quickly cycle through the other panes as well. Here we are in the job information pane. We have how many bytes were processed and how many bytes were billed. This is a really small table, just 30.5 KB, but we ended up being billed for 10 MB because that's the lower limit. You can also see that the job priority was interactive and use legacy SQL was set to false. Let's switch over to the chart tab where you can see that it's very easy to visualize data from within this table. Over on the right, we see the chart type is scatter. The x-axis dimension is miles per gallon, and then there are different measures, that is, different variables on the y-axis. All of those are visualized with that scatter chart we see at the center of the screen. If for some reason we'd like a JSON representation of this data, possibly to feed into some other NoSQL system, well, here it is. Just click on the JSON tab. Next, let's click on the execution details. This tells us how much time the query took, 401 milliseconds, the slot time consumed, that's 76 milliseconds, and various other details about the query execution. Down below, we have a visual representation of the different stages: wait, read, compute, write, and so on. We can view both the average time and the maximum time for these. These statistics aren't very interesting with a very simple query like the one we have here, but for complex queries with possibly nested joins or subqueries, this can be very helpful in improving and debugging query performance. There's more visual information about the execution of the query if we click on execution graph. We are now done running our first query and exploring the output. In the demo coming up ahead, we'll move on to some data cleaning and begin by eliminating rows that have missing values. We had ended the demo by examining the output from a very simple select star from our one table. Let's now move on and run a few more queries and perform some more operations. On screen now, we have another very simple query. This is also a select star, but with two differences from the previous example. First, on line 4, you can see that we've added the project name in front of the dataset name. So it now reads looney.gcp.cdl.autompeg.dataset.autompeg. That's just to demonstrate that if we really want to be explicit about the table name, we need to qualify it not only with the dataset name but also the project name. And then on line 5, we've added a limit clause, limit 5, which means that we will only get back 5 result rows from whatever query is passed before the limit clause. The green checkbox on the right tells us this query will run correctly, there's no syntax error, and indeed here are the results down below. We've got only 5 rows as expected. Now that we've run our second query, let's move on to something a little more meaningful. The query that you now see on screen looks to count the rows where there are missing values. You might recall that while doing a preview of the data in this table, we had seen that we had a question mark in the horsepower column for the missing values. And this query that you now see on screen is a way of getting a count of the rows that contain missing values. There are a few different points worth noting here. On lines 6 through 14, you can see that we've made use of the cast function in order to ensure that each of these columns is cast, that is, it's treated as a string. Then you can also see that we have all of the column names, and only some of those column names on lines 12 and 14 are enclosed within backticks. The reason for that is that those two column names, model year and car name, contain a space. The backticks help to delimit and make sure that the spaces are treated correctly. Finally, you can also see how we've made use of the logical OR to connect each of these conditions. Let's run this query through. We can see from the green checkbox that the syntax is valid, and the results down below confirm that there are indeed rows with missing values. There are 6 of them in total. For now, let's just go ahead and run a simple delete statement to get rid of all of these rows. So we very slightly modify the syntax of the query. We get rid of the select star and replace it with a delete from. The where clause remains the same. We run this through and we can see from the output down below that this statement removed 6 rows from our table. Now by this point we've eliminated all of those question marks from the horsepower table, but we've still not fixed the problem of the wrong schema that was auto-detected when we uploaded the data. You might recall that horsepower was being treated as column of type string, whereas in reality it's a numeric column. We have a couple of options here. For one, we could go in and edit that schema and actually explicitly cast the column to be numeric. Another option is to create a new processed version of the table and copy over the correct data from the data that we loaded in. The benefit of doing it this way is that we would still have the raw data in the original table. We'll do neither. We'll go with a third approach instead, which is to create a view. On screen now, you can see the syntax for this. Create view, and then within backticks, we have the project name, Looney GCP CDL, the dataset name, that's AutoMPEG dataset, and then the name of the view, which here is car age view. That's followed by the keyword as. So the first line of what you see on screen is the creation of the view. From lines 2 through 11, we have the view query. The important line here is line 6, where we use a cast in order to make sure that the horsepower column is changed from type string to type int64. We retain its original name, that's why line 6 reads cast horsepower as int64, close parentheses, as horsepower. Also on line 9, we've performed an interesting date processing operation. Here we have a new column called car age, and the way we get that is we take the year from the current date, that is the date when this query was run, and from that we subtract 1900 plus the model year. And in this way, we get how old this particular car model was. That line 9 gives us a sense of how we would go about processing dates in BigQuery. We go ahead and run this, and in the query results down below, we don't have any rows, we just have an update that this statement has resulted in the creation of the view car age view. If we look closely over on the left, we see that within our AutoMPEG dataset, we have the table AutoMPEG, but we now also have the view car age view. If we hover over that view, we get an interesting tooltip. As it tells us here, we can tap to open in current tab or command plus tab to open in a new tab. We go with the second option, and here is the car age view. The schema is visible. We can confirm that horsepower is of type integer. If we click through into the details, we can see that the storage is 0. That is, the number of rows is 0 and no bytes are occupied. Scrolling further down, we can see the view query is also displayed in here. Let's now close out of the details of this view and switch back to our query window, where we will now proceed to query our view. This is a select star, just like any select star on a table, except that we are now selecting from the view car age view. We run this through and we see the results down below. We originally had 398 rows, We deleted 6 rows for the missing data, and that's why we see at the bottom right that we have 392 rows left. We can also scroll to the right and check that the car age has been measured correctly. With this view query, it's also interesting to look at the execution graph. So we click on that particular tab and we see in the block diagram that the select operation is performed on a table. Let's click on the data source and we get the details of the table over on the right, table info, and this is our AutoMPEG table. This gives us a clear sense that the view has effectively run as a query on this table. Scrolling down, we can see the storage info. There are 392 rows and about 30 KB in the original table. That's in the total logical bytes, but looking down below, we can also see the total physical bytes, which are only 19.34 KB. That's because we've not selected all of the columns from the original table. The view query has only a subset of the columns. Next, let's save the results out, for which we click on the Save Results button towards the center of the screen. There are many options available here. We can save as a CSV on Google Drive if the file is less than 1 GB. We can save locally if the file is less than 10 MB. We can save in JSON format, again up to 10 MB. And then there are also additional options such as JSON, that's new line delimited. We could choose to save the results as a new BigQuery table or to Google Sheets or even copy to clipboard. Notice that the copy to clipboard will only work for up to 1 MB of data. Right now, what we're really interested in doing is saving the results out to another BigQuery table. So we click on that option. We are prompted for the project, dataset, and table. Let's go ahead and fill in each of these. When we click on dataset, we can see that there is an option there to create a new dataset. We won't do that. We'll go with the AutoMPEG dataset that we've already got. That's displayed under the loaded datasets down below. Next, we've got to specify a table name. Let's call this AutoMPEG cleaned. There are also all of the advanced options, but we'll give those a pass for now. We hit save. We get a flash message down below telling us that the query result has been exported. And we can also go to table from there. And over on the left, we can see that there are now two tables in our dataset. There's AutoMPEG, which was already in there, and now there's also AutoMPEG cleaned. Let's click on the three vertical dots next to AutoMPEG clean and open in a new tab. Here we are back with all of the details of this new table. So we have the schema, details, preview, lineage, data profile, and data quality. This time we can verify that the schema looks more correct. Horsepower is clearly of type integer. Then we can click on details and we can see there the storage occupied by this particular table. It's got 392 rows as expected and it occupies 21.44 kilobytes. We can also click on the preview pane in order to view the contents of this table which we've just created. That gets us to the end of this demo in which we created a view and then saved the results of that view out to a new BigQuery table. We are now going to turn our attention from querying to visualization. To begin with, we will perform some simple visualizations within BigQuery, but very quickly we will switch over to Looker. And we will then see how we can create a nice, elegant report and save that report as a PDF based on the data in our table. Let's start by cleaning up our workspace. We first close all of our open tabs and then we run a query on our AutoMPEG cleaned table. So we click on the three vertical dots next to the table name and then choose query from the menu that opens up. This query is a really simple one. It's effectively just a select star from this table. Let's go ahead and hit run. The results appear down below. And this time we are going to name and save this query. You could do this by hitting Command S or by clicking on the save button up top. We click on save query. We are prompted for a name and a region. Let's call this auto query and hit save. Now let's see if we can perform some visualizations on the results. So we click on the chart tab in the query results and expand it to view the visualization that BigQuery has prepared by default. Over on the right, we can see the chart type, which is currently set to scatter. Then we can choose the dimension, which is a fancy word for the x-axis. The current choice of x-axis is mpg, that's miles per gallon, and then we have measures, that's y-axis variables. You You can also see here that multiple columns have been placed on the y-axis. These include cylinders, displacement, horsepower, and more. As we can see from the message there, we can select up to 5 measures. Let's try and change the chart type. In the dropdown, we see that in addition to scatter, we have line and bar charts. So this is a nice feature, but still it isn't a very large or intimidating list of chart types. Let's try a bar chart instead. We get a warning telling us that the selected dimension contained duplicate values which were excluded from the chart. That's fine. Let's try with a different choice of dimension. So instead of MPEG, we try and go with cylinders. This way, there are unlikely to be duplicate values of the X variable. We then can also play around with the measures. So we've now changed the y-axis to be MPEG, and this chart is a little more interesting. On the x-axis, we have the number of cylinders, and on the y-axis, we have the miles per gallon. It's also somewhat interesting to change this chart type to scatter. We can now see the entire range of mileages for each of the cylinder counts. We spend some more time familiarizing ourselves with the data. Here, for instance, is a scatter plot where on the x-axis, that's the dimension, we have horsepower, and on the y-axis, we have miles per gallon. This looks like a pretty clear relationship. There is a downward sloping relationship between horsepower and miles per gallon. So as the horsepower increases, the miles per gallon decreases. That's very intuitive. That's what we would expect. Once we think we've reached the limits of the visualization capabilities of BigQuery, we can click on that Explore Data over on the center right. There are 3 options there: Explore with Sheets, Explore with Looker Studio, and Explore with Python Notebook. Let's choose the middle option and open up Looker Studio. This opens in a new tab. You can see first off that the URL is of the form lookerstudio.google.com. In the center of our screen, we can see that we have a report with a title, AutoMPEG Cleaned. That happens to just be the table name. And then there are 2 visualizations that Looker has helpfully placed in there for us. Let's go ahead and delete both of these and start adding our own visuals. Let's also give this report a nice name. Let's call this AutoMPG report, and we can also modify the title of this page that we see in front of us. It currently reads AutoMPG Cleaned. Let's go ahead and change that to something more descriptive like weight versus MPG. You can see that we have text properties and a lot of other widgets that we can add in there. Let's click on the Add a Chart button over up top. And this now is a truly impressive list of visualizations. Some of the really specialized ones appear down below. These include a tree map, Sankey chart, gauge charts, waterfalls, and timelines. We spend some time looking through this list, and then we decide to add a smooth line chart. So that's what we click on. A widget appears and we drag and drop it into the correct place in our page. This widget, like the widgets in BigQuery, has dimensions and metrics as they are now called. So the dimension still refers to the choice of x-axis and the metrics are the y variables. We can see that the current choice of dimension is MPG. We can also see the type, it's numeric. We infer that from the 1, 2, 3. A little further down, we also see the choice of metric. That is currently just the record count. Now we've titled this visualization weight versus MPG, and that's what we want to plot. So let's edit the choice of dimension so that instead of MPG, we scroll down until we get to the weight. That is going to be on the x-axis, that's the dimension, and then scrolling further down, we change the choice of metric. There are many options in here, and we pick MPG so that we are going to have weight on the x-axis and MPG on the y-axis. There's also a choice of sort. You can see ascending or descending. Right now, it's sorted in descending order. It's also possible for us to process the metric. So we click on the little pencil icon next to the metric. It opens up a dialog where there are aggregations. The default aggregation is sum, and we'll move this instead to be an average. Remember that this is a smooth line chart, which is why we need to have the aggregation in there. In any case, we continue experimenting with the choice of metric and dimension. Now we have the average miles per gallon as the metric, that's the y-axis, and we've also changed the sort so that it's on the weight, which is the x variable, and it's now in ascending order. We play around with some of the settings in this dashboarding UI, and once we are satisfied with this particular visualization, we click on the Add Page button towards the center left. This has now become a paginated report. You can see that we have arrows and we see page 2 out of 2. So we are on the second of 2 pages. You can also see that the back arrow is enabled, the forward arrow is not because we are on the last page. Let's add a text box. So we do that by clicking on the text button in the ribbon up top. Then we can drag and drop the location of this text box and start configuring its properties such as the font and paragraph style. We nicely format the text, including its bold, italic, underlining, and other properties, and we enter the text cylinders versus miles per gallon. Next, let's click on the Add a Chart button up top. Once again, we get this long list of visualizations. Let's add something simple this time, just a column chart. We again have to select the choice of dimension and metric. For the dimension, we pick the number of cylinders, so that's going to be on the x-axis. And as far as the y-axis is concerned, we go with the miles per gallon. We still have the aggregations to select. Right now, both of these are set to sum. Let's edit those and change both of those aggregations from sum to average. Like with any drag and drop UI, we have a lot of fine-grained control. Here, we are changing the sort so that it's going to be displayed in ascending order of the number of cylinders. Once we are satisfied with this page, we can click on the page 2 of 2 up top. There is a tooltip telling us that we can click here to manage pages. This opens up a dialog, and at the bottom right of the screen, you can see that we can add a page. This now adds a third page so that at the center in the ribbon, we see it says page 3 of 3. We now get busy designing this third page. We add a text box, perform all of the edits. This is going to be a heat map of the miles per gallon. For that, we click on Add a Chart, and this time we choose Table with Heat Map as our choice of visualization. Once again, you can see over on the right that we have the choice of dimension and of metric. Dimension is currently set to miles per gallon. Metric is currently set to record count. Now, both of our visualizations so far had just the one dimension, but if you look closely, you can see that there is a little plus icon and it says Add Dimension next to that. We are now going to make full use of this functionality. For each one of the dimensions that we wish, we'll need to click on that plus Add Dimension button. Then we'll need to edit the aggregation and configure the dimension. We are going to be going with average for each of those dimensions. We'll skip over the exact steps because they are quite repetitive, but you can see by the end that we have the visualization that you see on screen now. Over on the right, you can see that we have many metrics. We have the average of the acceleration, car age, cylinders, displacement, horsepower, and weight. Looking now at the actual heat map in the center, we see that over on the left we have a column with the miles per gallon. That's the x variable, i.e. the dimension. Then we have all of those metrics, all of these are averages, and each of these is represented in heat map fashion. Right now, this data is sorted by the acceleration dimension. How do we know? Well, because the shade of blue is clearly deepest up top and becomes uniformly lighter as we go down. The same is clearly not true for the other dimensions, such as, say, the weight, where we have some rows in the middle of the screen which are in a darker shade of green. Well, we can control the order of the sort. We scroll down and confirm that it's currently sorted by the average of the acceleration. That's simple enough to change. Let's instead sort it by the miles per gallon. We can confirm that this has taken effect by looking at the values of the miles per gallon over on the left. Up top, we have the smallest value, that's 9, and the values increase as we look down. We can resize the columns and change the appearance of this page to suit our appearance. We've built a very refined multi-page dashboard. At the bottom right, you can see that we are looking at rows 1 through 100 of 127. We click on the right arrow and that takes us to the remaining results. If we'd like to share this report with an external audience, we can click on File and Download as a PDF. That's what we do. You can see that it also allows us to select all pages or only a selection. We hit download, the PDF is prepared and it's saved to our local machine. That gets us to the end of our exploration of Looker Studio, which helped us to build a very sophisticated dashboard and then save that dashboard to a PDF for external consumption. Just for completeness, let's switch over to our local machine. In the downloads folder, we have this AutoMPEG report.pdf. We open it and it does indeed have three pages. The first is our weight versus MPEG visualization. That's a smooth line chart. The second is the bar chart of cylinders versus miles per gallon. And the third is our heat map, where we have many Y variables, all of which are plotted against miles per gallon as the dimension, that is the X variable. Looker Studio, with its drag and drop user interface, was one way of working with BigQuery. In this demo, we will switch to the other extreme. We will continue working with BigQuery, but now we will make use of BQ, which is Google's powerful command line utility for working with BigQuery. BQ is great if you'd like to integrate BigQuery operations into your scripts. So let's begin by closing our Looker Studio tab. We are now back in the Google Cloud Console. Let's activate Cloud Shell by clicking on that icon over on the top right. This will open up Cloud Shell at the bottom of this tab. Let's click on the Open a New Window tab over on the center right. This opens it up in a new tab. As before, let's run our gcloud config set project so that all of the other commands that we run automatically know that we are referencing this particular project. Here, it's Looney GCP CDL. When we run this command, we are prompted to authorize Cloud Shell. We go ahead and authorize, and this then changes the prompt in our Cloud Shell window. It now includes the name of the project in that yellow font. The BQ command line utility is already configured and available for use on Cloud Shell, so we can plunge right into our operations. Here we've run the command to create a dataset, bqmk, and then dash dash dataset, followed by the name of the dataset that we wish to create. Please also notice how we have prefaced that dataset name with the project name, Looney GCP CDL sample dataset. The command runs through successfully, and we are told that sample dataset has been created within the context of the project Looney GCP CDL. We will switch over to the web console and confirm the creation of this dataset. But before that, it's worth noting that the bqmk command can be used to create not only datasets, but also tables, views, and various other BigQuery entities. Let's switch back to the other tab where we've got the web console open. Here over on the left, we have the project Looney GCP CDL, and right now we only seem to have our existing AutoMPEG dataset listed down below. However, that's because this page has yet to refresh. We click on the three vertical dots next to the project name and then choose the refresh contents option from the menu that opens up. And once we do this, the page refreshes and we can indeed see sample dataset that's been created. It's visible at the bottom left of the screen. So this is proof that the creation of our dataset using BQ from Cloud Shell was successful. Right now, this dataset is empty. Let's switch back over to Cloud Shell and add a table to this dataset. This time we've run bqmk with the -t flag. That is short for --table. In other words, we are using this command in order to create a table. Whenever we use the -t flag, we also need to specify the schema of the table that we wish to build. We've done that on the last line of this command. Our table is to have three columns: name, sales, and year, and the corresponding types are string, float, and string. There's more, however. This particular table is going to have an expiration property. 600 seconds or 10 minutes is going to be the life of this table, which means that after we run this command, the table that we create will automatically be deleted after 10 minutes or 600 seconds. We've also added a description to our table, which reads sample table with expiry. We've also specified the fully qualified table name in the form project ID dataset dot table name. So here that's Looney GCP CDL sample dataset dot sample table. We go ahead and run this command. It goes through successfully. And now once again, we can switch back over to the web console and confirm that our dataset contains a table within. This time we will again click on those three dots and choose to refresh the contents of our project. And there at the bottom of the screen, we can see that we have sample table within the sample dataset. Let's click on that. Here we have the schema information, and as expected, we have the field names name, sales, and year. The types are string, float, and string. Next, let's move to the Details tab. To begin with, we can see that the description that we set from BQMK is indeed reflected here. It says sample table with expiry. And then, even more interestingly, we see the table expiration. This table expiration is in terms of a specific time. That is 7:34 p.m. on the 6th of June. And if we look carefully, we can see that that's exactly 10 minutes after when the table was created, which was 7:24 p.m. on the 6th of June. So our expiration of 600 seconds is indeed reflected in the point of table expiration. This is when that table will be automatically deleted by BigQuery. Now at this point, this table is empty. We can confirm that by clicking on the Preview tab where we are told that there is no data to display. Let's change that, and we will insert some data into this table from Cloud Shell using BQ. And what's more, we will insert this data in JSON format. Cloud Shell supports a simple text editor called Nano. So let's run the command nano sales.json. This will open up an empty file called sales.json. We've got some pre-prepared JSON which we will copy paste in here. This JSON is pretty simple. On each row, we have the data for one record that we would like to insert into our table. Remember that our table had the column names name, sales, and year, and that's why these are the keys in each of these dictionaries. While creating our table, we had specified the type of the name column as string, the sales column as float, and the year column as string. And that's why you can see here that all of the values for sales are not enclosed within double quotes. The values for the name and the year are enclosed in double quotes. Nano has very simple commands, and the important ones are listed out down below. For instance, Control K is cut, Control U is paste, and then over at the very bottom left, Control X is exit. So we now hit Control X. We are asked to confirm the file name to write out. We confirm sales.json, and 10 lines are indeed written out to this file. Now we are back at Cloud Shell. We've closed the Nano editor. Let's run BQ, this time with a different subcommand, load. The BQ load command is followed by the source format flag, and we've assigned the value new line delimited JSON. Source format is used to specify the format of the data that's being loaded into a BigQuery table, and supported values include CSV, new line delimited JSON, Avro, Parquet, ORC, and data store backup. Then we specify the dataset name and the table name into which we'd like to load this data, that's sample dataset.sampletable, and finally the file name that contains the data, that's sales.json. We hit enter and this command runs through successfully. The upload is complete. The current status says done. Now let's switch back to the web console, scroll down towards the bottom, and examine again the contents of our sample table. This time we click on the preview tab to find that there are indeed 10 rows listed in there. So we were successfully able to create this table using BQMK and also to load JSON data into it. Now that we've confirmed that, let's switch back to Cloud Shell and run some queries using BQ. Here is our first command, and it's simple enough. BQ query, and then the one flag that we specify here is use legacy SQL, which is set to false. That's followed by the actual query syntax. The query itself is simple enough. Select star from sample dataset.sampletable where sales greater than 2000. A couple of points worth noting. The entire query is enclosed within single quotes. So you can see the single quote before select and after 2000. Then the name of the dataset and the table is enclosed within backticks. Remember, the backtick character shares a key with tilde. We run this query and it runs through successfully. We have all of the rows from our data where the sales are indeed greater than 2000. We can verify that by looking at the sales values. The smallest value here is for the name John Doe. Let's rerun the same query but raise the sales threshold to 2600. And this time when we hit enter, we see that the row for John Doe no longer appears in the output. Let's run a few more simple queries. The one on screen now is going to select count star as total records from our sample table, and this returns total records equal to 10. If you're wondering about that use legacy SQL equals false flag, remember that BigQuery supports two dialects of SQL, Google SQL and legacy SQL. Google SQL is fully SQL compliant, but it also has some additional extensions. By setting use legacy SQL equals false, we are effectively using Google SQL, and in fact, our queries here are quite simple and completely standard SQL compliant. Let's round this demo off by running one last simple query in which we perform a group by. So now we select year and the sum of sales as total sales from our sample table, and then we group by the year. This query runs through successfully as well, and this highlights some of the capabilities of BQ, which is a very powerful command line utility that you can use in order to work with Google BigQuery. We started this course off by exploring BigQuery for analytical data, focusing on its capabilities for handling large-scale analytics. We focused on BigQuery for analytic workflows, learning how to efficiently manage and analyze extensive datasets. Additionally, we covered Bigtable for semi-structured data, emphasizing its scalability and performance for managing high-throughput workloads. We also examined Firestore, another solution for semi-structured data, highlighting its real-time capabilities and ease of use. Next, we learned how to choose the right storage solution for structured data, considering factors such as data volume, access patterns, and performance requirements. We discussed the process of migrating databases to the cloud, addressing key considerations and best practices for a smooth transition. We also explored how to derive business intelligence and insights using Looker, a powerful tool for creating interactive dashboards and reports that provide valuable business insights. Finally, we explored practical aspects of managing data in BigQuery. We learned how to create datasets and tables, enabling us to organize and store data effectively. We ran queries to extract and analyze data and worked with views and tables to optimize our queries and data management processes. Additionally, we used Looker Studio to visualize our data and gain deeper insights. We also practiced command line operations with the BQ tool, enhancing our ability to manage BigQuery resources programmatically. In conclusion, we built a strong foundation in utilizing Google Cloud's data solutions for enterprise data warehousing needs. We covered essential topics such as BigQuery for analytics, Bigtable and Firestore for semi-structured data, and Looker for business intelligence. We are ready to move on to the next course in this journey, Data Processing Pipelines on Google Cloud. Optimizing data processing and analytics is crucial for organizations to effectively manage and derive insights from their data. Leveraging Google's suite of tools including Dataproc, Dataflow, PubSub, and Cloud Composer enables businesses to build robust, scalable data pipelines and facilitate real-time analytics and workflow automation. In this course, you will learn about batch and stream analytics, focusing on their respective advantages and use cases. We will examine the processes involved in ETL pipelines, that is extract, transform, and load pipelines, as well as ELT pipelines, that's extract, load, and transform pipelines. You will understand how they support data integration and preparation for analysis of different scenarios, whether in batch mode or in real time. Next, you will learn about the characteristics of Dataproc, Google's managed Spark and Hadoop service, which simplifies big data processing on the cloud. You will explore various Google Cloud services for ETL, such as Dataflow, which offers real-time stream and batch data processing capabilities. Understanding these tools will help you to appreciate their roles in building robust and scalable data processing pipelines. Finally, you will explore real-time messaging with PubSub, Google's service for ingesting events from different data sources. It supports real-time analytics and data integration. You will learn about Cloud Composer, a fully managed workflow orchestration service, as well as other data-related technologies, gaining conceptual insights into how they facilitate the management and automation of complex data flows. We've spoken a fair bit about the importance of real-time analytics, and in order to really get the full benefit of real-time analytics, we've got to understand the differences between batch and stream processing. Batch analytics involves processing and analyzing large volumes of data that have been collected over a period of time. This data is processed in batches, often on a scheduled basis, maybe daily or weekly. In contrast, stream analytics involves processing and analyzing data in real time as it is generated and received. Stream analytics allows for continuous computation and the generation of immediate insights from data streams. As you might imagine, between the two, stream analytics can get a lot more complicated quite easily. Batch analytics work well for tasks that do not require immediate results, such as end of day reporting, monthly performance reviews, or historical data analysis. In stream analytics, however, the instantaneous nature of the data processing and the real time nature of the insights make this process useful in monitoring systems, fraud detection, real time recommendation engines, and personalization systems. With batch processing, volume and variety are likely to be issues that the system has to contend with. With stream processing, it's often velocity which is the hardest to deal with. Let's visually understand the difference between batch and stream processing. Here, you can imagine that there's processing data for days 1, 2, 3, and so on. Because there's no real-time requirement here, the data is lagged by a day. So, the input data from day 1 is processed on day 2. The input data from day 2 is processed on day 3, and so on. The stored data is processed over a period of time. Let's now say that the same data needed to be processed in a stream pipeline. Here, we need to ingest and process the data as soon as possible. So the data that's collected or input on day 1 needs to be processed on the same day. Likewise for day 2 and every subsequent day. Let's enumerate some of the differences between batch and stream processing. In batch processing, we are always dealing with bounded, finite datasets. On the other hand, with stream processing, because new items might be added to our stream at any point, we are dealing with unbounded and infinite datasets. Batch processing is slower because there's greater time available between data ingestion and analysis. That's why velocity of the data matters less in batch processing. Stream processing is high velocity because the data needs to be processed immediately as soon as it's received. In batch processing applications, latency on the order of hours and minutes is considered quite acceptable. However, with stream processing, the latency is measured in units of seconds and milliseconds. By their very nature, batch processing jobs throw out periodic updates as batches are processed and jobs complete. Stream processing, on the other hand, sends out continuous updates because jobs are constantly running. There are other, somewhat more technical differences between batch and stream processing. One key one is that in batch processing, the order in which the data is received is unimportant. With streams, however, the order matters a lot, and out of order arrivals need to be tracked and potentially handled in a special way. With batch processing, we can point to all of the data that's been collected in the batch, and that constitutes a single global state of the world at any point in time. That's not the case with stream processing. There's only a history of events received, because there may be other events which have already been created but which have yet to be received into our stream. The implication of this is that batch processing code knows all of the data from start to finish. With stream processing, however, the code has no idea of what lies ahead. Let's discuss some familiar examples of batch analytics. One of these might be end-of-day financial reporting in a financial institution such as a bank. Banks often use batch processing to generate end-of-day reports to summarize the day's transactions. This will involve aggregating data from various sources such as transactions, account activities, and market data into a central data repository. That data will then be processed, possibly overnight, to produce reports on daily balances, transaction summaries, P&L statements, and compliance checks. These reports are crucial for regulatory compliance, auditing, and financial analysis. Another very familiar example of batch analytics is monthly payroll processing. Organizations use batch processing to handle payroll calculations and disbursements on a regular basis, typically once or twice a month. This process involves collecting data on employee hours worked, salaries, bonuses, tax deductions, and other relevant information. That data is then processed in bulk to calculate net pay, generate payslips, and initiate direct deposits into employees' bank accounts, and also make any tax payments towards payroll taxes that might be required. Batch processing ensures that all payroll data is processed consistently and efficiently, reducing the likelihood of errors and ensuring timely payment to employees. A third common use case of batch analytics is in data warehousing and ETL pipelines. ETL is short for extract, transform, and load, and this is a way to get large volumes of raw data from various sources, fit into some target schema, and then get that into a storage system such as a data warehouse. Such ETL pipelines in batch mode might run nightly or weekly, depending on the organization's requirements. The transformed data is then available for BI, reporting, and analytics and can provide insights for strategic decision making. However, batch ETL will not be timely enough for real time decision making. For real time insights, we've got to turn to stream analytics. Let's walk through some examples of stream analytics. A common one is real time fraud detection. Financial institutions and payment platforms use stream analytics to detect and flag potentially fraudulent transactions in real time. The real time aspect is important because these transactions are ideally flagged before the money has been sent out to the bad actors. By continuously analyzing transaction data as it flows in, these systems can identify patterns and anomalies that indicate potential fraud, such as unusual spending patterns, transactions from unexpected locations, or a series of high value transactions in quick succession. When a suspicious activity is detected, the system needs to be able to immediately trigger an alert, potentially block the transaction, or take some other remedial action. Another common use case of real time analytics is in device monitoring of Internet of Things devices such as sensors. In operationally intensive industries such as manufacturing, energy, and transportation, such stream analytics can be used to monitor and manage operations in real time. In a smart factory, for instance, sensors will continuously stream data about equipment performance, temperature, humidity, and other critical metrics. Stream analytics processes will rely on this data to detect any deviations from normal operating conditions, for instance, an unexpected spike in temperature or pressure. Doing so can help to flag potential issues. These could lead to equipment failure or even more catastrophic outcomes. Another case where streaming analytics are required is in real time customer recommendations. Here, the real time aspect is because the recommendations need to be presented on the fly as the user navigates the website. E commerce platforms or content streaming devices leverage stream analytics to personalize recommendations to users in real time. Such information combines very recently acquired information about user actions, such as the video the user is browsing right now, along with historical information of past browsing patterns, purchase history, and demographic information. As we can see from all of these examples, stream analytics are quite complicated to get right, and that's why there is a host of specialized tools, including on the Google Cloud, to deal with these complex use cases. There are some important services on the Google Cloud, such as Dataproc and Dataflow, that we've got to understand. And in order to understand these services, we first need to familiarize ourselves with ETL and ELT pipelines. ETL, that's short for extract, transform, and load, is an end to end process in which a company takes its data, hopefully the full breadth of its data, that is structured, semi structured, and unstructured, from as many different sources as possible, and then gets it into a state where it's actually valuable for the business. Organizations have been using ETL for decades. Traditionally, it's been the acceptable way for organizations to combine data from multiple systems, departments, and sources into a single database, data store, data warehouse, or data lake. ETL can also be used to store legacy data, but more typically these days, it's used to aggregate data for analysis and thus to drive business decisions. In this way, you can think of the typical end state of data as residing in a data warehouse. Let's talk about each of the steps in this ETL process one by one. Let's start with the extract phase. This is where the enterprise retrieves and verifies data from as many sources as possible. The extraction phase involves collecting data from multiple source systems that might include databases, flat files, APIs, and any other type of data repository. The goal is to gather all of the relevant data needed for analysis in one centralized location. During extraction, the data will come in various formats and structures and reflect the diversity of the source systems. It's crucial for this extraction process to be efficient and minimize the impact on the source systems that collect the data so that their performance and availability does not take a hit. Data extraction can be performed either in batches or in streaming fashion in real time. That depends on the requirements of the ETL process in this organization. Next comes the transform step. Once all of the data has been extracted, it enters the transformation phase where it's cleaned, enriched, and converted into a format that is suitable for analysis and meets the requirements of the target system. Transformation might involve several steps such as data cleaning, removing duplicates or correcting errors, data integration, that is, combining data from different sources, data enrichment, where context or additional information such as tags are added, and data conversion, where data types and structures might be changed. Business rules and logic will be applied during this phase to ensure that the data is consistent, accurate, and usable. The transformation step is critical for ensuring data quality and making it ready for meaningful analysis. Finally, we get to the load phase. This is where the transformed data is loaded into a data repository, which is the target data storage system. Typically, this will be a data warehouse, although it could also be a data lake or a data lakehouse. The loading process must be carefully managed to ensure that the data is inserted correctly and efficiently, neither causing disruptions to the target system nor introducing errors or bugs into the data. Depending on the use case, again, the loading might happen either in batch or real time streaming mode. Real time data loading is superior in that it allows for continuous data updates. These are essential for real time analytics and decision making. Batch loading is typically done off peak hours to minimize the impact on the system performance of the target system. Once the data is loaded, it is available for querying, reporting, use in dashboards, and analysis by end users. Notice that in an ETL pipeline, the transform step occurs after the data has been taken from the source system, but before it is placed in the target system. As you can see in the schematic up above, the source systems might be individual databases for CRM, billing, or ERP, and the target system may be a data warehouse like Snowflake, BigQuery, or Redshift. In between comes the transformation step. There's a lot of heavy lifting that needs to be performed during the transformation step, operations such as masking, filtering, and joining, as well as stages such as data cleansing to remove duplicates or errors, data conversions, change data types and formats, and data aggregation, such as calculating sums and moving averages. Data filtering, in order to select only relevant data and remove noise, also needs to be performed here. Notice again that the transform step here is being carried out outside of the target system. As data warehouses have become more and more powerful, it makes less and less sense for the transformation to happen outside the target system. And that's why ETL pipelines are increasingly being replaced by ELT pipelines. As the acronym would suggest, this stands for extract, load, and transform. An ELT process is an integration process in which the data is extracted from the source systems and then loaded into a target system before any transformations are performed. The benefit of the ELT paradigm is that those transformations happen within the target system and they can leverage all of the capabilities of data warehouses such as Google BigQuery. Another benefit of using ELT over ETL is that all of the raw data is available in the data warehouse. That ensures that there's no data loss during the transformation step and the entire audit trail is maintained. In the schematic visible on screen now, you can see that extraction is followed by loading, and then we have the transformation way over on the right. The load step now often involves only minimal processing, the idea being to capture the data in its raw form to maintain its completeness and integrity. Another advantage of the ELT approach is that the data is loaded before all possible use cases have been thought through. After the data has been loaded into a data warehouse, then the transform phase begins. or more accurately, the transform phases begin. Because now all of the data is available, we've not made any assumptions about the end use case. Multiple new use cases might arise, each one requiring its own transform step. Transformations will likely include operations such as removing duplicates, correcting errors, aggregating data, and applying business rules to derive new insights. Although an ELT pipeline can be performed with operations largely within BigQuery, ETL pipelines are still extremely important, and Google Cloud has various services optimized for ETL. The first of these is Cloud Dataproc. This is a fully managed service that simplifies running Apache Hadoop and Apache Spark workloads. This allows users to quickly create, process, and scale clusters for big data processing. It offers flexibility and cost efficiency via per second billing. Cloud Dataproc integrates seamlessly with other Google Cloud services such as BigQuery, Cloud Storage, and Cloud Bigtable. This is an ideal offering for ETL, data mining, and machine learning tasks. It also helps to leverage the power of the Hadoop ecosystem and a wide range of open source data tools. Another powerful tool is Cloud Dataflow. This is a fully managed stream and batch data processing service. This enables the creation of data processing pipelines using the Apache Beam API. That allows for unified programming of both streaming and batch data flows. Cloud Dataflow automatically scales to handle varying data volumes and also integrates with other cloud services such as BigQuery, PubSub, and Cloud Storage. Dataflow is specifically designed for real-time analytics, ETL processes, and complex transformation tasks. And finally, Cloud Data Fusion is a fully managed cloud-native integration service that helps users build or manage ETL or ELT data pipelines visually. It has an easy-to-use drag-and-drop interface, and it simplifies the creation of data workflows in a no-code fashion. It supports a wide range of data sources and transformation capabilities, allowing users to connect, transform, and analyze data seamlessly across various environments. It integrates with other Google Cloud products such as BigQuery, Cloud Storage, and the AI tools. We've briefly introduced Dataproc, Dataflow, and Cloud Data Fusion. Let's now talk about each of these in a little more detail. In order to very quickly jog your memory, Dataproc is the managed Hadoop and Spark offering on Google Cloud. Dataflow is a way to build unified batch and streaming pipelines using the Apache Beam API, and Cloud Data Fusion is a no-code or low-code way to build ETL pipelines. Let's talk about each of these, starting with Dataproc. Remember that Dataproc is the managed Hadoop and Spark tool on the Google Cloud, and Hadoop and Spark are both examples of distributed systems. If you think about it, the two competing approaches to building complex systems are monolithic and distributed. Monolithic systems scale vertically, distributed systems scale horizontally. In almost every distributed system, we have a group of machines that are usually called nodes and which collectively are called a cluster. So all of the nodes together form a cluster. It's probably fair to say that Hadoop sparked the big data revolution by making it possible to run big data processing applications on a cluster of machines. Before Hadoop, incredibly powerful vertically scaled machines were needed in order to run big data operations. Hadoop marked the victory of distributed over monolithic. Hadoop has a few different components which we should be aware of. It has a storage layer called the Hadoop Distributed File System, or HDFS. It has another component known as MapReduce, which can be thought of as the compute component. And finally, it has a coordination manager called YARN. That's short for yet another resource negotiator. HDFS is a distributed file system. It's used to store large amounts of data across multiple nodes. It ensures high availability and fault tolerance by dividing the data into blocks and then replicating them across different nodes to guard against hardware failure. MapReduce is a programming model. It works with large datasets using a parallel distributed algorithm on a Hadoop cluster. MapReduce splits every processing task into a particular type of smaller subtasks which can be executed in parallel on parts of the data. This is the map phase. And then after the map phase has been executed concurrently on many nodes, the results are going to be combined in something known as the reduce phase. MapReduce is very elegant. There are great ways of splitting up all kinds of common problems into a map and a reduce phase so that they can be executed in parallel. Yarn is the resource management layer. It allocates system resources to various applications running in the cluster and deals with job scheduling and cluster resource management. There is also an additional component known as Hadoop Common, which consists of libraries and utilities needed by other Hadoop modules. This provides essential services and features such as file system management, serialization, and configuration management. Dataproc is effectively a managed Hadoop service on the Google Cloud. It functions by running clusters on compute engine virtual machine instances. The data in HDFS can be stored on the persistent disks of those virtual machine instances, and it also can store data in Google Cloud Storage buckets. The latter approach is preferable. Dataproc has a number of attractive features. For one, it's really easy to create a cluster and manage a cluster. Properly administering a Hadoop cluster used to be a formidable task, but now it's become very simple with Dataproc-like tools. Dataproc integrates with the Google Cloud Console, and so the Hadoop admin effectively has an intuitive interface for cluster management. Dataproc will also support automated cluster scaling, allowing resources to be added or removed based on workload demands, thereby ensuring better performance and cost efficiency. Also, users can schedule cluster jobs and shut down clusters automatically when tasks are complete. Dataproc allows access to the entire Hadoop ecosystem, including popular tools such as Apache Hive, Pig, and HBase. These are in addition to Spark, which is also available via Dataproc. This comprehensive integration allows users to make use of these familiar open source technologies. The VM instances in the Dataproc cluster come pre-configured with these tools, making it very easy to switch over. Dataproc provides high performance and scalability by making use of Google Cloud's infra. For one, there's a high-speed network connection between nodes within a cluster. This guarantees high throughput and low latency access to data. That becomes quite important because there's a lot of data flowing across nodes in the map and reduce steps. Dataproc can also scale clusters horizontally by adding more nodes as workloads increase. Additionally, users can directly configure and make use of aspects of the Google Compute Engine VM instances and leverage hardware accelerators such as GPUs and other machine types. On-prem Hadoop clusters tend to be very expensive because it's rarely the case that all of that compute and storage is being utilized. In contrast, Dataproc is much more cost-effective because it's billed on a per-second basis with a 1-minute minimum. In this way, users only pay for the resources that they actually use. This fine-grained billing approach helps organizations optimize costs versus on-prem clusters. Also, you can make use of preemptible VMs, which are effectively lower-cost compute instances for transient workloads. Finally, there's a relatively new feature called Dataproc Serverless, which eliminates the need to even manage the cluster infrastructure at a high level. Dataproc Serverless is specifically aimed at Spark users. Over the years, Spark has become more and more popular and widespread relative to the original Hadoop use case. And for folks who wish to run Spark batch workloads without provisioning or managing any servers or clusters, Dataproc Serverless is the answer. So in summary, Dataproc is the managed Hadoop and Spark offering on Google Cloud. Dataproc can run all Hadoop workloads including MapReduce, Hive, Spark, Pig, Flume, and Scoop. It's primarily used to run Spark workloads these days because that's the most popular one of these technologies right now. Dataproc Serverless is a relatively new feature which allows you to run Spark batch workloads without the provisioning and management of servers. Let's continue our discussion of Google Cloud Services for ETL. Now that we are done with Dataproc, which is the managed Hadoop and Spark offering, let's turn to Cloud Dataflow. Dataflow is a unified stream and batch data processing service. It helps you to create data processing pipelines which can deal with either kind of data. It adheres to the Apache Beam API and integrates well with other cloud services, notably BigQuery, PubSub, and Cloud Storage. A couple of important keywords in this context: serverless. Dataflow is serverless and fully managed, and unified, because Dataflow helps you to build pipelines which will manage both batch and stream processing in a unified manner. Serverless is important because it allows developers to focus on building the processing workflows and not worrying about scaling up and down storage and compute. And the unified nature is important because it allows code reuse. Effectively, now the same pipeline and the same code flow will work for both batch and streaming data. The steps involved in using Dataflow are as follows. First, you write the code for the pipeline. This tends to be in Java or Python. Then you submit the job for execution, at which point Dataflow takes over. It will assign compute resources known as workers and go ahead and execute the workload using those workers. The code for the pipeline makes use of the Apache Beam APIs, which can inherently be parallelized, and that's what Dataflow does. The parallel execution of all of the tasks happens through the workers, and this is only possible because you write code invoking the Apache Beam APIs, and those APIs are well understood by Dataflow. Those APIs are also unified, which means that they know how to deal with both batch and stream data. The APIs are implemented by Dataflow and inherently parallelized. Apache Beam is an open source unified programming model that's designed to define and execute both batch and streaming data processing pipelines. These APIs can be invoked from either Python or Java. There are various execution engines which implement these APIs. These include, of course, Google Cloud Dataflow, but also Apache Flink, Apache Spark, and others. The constructs in Apache Beam pipelines are very similar to an ETL pipeline. There is a data source, which could be a source of either batch or streaming data. Then there are transformations, which modify the data to get it into the correct final form for the target system. And finally, there is the data sink, which is some form of persistent storage representing the target system. For example, a data warehouse like Google BigQuery. You might be thinking that Dataflow clearly requires developers to invoke those APIs in Python or Java. Isn't there a no-code or low-code way to set up ETL pipelines? Well, that's exactly what Cloud Data Fusion is. This is a fully managed cloud-native data integration service that can be used to build and manage ETL and ELT pipelines, and it features an easy-to-use drag-and-drop interface. Cloud Data Fusion touts what it refers to as code-free self-service. That is because using a graphical interface, non-technical users can also perform data integration tasks using simple point-and-click interactions. This self-service approach removes the dependency on data engineers or other technical professionals. Data Fusion supports collaborative data engineering because it allows users to create and share custom connections and transformations. The reusability of these components via collaborative data engineering is an important attraction of this tool. Cloud Data Fusion has some great real-time data integration capabilities. These include with operational databases such as SQL Server, Oracle, and MySQL, and it can get data into BigQuery from these sources with minimal effort. Also, it can be integrated with DataStream, and thereby it can deliver streams into BigQuery from where they will be accessible for real-time analytics and decision making. Cloud Data Fusion has a comprehensive integration toolkit. This can be used to connect to a variety of both modern and legacy systems using code-free transformations, conditionals, pre- and post-processing steps, as well as alerting and notifications for error processing. Cloud Data Fusion is a great way to get unstructured data from an external or on-prem source into Google Cloud Storage. And for this reason, it's an important tool for hybrid enablement. Hybrid and multi-cloud environments are seriously at risk of data siloing. Cloud Data Fusion helps to get unstructured data from those environments into Google Cloud Storage and mitigates that risk. How do you pick the right pipeline service? Well, Dataproc is the managed Hadoop offering, And so you should definitely go with Dataproc for your data pipelines when you need to run large-scale data processing tasks using Hadoop ecosystem tools such as Hadoop, Spark, Hive, or HBase. Dataproc is great for batch processing ETL jobs and data warehousing tasks where you need all of the power of Hadoop or Spark. You can rely on Dataproc to help you with the creation, management, scaling of clusters, and it's pretty cost effective because of the per second billing and the use of preemptible VMs for transient workloads. Dataflow is the obvious choice when you need to build a pipeline that can deal with both real time streaming as well as batch processing using the same unified programming model. Dataflow leverages Apache Beam, which is great for this particular use case of unified processing. Bear in mind, though, that Dataflow requires the most technical expertise and knowledge of programming in Python or Java. Even so, Dataflow is great for low latency real time processing scenarios such as fraud detection, personalization, recommendations, or live analytics. Finally, you should go with Cloud Data Fusion if you need a low code or no code implementation where you can use simple point and click UI in order to build and deploy data pipelines easily. Data flow pipelines require fairly proficient developers in order to build them. Cloud Data Fusion pipelines can be built by technical or non technical users. Also, do remember how Cloud Data Fusion works well in hybrid and multi cloud scenarios because it can help to get your unstructured data from on prem or other cloud providers onto Google Cloud Storage. We've spoken a fair bit about real-time systems and streaming analytics. However, we've yet to introduce a really important component in this context. That component is Google Cloud Pub Sub. Cloud Pub Sub is a messaging service. More accurately, it's a fully managed real-time messaging service which enables event-driven architectures and asynchronous communication between distributed systems. The name PubSub comes from the fact that it follows the publish subscribe model. Messages are sent by publishers to a logical abstraction called a topic. Subscribers can choose to subscribe to a particular topic, and then every time a message is published on that topic, the subscribers will receive it. In this way, the production and the consumption of the messages is decoupled. The subscribers and the publishers do not depend on each other in any way. PubSub is a very scalable product. It can automatically scale to handle high throughput, and that means that it can work with large volumes of messages. And it's not only large message volumes that PubSub can deal with, it's also very scalable in terms of growth in the number of topics, the number of publishers on a topic, or of subscribers listening in on that topic. PubSub delivers very low latency, and in that way, it ensures that communication is near real time. This makes PubSub excellent for applications that require immediate data processing, such as real time analytics monitoring, IoT device communication, and personalization systems. PubSub has excellent levels of reliability and durability. It has an at least once delivery guarantee, and it will store messages durably until they have been successfully acknowledged by subscribers. The at least once delivery guarantee ensures that messages are not lost even in the event of system failures. PubSub enables event-driven architectures, which means that different parts of the application can communicate and react to events asynchronously. This decoupling between the sender and the receiver is a key aspect in any scalable event-driven architecture. The decoupling of the publishers from the subscribers via the topic abstraction allows PubSub to function as an asynchronous many-to-many messaging system. There can be many publishers sending messages on a topic, there can be multiple topics, and there can be multiple subscribers receiving those messages on a given topic. This combination makes PubSub great for large-scale distributed systems where multiple components need to communicate seamlessly. The decoupling of senders and receivers has another benefit in terms of system design. We can add, remove, or change the code of individual publishers and subscribers, and the overall system will be unaffected. Let's understand in a little more detail each of these different abstractions contained in PubSub. A topic is a named resource to which messages are sent by publishers. The topic acts as a conduit or a level of abstraction between the publishers and the subscribers. A publisher is any entity that sends messages to a topic in PubSub. Publishers might be applications, services, or any system component that needs to share data or events with other parts of the system. When a publisher sends a message to a topic, PubSub will ensure that the message is delivered reliably to all subscribers of that topic. As we've discussed, publishers are decoupled from the subscribers, which means that they can send messages without needing to know how or where those messages will be consumed. In PubSub, a subscription represents a stream of messages from a topic that is to be delivered to some receiver, i.e., to the subscriber. The subscription acts like a message queue. It holds messages, i.e., it encapsulates state, until those messages are acknowledged by the subscribers. A topic acts as a buffer between publishers and subscribers. A subscription acts as a buffer between different subscribers on the same topic. Because of the subscription abstraction, different subscribers can receive messages on the same topic independently without knowing anything about each other. This also means that the individual subscribers do not need to be processing messages at the same speed. The subscription is an important mechanism for robust and reliable message delivery. A subscriber is an entity that receives messages from a subscription. Subscribers might be applications, services, or system components that process data or events published on a topic. Once a subscriber receives a message, it must acknowledge to indicate that the message has been successfully processed. This acknowledgement mechanism ensures that messages are not lost. Because of the at least once delivery guarantee, PubSub will keep trying or retrying to send the message in case of processing failures. One important note, subscribers can be configured to handle messages either in real-time or batch mode. Finally, a word about the message and message attributes. A message in Cloud PubSub is a combination of data and attributes sent from a publisher to a topic and then delivered on to various subscribers via the subscription. The data part of the message is called the payload, that's the actual information being conveyed. Message attributes are key value pairs associated with the message. These might provide additional context or metadata. These attributes can be used by subscribers in order to filter, route, or process messages based on specific criteria. This combination of data and attributes makes messages flexible and informative. Schematically, we can think of Cloud PubSub as messaging middleware. It connects publishers and subscribers while also acting as a buffer and a level of abstraction between them. If we double-clicked on the Cloud PubSub block at the center of this diagram, we would find there the abstractions corresponding to different topics as well as the subscribers. PubSub has some classic use cases that are worth discussing. The first and maybe the most obvious is in real-time analytics. PubSub is often used for real-time analytical applications because it helps with immediate data processing. For instance, e-commerce platforms might use PubSub in order to collect and analyze customer behavior as those customers interact with the website. You can imagine that this will be a way to personalize their browsing experience. Another common use case for PubSub is in log aggregation. In this use case, logs from different services and applications are collected and centralized for monitoring, analysis, and troubleshooting. In a distributed system, each component might publish log messages to a PubSub topic. A centralized logging service, which is acting as a subscriber, will consume these messages, store them in a log management system like Google Cloud Logging or BigQuery, and then use them for further analysis. This approach simplifies log collection and also makes it easier to monitor system performance and detect anomalies or diagnose issues in real time. PubSub is also heavily used in event-driven microservices. In such architectures, services communicate with each other through events rather than through direct calls. This promotes loose coupling and scalability. For example, in an online order processing system, there may be multiple microservices dealing with order management, payment processing, and inventory management. When an order is placed, the order management service might publish an event on a PubSub topic. Other services, such as the payment processing component and the inventory management component, subscribe to this topic and react correctly by processing the payment and updating the inventory respectively. This event-driven approach allows each service to operate independently and scale as needed. IoT networks, consisting of a lot of sensors and other small hardware devices, have heavy data ingestion systems. IoT applications will often generate large volumes of data from numerous devices. These need to be processed and analyzed in real time. PubSub provides a scalable and reliable way to do this. For instance, in a smart city project, IoT sensors might monitor traffic conditions, air quality, and energy usage. These sensors will publish data to PubSub topics, which are then consumed by real time data processing systems and analytics platforms. This might allow city admins to monitor conditions in real time and react accordingly every time they see conditions such as traffic congestion or pollution spikes arising. PubSub is a very important Google Cloud service. We can see that by looking at this architecture diagram on screen now, which represents a unified batch and streaming pipeline. This is known as a Kappa architecture. It takes in both historical data, which is effectively batch data, as well as real-time events and metrics. It aggregates them in a data flow and then makes all of this available for consumption over on the right. Let's only focus on the components towards the left of the screen. You can see here that we have historical data which is in cloud storage that is being fed in via a batch process into data flow. Now remember, the data flow is great about unifying batch and streaming processing, and that's why it's able to also deal with streaming data coming in from Cloud PubSub. The original data there is events and metrics, possibly from some IoT devices somewhere. So here, Cloud Storage and Cloud PubSub are the source systems. Dataflow is the transformation step, and BigQuery and Bigtable are the target systems or the sinks. Once the data has been ingested into these systems, it can then be consumed either via tools like Data Studio or Vertex AI and Vertex Workbench. And the end goal is data activation, i.e., the unlocking of value from the data, and for that, data needs to be made available to co-workers in the enterprise, and that's where all roads lead to, at the bottom right of the screen. This is a good case study of a complex unified batch and streaming pipeline, and you can see here that Google Cloud PubSub plays a key role here in the streaming analytics portion. Even after discussing all of these data-related technologies on the Google Cloud, we are still left with a grab bag of technologies that we haven't discussed, and that's the topic of this video. There are 4 technologies in particular that we ought to be aware of. The first is Google Cloud Composer, which we are going to talk about in more detail. The second is Cloud Data Prep. This is a data preparation tool which allows users to visually explore, clean, and prepare both structured and unstructured data for analysis. It has an intuitive drag and drop UI, and it allows users to perform data wrangling without writing any code. Data Prep integrates seamlessly with cloud storage, BigQuery, and other data sources. A fairly typical use case would be to have data in a file on Google Cloud Storage. This would be structured data in the form of a text or a CSV file. We would then open that with Data Prep, perform some pre-processing and cleaning, and then load the results into BigQuery. Another tool worth discussing is Data Catalog. This is a fully managed metadata management service which provides a centralized repository for storing and managing metadata so that users from all across the org can find and access the metadata they need. It supports features such as data tagging, search, and lineage tracking. This can enhance data governance and compliance efforts. A fourth service that's worth knowing about is Data Studio. This is a free web-based data visualization and reporting tool. You can use this to create interactive and shareable dashboards. It can connect to a range of data sources, including Google Analytics, Google Sheets, BigQuery, and other databases. Data Studio is user-friendly, it has a drag and drop UI, and you can use it even if you don't have any technical expertise. Of these 4, Cloud Composer is perhaps the most important and interesting, so let's come back to this one. Google Cloud Composer is a fully managed workflow orchestration service built on Apache Airflow. It allows users to create, schedule, monitor, and manage complex data workflows seamlessly. It automates the execution of tasks across different cloud and on-prem environments and helps with the orchestration of ETL processes, data pipeline management, and other automated workflows. It has close integration with various Google Cloud services, including, of course, BigQuery, Cloud Storage, and PubSub. Cloud Composer is built atop Apache Airflow. This is an open source platform for developing, scheduling, and monitoring batch workflows. The idea of Composer is that workflows are defined using Python code. That code gets executed and it's used to generate a pipeline dynamically, that is, at runtime. The Airflow APIs are extensible and they define operators so that the pipeline can connect to external technologies. Here is an architecture diagram of Composer. You can see that this is quite complex. Let's break it down a bit. To begin with, it's worth noting that every pipeline can be modeled as a directed acyclic graph. The edges between the nodes represent data, and the arrows represent the direction in which the data flows. The nodes represent tasks that need to be executed. Now remember in Composer that every pipeline workflow is represented as Python code. That Python code is parsed and stored in the DAG directory at the bottom. That directory holds the directed acyclic graphs for all pipelines that need to be run, and it's the scheduler's responsibility to actually trigger the execution of those pipelines. The way it does this is by submitting tasks to a component called the executor. The executor receives the tasks from the scheduler and then pushes out the execution of the pipeline to worker nodes. These worker nodes are actually executing the steps, that is, the nodes in the DAG. There's also a web server which can be used by users in order to keep track of the progress of the ETL pipelines. Composer also has a metadata database. This is used by the scheduler, the executor, and the web server to store state. The DAG directory will contain DAG definitions and code. These are going to be accessed by all of the components in Airflow. And now, having gone through all of these components step by step, the Airflow architecture makes a lot more sense to us. A couple of attractive features of Cloud Composer and Airflow: there's no installation or management overhead needed, and managed Airflow environments can be created very quickly. We started this course off by diving into batch and stream analytics, focusing on their distinct advantages and use cases. We examined the processes involved in ETL, that is extract, transform, and load, and ELT, that is extract, load, and transform pipelines, learning how they support data integration and preparation for analysis. These foundational concepts set the stage for understanding how data can be processed and analyzed in different scenarios, whether in batch mode or interactively and in real time. Next, we learned about the characteristics of Dataproc, Google's managed Spark and Hadoop service, which simplifies big data processing on the cloud. We explored various Google Cloud services for ETL, such as Dataflow, which offers real-time stream and batch data processing capabilities. Understanding these tools helped us appreciate their roles in building robust and scalable data processing pipelines that cater to various analytical needs. Finally, we explored real-time messaging with PubSub, Google's service for ingesting event data from multiple sources, which supports real-time analytics and data integration. We also learned about Cloud Composer, a fully managed workflow orchestration service, along with other data-related technologies, gaining insights into how they facilitate the management and automation of complex data workflows. In conclusion, we've built a solid foundation in data processing and analytics using Google Cloud's suite of tools. We covered batch and stream analytics, ETL and ELT pipelines, and gained a conceptual understanding of Dataproc, Dataflow, PubSub, and Cloud Composer. We are ready to move on to the next journey in this course, AI and ML on the Google Cloud.